In Italy, a catastrophic crane collapse on a major construction project.
Once this crane started to go, nothing was going to stop it.
In Massachusetts, devastation as a high-rise comes crashing down to earth.
One eyewitness said the sound was like 10 jets taking off. How could a 16-story building just crumble to the ground?
In New York State, disaster strikes a vital river crossing.
It was cataclysmic, it was sudden, and it was violent.
And in Sweden, chaos as a bridge build smashes onto a railway line.
It was shocking. All that concrete absolutely collapsed. This was a major accident.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. For engineers, protecting big structures against the elements is an ongoing battle. Overlook one detail, and the results can be catastrophic. Like this deadly bridge disaster in New York State that felt the full force of Mother Nature.
The bridge crashed more than 25 meters into the river below, taking vehicles down with it.
The devastating collapse of a crucial crossing.
A truck was found more than half a mile downstream because there was so much water moving through this channel.
This tragedy caught everyone by surprise and left local citizens reeling.
We're talking 84 to 100 feet of just steel and cement crashing into this roiling creek below.
With more than 6.5 million kilometers of thoroughfare, the US has the largest road network in the world. And one of the nation's most important stretches is this, Interstate 90.
The I-90 is the longest highway in the entire US and stretches over 4,800 kilometers from Boston in the east all the way to Seattle in the west.
One key section of I-90 is the New York Thruway, running over 600 kilometers from the Massachusetts border to Lake Erie. Mark McGuire is a retired journalist.
The New York State Thruway is a major corridor in the Northeast for both pleasure travel and commerce. So this has been a traditional thoroughfare for America.
In a state carved up by water, the Thruway has a staggering 815 bridges, including this one. The 165-meter-long Schoharie Creek Bridge, crossing waters that flow down from the Catskill Mountains.
The Schoharie Creek, you can see it in the summer here. It is placid, it is calm. In the spring, when you have a combination of rain and snowmelt, you could turn a placid body of water like this into a raging, roiling river.
And a fast-flowing river can be very dangerous for bridges, causing a type of erosion known as scour.
Scour is one of the great challenges of river engineering. Fast-moving water can erode or scour away the soil around the base of the shallow footings, leaving the piers exposed to the elements.
But, like many bridges, here the piers are protected against scour by a layer of stone or rock called riprap.
You'll often see riprap, or rocks, placed around structures to protect not only against scour, but also wave or ice erosion.
Geotechnical engineer Peter Deming explains.
Riprap is a large stone, and usually it's a broken stone so that it interlocks and has a high friction and it joins with other rocks. The water tries to move the riprap and it can't get below the riprap because the riprap is so heavy and it's able to stay in place even with the water flowing by. The riprap is what prevents the scour from reaching deep.
The bridge standing today opened in 1988, but it wasn't the first crossing here. Its predecessor was built in 1954 to coincide with the opening of the thruway. For more than 3 decades, the first bridge served as a vital passage around 25 meters above Schoharie Creek, widely used but largely unnoticed.
Drive this thruway every day, you drive highways like this. You go over this, it doesn't even look like a bridge. You just think it's another patch of road.
The Schoharie Creek Bridge wasn't intended to be iconic or eye-catching. It was just a run-of-the-mill interstate bridge like you'll see crossing numerous waterways all over the US.
But in 1987, one devastating event etched the bridge into the minds of people across the country. April 5th, 2 days of heavy rain had caused the Schoharie Creek to swell to dangerous levels.
As a precaution, other bridge crossing the creek had been closed earlier that morning. Although the I-90 crossing was inspected, it was decided to leave this vital connection open.
A few minutes later, at approximately 10:45 a.m., disaster struck. At the time, Mark Maguire was a 23-year-old local journalist.
I first heard that there had been a bridge collapse and that the thruway was closed. And I tried to get as close to the scene as possible.
Mark was unprepared for the scale of the devastation he was racing towards.
People who witnessed the collapse, and there were more than a few, all had the same description. It sounded like an explosion.
People on the bridge downstream thought it was a bomb, and then the bridge dropped into the water in fractions of a minute.
We're talking 84 to 100 feet of just steel and cement crashing into this roiling creek below.
4 cars and 1 truck went down with the bridge. Emergency responders rushed to the scene.
State police, the sheriff's department, divers. There was even an aircraft searching the water. But in this raging torrent, it soon became clear that the likelihood of a rescue was gone.
The truck and the automobiles that came down were found in the Mohawk River more than half a mile downstream because there was so much water moving through this channel.
10 people were in the 5 vehicles that fell into the water. Tragically, none survived.
1 minute's there, next minute's not. It was a dark day.
A vital connection was now gone, lying in the creek below. And people wanted to know, how could an interstate bridge 25 meters above the water be destroyed by a swollen creek? One key suspect was the bridge's shallow foundations. Geotechnical engineer Peter Deming helped spearhead the investigation.
The investigation needed to remove the water so we could look at the foundations. So we brought in demolition contractors to remove the slabs that were still up in the air to make it a safe investigation. And we were able to go in after drying it up and do a physical examination of the pier.
The soil beneath the pier foundations had been severely eroded by scour, creating a hole around 3 meters deep, causing the pier to sink down on one end and the bridge above to collapse.
The center pier dropped on the upstream side, and both pieces of the bridge were supported on that pier, and so both spans collapsed into the water because the pier lost support on the upstream side.
Gerard Butch was the project chief tasked with investigating bridge scour across the entire state.
Scour is the most common cause of bridge failure. It's the erosive action of flowing water that removes material from the stream bed. It's a natural phenomenon. So the thinking was that it was sturdy enough to withstand scour.
It was assumed the bridge piers had been protected by the huge rocks or riprap surrounding the base.
The design put riprap, large rocks, around the foundation, and the energy of the water is supposed to be working on those large rocks. And the energy of the water can't get to the foundation because it's trying to shift those large riprap rocks.
But the investigation discovered that most of the riprap was missing.
When we looked at Pier 2, we collected all the riprap from the creek channel and we made a big pile. And we compared it to the quantity of riprap that was shown on the drawings, and the quantity of riprap that we found was 25%.
Without the riprap, these shallow foundations were missing the one thing that was designed to protect them.
So where had all the riprap gone?
The investigation found that riprap placed along the piers had mostly washed away in a massive flood more than 30 years earlier. And despite numerous inspections, it had never been replaced.
When the massive 1987 flood hit, years of scour finally took the bridge down.
Hindsight's a wonderful thing, but not closing that bridge proved to be a tragic mistake.
This was one of the deadliest bridge disasters in US history, and action needed to be taken. Today, Gerard Butch from the US Geological Survey is part of a team monitoring the modern-day threats.
The collapse of the Thruway Bridge resulted in the New York State developing a bridge scour project. The force of water should never be underestimated. The riprap has to be maintained.
High-tech underwater scanners are key to the inspections.
The multi-beam echo sounder is producing a three-dimensional map of the water depth in the channel so we can see where the rocks are, where the scour holes are. This is indicating that the top of the spread footing has been exposed by scour, but it's certainly not in any danger of compromising the bridge.
When you're in a case where you have scour, you need to be maintaining your scour prevention, your riprap, and you need that to be full-time because the creek will flood when the creek wants to flood. It's not going to wait for your next maintenance program.
These readings are revolutionary compared to 1987. Back then, someone would literally have to wade into the water, take a manual depth measurement one dip at a time.
The new bridge, completed in 1988, was built stronger with bigger footings, supported by pilings driven deep into bedrock. And although lessons were learned, the lives that were tragically lost on that day will long be remembered.
It really was a story that touched so many different lives and so many different people in so many different ways. And it's a story that's still being written.
With big construction, how you build is just as important as what you're building. The smallest mistake can have dramatic consequences. Like this catastrophe in Italy that derailed a new bridge.
With this lift, things went spectacularly wrong.
As big engineering went up against gravity and lost.
Once this crane started to go, nothing was going to stop it.
Varese, northern Italy, is nestled into the shadows of the southern Alps. The striking landscape helped earn this town the nickname Garden City. Nicola Antonello is a local journalist.
Varese è chiamata la città giardino per via dei suoi parchi, delle sue ville d'epoca, che sono l'eredità dei signori ricchi milanesi che qui stabilirono la loro dimora estiva. Adesso questi parchi sono a disposizione spesso del pubblico e sono collocati comunque in un'area molto verde con parchi, colline e tantissimo verde.
The landscape in this region is stunning. The lakes and hills have long been a draw for tourists.
But tourists have to share these hilly roads with commuters from both sides of the nearby border with Switzerland.
Every day, thousands of people cross the border here to get to work in Italy or Switzerland. So in 2010, work began on a new rail link that would make the commute both quicker and smoother than by road.
Crossing over the hilly landscape, this was the key to the new line, the Bavera Viaduct. The 438-metre structure consists of 7 bridge spans intended to ease the journey across the valley.
Trains work best on tracks that are straight and level, so they can keep a nice, constant speed between stations. But there are lots of parts of the world, like here in northern Italy, where geography gets in the way, and engineers are forced to build tunnels and bridges.
Although the Swiss section ran on relatively even ground, in Italy engineers faced natural obstacles. Riccardo Assetti is a local engineer.
Questo viadotto ferroviario, che poi vediamo meglio rappresentato nelle fotografie qui sopra esposte, è stato realizzato a una quota ben definita rispetto alla quota del terreno esistente in funzione di quello che era il progetto ferroviario, che non può, proprio per motivi tecnici, avere continui sali, scendi nel suo percorso, ma deve essere il più omogeneo possibile.
As with any bridge, engineers had options when it came to construction.
When constructing a bridge, you can build temporary wooden molds and cast your decks in their final position, or you can make them on the ground and lift them into place using a crane. Each has its own benefits and risks.
In the shallow valley, the bridge ranges from 3 to 18 meters high, which is within easy reach for a crane. So, engineers opted to lift the deck spans from the ground. On May the 9th, 2017, a massive crawler crane was in position, lifting one of the decks, while hundreds of locals looked on.
Engineers have been working on this new line for years, boring tunnels and constructing the new viaduct. Now they were lifting one of the last sections into place. The anticipation was huge.
Sul cantiere c'erano una quarantina di persone, tecnici, operai, ma anche persone che, vista la dimensione del cantiere, della campata e delle gru, si fermavano a filmare e a osservare questo che per loro era uno spettacolo.
But that evening, things took a dramatic turn.
This viaduct had 7 spans. 5 had already been lifted without a hitch, but this time, things went spectacularly wrong.
And it was all captured on film.
Once the crane started to go, nothing was going to stop it.
In 10 secondi si è ribaltato tutto.
Horrified workers and bystanders ran to help. Incredibly, no one had been seriously injured.
Il vero miracolo di questo incidente è che il gruista, cioè l'operatore della gru, è riuscito a salvarsi senza riportare un graffio.
If you look very carefully, just as the crane finally smashes down, the driver comes running from beside the track. This couldn't have been any closer.
The crane and bridge section were destroyed, and local communities were in shock.
Nei giorni successivi moltissime persone sono venute sul luogo dell'incidente per fotografare, fare video e vedere il disastro.
As the dust settled, everyone wanted to know what had gone so wrong. Although the cause hasn't been made public, strong clues were caught on camera.
From the video, you see the back of the crawler start to lift. That's a sure sign that the system is losing balance. And once that happens, there's nothing anyone can do.
Maintaining balance is crucial for any lift, but gravity is powerful and dynamic, constantly working against the crane to bring its load back down to Earth.
The further a crane reaches, the more effort force there is pulling down on the boom. Just like when you lift something with your arm outstretched, it feels heavier than close to your body.
To help balance out those forces, cranes have counterweights known as ballast, but they still have their limits. Push them too far and over you go.
With this crawler crane, the counterweights were attached to the back of the cab and suspended from a rear arm known as the mast. But here, as the load was moved further from the crane, the delicate balance failed. Civil engineer Riccardo Assetti demonstrates.
Tenendo fissa la posizione del contrappeso, può variare la posizione invece del carico che noi andiamo a collocare in quota, per esempio la posa della trave a una certa altezza. Man mano che io sposto il carico che sto collocando in quota rispetto al basamento della gru, rispetto al piano di appoggio della gru, noterò che il contrappeso, pur collocato in maniera idonea, potrà non essere più sufficiente a garantire l'equilibrio del sistema.
With the crane's balance compromised, the ballast on the mast shifted, which spun the crane sideways.
Se giro di 90 gradi lo stesso sistema, spostiamo la distanza, o meglio, facciamo diminuire la distanza tra l'elemento che può stabilizzare e il punto di rotazione stessa, cosa succede? Succede che la gru si ribalta.
Although no one was hurt, local residents were worried the project would be indefinitely suspended. But just 3 months later, a new span was lifted into position with perfect balance, and the viaduct was one step closer to completion.
Every project has dozens, if not hundreds, of risky moments. This is just a reminder that just when it seems everything's going according to plan, something can always go wrong.
The new viaduct opened on December the 22nd, 2017, and trains have safely been using it ever since.
Ai cittadini alla fine con l'inaugurazione hanno vissuto due sentimenti. Da un lato la soddisfazione di un'opera che finalmente rendeva Varese una città più internazionale e dall'altro lato un sollievo perché finalmente dopo 8 anni di cantiere la ferrovia era terminata.
When it comes to big construction, meticulous planning is crucial for every step. Because any mistake at any stage and the results can be devastating. Like this construction disaster in the heart of Boston.
This should have been a routine build, but it went disastrously wrong.
An apartment building collapse on a catastrophic scale.
First the roof, then the next floor, then the floors go one by one and the whole building collapsed.
And a tragedy that shocked an entire city.
People couldn't see anything. People were screaming. I mean, how could a 16-story building just crumble to the ground?
Boston, Massachusetts, founded in 1630. It's one of America's most celebrated cities. Local journalist Fred Tice knows what makes this town tick.
Boston is a special place for one thing because it's such a historical place. This is an old city, several centuries old, and many remnants of that history can still be seen today. It's become a very cosmopolitan city. You really have people coming here from all over the world.
This charismatic city is also a big draw for students. Boston reporter Emily Sweeney is proud of her hometown.
I was born and raised in Boston, and I think it's one of the best cities in the world. It's a big college town, really well known for its education.
Boston has a strong tradition of attracting and producing some of the finest minds in the country, with world-renowned institutions like Harvard and MIT adding to its cutting-edge academic clout.
Boston is perhaps the greatest academic center in the United States, and it's also a really important center for high tech and for biotech.
But with a relatively small footprint for such a major city, Boston's limited space has been stretched thin as it continues to draw in new residents.
There's so many people in the metropolitan area that it's become very densely populated, and if you drive around here, you will notice that the streets are very congested. Boston is the fourth most congested metropolitan area in the United States after New York, Los Angeles, and South Florida.
One solution was to go up rather than out with buildings like this. Containing 17 stories of living space, it towers over its neighbors.
We're in front of 2000 Commonwealth Avenue, and a lot of the residential neighborhoods of Boston, there's a lot of older houses, Victorians, three-deckers. You know, high-rises are kind of few and far between, and this one was one of the few that was, being built at the time.
This building opened in 1984, but it wasn't the first structure on this site. The original tower was a 16-story cast-in-place flat slab construction. 19mm thick precast concrete slabs would sit on columns. Each slab was then held in place by temporary supports known as shoring, while another layer of concrete was poured on top, completing each floor.
Cast-in-place reinforced concrete flat slab construction is popular for multi-storey buildings because essentially there are no beams.
Construction on the original tower began in 1969, and while the current building now houses more than 500 students, its predecessor would never see a single resident. January the 25th, 1971, with construction nearly complete. Around 100 workers were on site when trouble started.
It was a Monday. It was around 3:30 in the afternoon. Suddenly, there was this sound. Workers could hear creaking, moaning, groaning.
The foreman immediately yelled a warning to the workers on the 16th floor of a possible roof collapse.
Minutes later, disaster struck.
Suddenly, the building came crashing down.
The entire east side of the building, 16 stories high, had collapsed all the way down to the basement below.
Some people said it kind of went down like dominoes. One eyewitness said the sound was like 10 jets taking off. Dust filled the air. It was a chaotic scene. Police and first responders were trying to get to the scene, but given it was like in the afternoon, right before rush hour, they couldn't because there was so much traffic.
Of the 100 or so workers on site at the time, most but not all made it out. Around 30 were injured, but tragically 4 lost their lives.
If you see the size of the building and just like where it fell in the middle of a busy urban neighborhood, it's really a miracle that more people weren't hurt or killed.
The tragic and catastrophic destruction shocked the entire city, and Bostonians wanted answers.
Everybody in Boston was wondering, how could this happen? Were there any warning signs? How could a 16-story building just crumble to the ground?
The mayor of Boston appointed a special panel to investigate the cause of the disaster. Based on eyewitness accounts, the structure had started to fail shortly before the fatal collapse. Mehrdad Sassani is a professor of structural engineering.
First, the roof of the building failed. It took some time for the roof to fall on the next floor. And after it fell, the progression was very fast. Floors go one by one, and the whole building would have collapsed.
This progression is characteristic of a type of failure that can threaten concrete slab construction, known as punching shear.
Punching shear failure happens when a slab is either too weak, overloaded, or when any supports or connections below don't have enough strength to hold the slab up.
Punching shear can often cause the rapid collapse of an entire building. But here, after the initial fail, the slab began to sag, buying workers valuable time.
Luckily, the collapse happened relatively slowly, taking more than 10 minutes, so most of the workers had time to escape.
As the roof slab finally collapsed onto the floor below, the sudden impact and extra weight of concrete was too much for the structure to bear, creating a domino effect all the way down to the basement. Punching shear is a well-known phenomenon, so the big question here was not how it failed, but why. The first suspect was the temporary supports or shoring.
At the beginning, concrete does not have the strength to carry its own weight. Therefore, the weight of the concrete needs to be transferred to the slabs below. The shoring would function as that vertical element that support the weight of the newly poured concrete.
It's a crucial stage of construction because the higher the floors, the younger and weaker the concrete is. But here, witnesses reported that there were too few shoring poles to support the slabs.
Not only was there insufficient shoring, but the concrete itself was flawed.
When we look at punching shear failure, there are two important factors that come to play. One is the slab thickness, one is the concrete strength. The concrete was not protected against the cold weather, and as a result, the concrete strength at the time of collapse is estimated to be less than 2/3 of the strength that it should have had.
The investigation found that leaving this fresh concrete exposed to the cold had prevented it from curing or hardening properly.
If freshly poured concrete cools below 0 degrees, the water in the mix can freeze and expand. Potentially, this can damage concrete so much that it becomes useless and has to be replaced.
Here, the average daily temperature was -4 degrees, and the concrete wasn't being protected against the effects of cold weather.
In freezing winters like Boston's, this caused a major problem.
The Mayor's Commission cited a catalogue of errors that contributed to the collapse, but in the end, it concluded that the primary causes were low concrete strength and a lack of shoring. Tragically, in this case, they proved to be fatal.
After the disaster, a large section of the building was left standing, but was structurally unsafe. A year later, it too was brought down.
It wasn't until July 1972 that there was a demolition of the building. A huge crowd gathered, and the skeleton of the building, everything that was left, just came down.
And while it has taken time, the devastating collapse eventually helped lead to a change in protocol.
So the failure of the 2000 Commonwealth Avenue has led to changes in the code to make structures more integrated, as well as the importance of better construction practices in terms of better quality concrete, as well as protecting fresh concrete against cold weather.
It's important for people to remember what happened here and the men who lost their lives here and the lessons that we've learned from it so it never happens again.
When it comes to big engineering, design and construction must go hand in hand. Even the most basic oversight can lead to major catastrophe. Like this construction disaster in Sweden, where devastation struck on a crucial crossing.
It was shocking. All that concrete absolutely collapsed. This was a major accident.
A bridge catastrophe that caught everyone by surprise.
I had never seen an accident like that before. You don't know who's under there. It was just a disaster here.
And a sudden collapse with workers still on top.
One man, he was covered in concrete from bottom to top. Concrete is like mud, it sucks you in.
Around 200 kilometers northwest of Sweden's capital Stockholm lies the small town of Ludvika. Although its modern-day population is just under 15,000, it was once a powerhouse at the heart of Sweden's lucrative copper mining industry.
One mine, about an hour from Ludvika, was once the largest copper mine in Europe. As an added benefit, the leftover rock could be turned into a hard-wearing, bright red paint, which has become famous across Scandinavia.
With the mines came the railroad to move this valuable metal out for production, a vital means of transportation that Ludvika still relies on. Anders Hansson is a TV reporter.
It's vital for this region that the train keeps running. A lot of people commute from other cities, and we have to ship out a lot of industrial goods.
Running right through town, the railroad separates the community from Ludvika's main source of recreation, Lake Väsman, making this bridge one of the busiest thoroughfares in town.
There's the town on one side and there's the lake on the other. The lakeside is very popular. The bridge is the only place where you could cross the railway.
The first bridge built here in 1905 was a single-lane steel crossing that was struggling to cope with the demands of modern traffic.
The old bridge was a quite narrow steel bridge. One lane, so 2 cars couldn't meet on the bridge. Tricky for the community to reach the lake. So they demanded a new bridge to be built.
The old bridge was very bad. It didn't do its job. People had to wait for other cars since they could not pass on the bridge. A new bridge was badly needed.
In 2017, construction began on a bigger, better crossing. But with a busy rail line running directly below the worksite, the team needed a strategy to build without halting train traffic.
To minimize disruption, the bridge will be built using a technique known as cast in situ.
Wooden moulds, known as formwork, built in the shape of the bridge, raised up and supported on top of temporary steel supports.
The concrete is then poured into the mold, and when hardened, the deck is simply lowered into place.
This is a tried and true technique, allowing entire bridges to be built while traffic continues to flow below. Thursday, July the 13th, 2017, shortly after 2 p.m. As engineer Jens Skans explains, construction of the new bridge was well underway.
They had poured about 2/3 of the concrete in the wood frame, and the midsection was taking its full load.
Around 15 workers and 700 tons of concrete were overhead, when suddenly, the entire section came crashing down.
First there was a large bang, followed by a snapping, popping sound. A few seconds later, the wood frames started to crack, crumble, and the bridge collapsed quite fast.
As reports of a disaster began filtering in, local journalist Lotta Ullin received a call from her producer to get the news on air fast.
As a reporter, I'm used to report from accidents, but I had never seen an accident like this.
The wooden formwork, steel, and tons of wet concrete had fallen onto the active train track below, taking the workers on the bridge down with it.
It was just a disaster here. A lot of people around the place that are wondering what has happened. It's quite scary because you don't know who is under there. We didn't know if there were people that was hurt.
Reporter Anders Hansson also witnessed the devastation firsthand.
this was a major accident. It was shocking to see all that concrete that had absolutely collapsed. From the looks of it, I was expecting casualties.
Especially since one worker was thrown headfirst into the wet concrete.
He was covered in concrete from bottom to top.
The rest of the team there were trying to pull him up because he couldn't get up.
He was submerged, head down in the concrete, and it's so thick that you can hardly move in it because concrete is like mud, it sucks you in. Scary.
Thankfully, the worker survived. And while 11 more were injured, 6 of them seriously. Despite the devastation, there were no fatalities.
This thing was so big, you wouldn't believe. It's only when you stand there and look upon it that you realize how big a bridge of this kind really is.
Tragedy had been narrowly avoided, but with the railroad in chaos, people wanted answers. Engineer Jens Skans from the Swedish Work Environment Authority was part of the investigation, which began by examining the steel in the incomplete bridge structure.
We found a lot of snapped metal pieces. We found a lot of bent steel beams. Not a single piece that was straight anymore. It was all bended or broken in some way. We checked it to the drawings, and our opinion is that at least the framework and the steel and so on, it matched. It matched the drawing.
The structure seemed to be built according to the designs, so in theory, the falsework should have been able to carry the weight of the concrete. But in reality, things didn't go to plan. The obvious question was, why?
Attention turned to the wooden mold where the concrete was being poured.
The wooden formwork was harder to inspect because it was cracked, crumbled, and we checked what we could check, and we didn't find anything that caught our attention.
With the cause of the disaster still a mystery, investigators shifted focus to the steel falsework. They found one key component had been overlooked in the original plans.
Normally, when you build a scaffold, you have to make sure that the load is spread evenly. And to do that, you have to have a lot of diagonals, creating a pattern of loads taking the weight down to the ground. And one of the reports point that there are too few diagonals supporting in this steel frame.
A miscalculation meant bracing was missing, crucial for resisting any lateral or horizontal movement when concrete is being poured.
When you're pouring tons of heavy, wet concrete, one thing you're going to get is movement. So if that isn't properly braced, any lateral movement could bring the whole thing crashing down.
The weight and motion of the wet concrete overwhelmed the temporary structure, causing the catastrophic failure.
At the end, they found that the bracing that was supposed to hold up the mold was too weak. They had been working so hard in order to try to make the trains run all the time. This was really bad.
With a vital connection severed for both commuters and commerce, a fix was needed fast.
Since the railroad is so important for this area, they wanted to open the tracks again as quickly as possible. So they had to work very hard for a couple of weeks in order to clear the tracks again and get the trains running.
Once the debris was cleared, the bridge was rebuilt. This time, both the wood and steel were up to the job. And not only are the trains rolling once more, but Ludvika's citizens can now easily access the natural beauty of Lake Väsmen just across the tracks. In Pennsylvania, a historic bridge does battle with Mother Nature.
Oh, man! It was like listening to a train wreck.
A New York neighborhood is rocked by a construction catastrophe.
I don't know what's going on, but it's big.
Somebody came in and said, house collapsed.
In Naples, disaster nearly destroys a hospital.
People thought a bomb had gone off.
And in the UK, a key viaduct starts cracking at the seams.
There was all sorts of people working 24 hours a day, floodlights, the lot.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Even with the strongest structures, engineers are in a constant battle with the forces of nature. Underestimate their power, and the results can be catastrophic. Like this disaster in Pennsylvania. Dramatic destruction that caught a city by surprise.
This lady starts screaming, "The bridge is falling, the bridge is falling."
A landmark crossing torn from its foundations.
I never thought something that was so solid could possibly be swept away. It really scared me.
As Mother Nature goes head-to-head with engineering.
It was a demonstration of the power of water that I had not seen before.
Harrisburg, as Pennsylvania's state capital for more than 200 years, it's divided by the river that runs through it, the Susquehanna. Sue Yenchko is a long-standing resident of the West Shore community.
We are on the west shore of the Susquehanna River, and Harrisburg proper is on the east shore. Most people think Philadelphia is the capital, but it's Harrisburg. That's where the Capitol and all the state government buildings are. There are a lot of state employees who come and go from the east to the west shore.
With many bridges now spanning the river, commuting couldn't be easier. But back in the 1800s, there was only one option. The Market Street Bridge, and crossing it wasn't cheap.
With only one bridge over the river here, owners had a monopoly. And for 70 years, they could effectively charge as much as they wanted for people to use the bridge.
People were really getting fed up with the ever-increasing toll prices to cross the bridge, and from that disquiet came the People's Bridge, to show the people were going to have their way to get into Harrisburg, too.
Like many crossings of its day, the People's Bridge, also known as the Walnut Street Bridge, would be a through truss design. But crossing the wide and mighty Susquehanna with steel would be no walk in the park. So, as State Museum curator Robert Hill explains, engineers took advantage of the natural midstream city island.
The river's about 3/4 of a mile wide in this area, and because of that, City Island was used as a midpoint for the central section. So it's not really one bridge, it's two bridges with the embankment in between. You have one bridge that runs from Walnut Street, where the name comes from, to the island, and then another section that runs from the island to the West Shore.
The two halves of the Walnut Street Bridge combined were more than 800 meters long, made up of 15 wrought iron spans, 8 to the west of the island and 7 to the east, all supported by huge stone piers.
Opening in April 1890, the Walnut Street Bridge was an immediate success, charging just 2 cents to cross, which was less than half the cost of its rival. And the people loved it.
It was a much more picturesque bridge because there's a beauty to the design. And so it really was the future.
This futuristic bridge carried people to and from the capital for more than a century, until one very harsh winter. January the 20th, 1996, an unprecedented cycle of freezing and thawing left its mark on Harrisburg.
The winter of '96 had been very severe. About 2 to 3 feet of snow had come down, and there was a great deal of ice on the river, combined then with the problem of a heavy rainstorm that thawed the snow, flooded the river, broke up the ice so that it put all of that tremendous power of flowing water up against the bridge.
With the floodwater rising, huge chunks of ice were now pressing hard against the top of the 106-year-old Walnut Street Bridge. Local resident Teresa Irvin McCurdy was filming the icy river.
There wasn't really a lot to see at the time, and this lady starts screaming, "Bring the camera, the bridge is collapsing, bring the camera!" And I'm like, what? And as soon as I saw it, I just zoomed right in on what was happening and couldn't believe it.
Oh, man!
2 entire spans were being forced off their piers by the ice and water.
It literally was strong enough to pick up the bridge and carry it downriver. It was just an unbelievable sight.
From her apartment overlooking the bridge, Sue Yenchko also witnessed the disaster unfolding.
I came upstairs to use the phone, and as I was talking, the pieces of the bridge started to move away from the bridge, being carried on top of the ice.
This was incredible. Not only had the massive wrought iron spans been shoved off their piers, they were now moving downstream on a raft of ice.
Residents watched powerless as the bridge was torn apart.
I did feel helpless because I said to myself, call 911, and I thought, what will 911 do to a bridge that is floating down the river?
Instead, Sue captured the catastrophe on camera. But from her vantage point, she feared the disaster was far from over.
It's gonna hit the other bridge!
I was afraid that it was going to topple the Market Street Bridge and keep going and topple the next bridge and the next bridge. I thought disaster was striking.
Ironically, it looked like the 2 spans were about to take out the crossing they had been designed to compete with.
When it hit the Market Street Bridge over here, it just let out this loud, crinkling sound.
It was like listening to a train wreck. I've never heard anything quite like that. I thought the bridge was screaming.
Amazingly, the Market Street Bridge stood firm against the huge collision.
As it hit the bridge, the current pulled it underneath the stone arches
and broke up into pieces and crumbled underneath.
In total, 3 spans of the Walnut Street Bridge were destroyed, lying in a twisted mass of metal at the bottom of the Susquehanna River.
The Walnut Street Bridge is part of the history of this area, so to see something like that get damaged so quickly and just disappear, that was very sad.
Luckily, no one was injured in the disaster, but a large part of the so-called People's Bridge was gone.
It was a shock. Still can't believe that, 1, it happened, and 2, that I was there to be able to film it.
As the waters subsided, many were left wondering whether the collapse was down to the elements or engineering.
The extreme conditions ranked among some of the worst the state had ever seen. From record snowfall to an unexpected thaw, which sent snowmelt flooding into frozen rivers. There were huge forces at play.
All that power headed straight for the aging Walnut Street Bridge. Abdullah Shafizadeh is an associate professor of civil engineering.
There are 2 forces that are applied to bridges subject to flooding events. One is the drag force that is applied in the horizontal direction. And the other force that can be applied to bridge decks is the uplift force. Immense amount of forces are applied vertically, and it can lift the deck and lift it off from the bridge piers.
Due to its design, this bridge was more vulnerable to uplift than its neighbors.
The main force holding these trusses in place is essentially gravity. When they were built, engineers hadn't anticipated such extreme weather. So being shoved hard from one side just wasn't a factor.
A bridge typically is made to deal with forces vertically, what's on the bridge surface being carried down on the piers to hold it. This is then a horizontal force, and with ice there, now you have the force of the river building up behind it and continuing to push against it.
In a normal flood, water can work its way underneath the bridge, but here, huge slabs of ice were building up against the side, almost like a dam, focusing all that power onto the bridge deck.
If the level of the flood and the ice reached the deck, then that would apply immense drag forces and also uplift forces, and that can eventually lead to the collapse of the structure.
It was a demonstration of the power of water that I had not seen before. A great deal of water moving with incredible force against a structure that's trying to stay in place. And it was the irresistible force moving it out of the way.
As well as massive forces pushing against the bridge, something else may have been at play underneath. The scourge of bridge engineers across the world. Scour.
Scour is one of the great dangers to bridges, where water flowing fast around the base of the pier erodes the foundations. And here, it had been doing it for more than 100 years.
Scour is one of the main causes of bridge failure in the US. But with the fast-flowing river also heavily iced over, things were made a whole lot worse.
The problem becomes more severe when we have ice cover, particularly rough ice cover, which increases the velocity of the flow, and that can intensify the formation of a scour, in turn impact the integrity of the piers, move them away from their foundation, and then unseating of the bridge deck and eventually collapse of the structure.
In the end, the flooding combined with decades of scour proved too much for the century-old People's Bridge.
All of that tremendous power of flowing water, you could see afterward, had pushed those heavy stone piers quite literally back several feet before tearing the iron off the top of them and taking them down to the Market Street Bridge.
In the aftermath of the disaster, the Walnut Street Bridge was closed and the huge cleanup job began.
The next step, of course, was to make sure that the Market Street Bridge was still structurally safe, but then they also had to take up all the old pieces from the bridge up out of the water, since boats do go up and down the river.
And while the Market Street Bridge was given a clean bill of health, the People's Bridge wasn't so lucky.
The sad thing is, the cost of restoring the entire bridge was just too much to ever have it done.
Today, most of the bridge remains intact, serving as a constant reminder to the people of Harrisburg. Maybe one day, this historic crossing that stood firm for more than a century will rise again.
This whole event was extremely unexpected, and one in which I'll never forget.
It was a symbol. It started out as the People's Bridge because it's a beloved bridge, and it just got some teeth missing from it now.
In engineering, every part has to work together in perfect harmony. Overlook one piece and everything can come crashing down. Like this disaster in New York that struck a Brooklyn condo build.
I don't know what's going on, but it's big.
Somebody came in and said, house collapsed in Brighton Beach.
They watched it just pancake in on itself. It just sounded like an explosion.
engineering errors that ended in tragedy.
There was no warning and nothing anyone could do to stop it.
This must have been a cascade of failures. More than one thing had to go wrong.
New York City is world famous for its iconic Manhattan skyline, but it isn't actually the most populated borough in the vast city.
With more than 2.5 million residents, Brooklyn is the Big Apple's most populous borough. If it was a city in its own right, this would be the 4th largest in the nation.
And within Brooklyn, each neighborhood has its own distinct identity, like here at Brighton Beach. Pat Singer is director of the Brighton Neighborhood Association.
We're in the place that I love. This is Riegelman Boardwalk and our famous Brighton Beach. I fell in love with Brighton Beach coming here as a child. For me, it's been a kaleidoscope of experiences because it's ever-changing and just ever-beautiful.
Local journalist Hannah Frischberg knows the area well.
Brighton Beach is definitely a different vibe than people associate with New York. People think of Manhattan, they think of Times Square, and they think of the big tourist hotspots. And then Brighton is very residential. People down here, they still got extended families living with them.
But in this fast-moving city, nothing stands still for long.
Demand for property in the 5 boroughs keeps growing, so developers are constantly working on new projects to bring more housing to neighborhoods like Brighton Beach.
In August 2011, work began on a new condominium in Brighton Beach. Adrian Brugger is a civil engineer.
It's a 5-story multi-apartment building with about 20 units and parking on the first floor. So this is what one would expect in developments in that area.
The structure was relatively conventional in layout. A concrete core surrounded by a steel framework of columns, girders and joists, onto which the concrete floor slabs would be poured.
Each steel and concrete floor would also double as the connection from the outer wall to the solid core of the building, tying everything together.
As structures go, this one was relatively straightforward. And in true New York style, it was going up fast.
4 months into construction, the first 2 levels were complete, as was the steel framework for the upper levels.
The construction at this time was progressing relatively quickly, as in the core of the building was already in place. This was concrete masonry unit surrounded by steel columns, and then light steel extruded sections on the outside. And at this time, the contractors were pouring the 3rd and 4th floors of concrete.
On November the 8th, contractors were on site to pour the 3rd level. At 2:30 p.m., disaster struck. Local resident Pat Singer heard the news.
I had a storefront office. Somebody came in and said, house collapsed in Brighton Beach, you know, and oh, but you couldn't get over there because there was so much ambulances and fire department, everybody over here.
The front of the building had failed catastrophically.
People who were in the area when the building went down said it was horrible. They said that they watched it just pancake in on itself. They said it just sounded like an explosion.
These workers were focused on pouring the concrete. They had no idea anything was wrong until the structure just dropped.
Tons of concrete and steel had collapsed. Emergency services worked tirelessly to rescue the workers, but for one member of the team, it was too late. Engineering professor Adrian Brugger knows the story.
Tragically, 1 construction worker lost their life and 4 more were gravely injured.
I think there are a lot of bad construction stories in New York. I mean, there's just a lot of construction in New York, but any time that something ends in a loss of life, it is a headline.
With the building in ruins, New Yorkers were demanding to know what had caused the catastrophe.
As a civil engineer, I know that for something like this, for a structure under construction to actually collapse to the extent that this has collapsed, more than one thing had to go wrong. This must have been a cascade of failures or bad decisions.
One of the most dangerous events in this type of construction is when the concrete is actually being poured. Suddenly, you have a huge amount of extra weight pushing down on the structure below.
If there's any weakness, there's a good chance this is when it will be exposed.
Investigators focused on how the structure had been held together.
One of the main reasons why this failure occurred is that the outer columns on the perimeter of the building were affixed to each other so poorly that they were not actually holding the building together laterally.
Here, the floor joists were a key connection between the columns supporting the outside of the building and the central core. But it turns out they were only loosely held in place.
The outer columns that are holding the periphery, where the facade would go, where the windows would go, were not properly fixed at the top and the bottom.
In places, the girders were held with only one screw, some with none at all.
When securing steel together, 2 screws will hold everything firm, but use just one and it can work as a hinge, making rotation more likely, which is bad news for stability.
So the slab itself is not actually connecting those outer columns to the core of the building, which, if you can think of the core very much like a spine of a building, it's sort of the backbone of the building. So you just have these lanky columns on the outside, and if they're not being restrained in any way, it's very easy for me, I don't have to put a lot of force on this to actually topple these columns over.
The steel structure couldn't handle the load of the concrete being poured above. As the weight of the slab increased, everything above the second floor began to move sideways.
Further investigations revealed another problem that had added to the instability.
When you're pouring a new slab like this, you have to pump tons of concrete from ground level up to the floor you're building. But the exact technique used here seems to have caused problems for the structure.
Normally a boom truck is used, so you would actually bring a truck in with a pump that has a large crane arm, essentially an articulated arm, that would pour the concrete straight onto the floor. Instead here, they actually tied that concrete hose to the side of the building, which sounds like it's not a big deal, but if you think about it, concrete is essentially liquid stone. So if you're tying a hose of considerable size to the side of a building, then you're actually putting an incredible amount of weight. You're putting vibrations and you're putting lateral force, sideways force onto a building where it is not designed to carry it.
The loosely connected structure was already being shaken by the hose, but one more factor was at play.
The straw that broke the camel's back was the fact that during the pouring of the concrete, the contractor chose to actually pour the 4th floor before they poured the 3rd floor. So you can imagine that this system is very unstable at this point. And once the concrete sets, it actually connects those outer columns with the core. But if you start top down, then that very unstable network just essentially is pushed to failure.
A combination of loose structural connections and an off-balance concrete pour brought this construction project crashing down.
Today, the plot remains vacant, serving as a warning to developers and engineers alike.
One lesson here is that no matter how routine or normal something might seem, any mistake can have devastating consequences.
Everyone wants their project completed on budget and on schedule, but in the end, we should always remind ourselves of the awesome responsibility as civil engineers and as builders that what we build is critical to life and safety of humanity.
Although the tragic event will be remembered in Brighton Beach, the community is once again looking to the future.
I'd like to see small houses come back in backyards and bring back the families into Brighton Beach. I mean, that's the future, the children.
When building big, engineers must always consider what lies beneath. Any weakness could trigger a catastrophe. Like this disaster in Italy.
People thought a bomb had gone off.
An engineering fail that almost swallowed a hospital.
Infatti si vede dalle immagini questi pilastri singoli che come dei funghi che escono dal terreno.
This was larger than an Olympic swimming pool and about 10 times deeper.
Just what had caused this massive chasm to open up? Naples, Italy's third largest city with around 3 million residents, is famed for its history, culture and natural beauty. Marco Caiano is a local journalist.
Napoli è una città speciale per tantissimi motivi, non solo per un qualcosa tipo il mare, il castello, il Vesuvio che abbiamo alle nostre spalle. Napoli è una città particolare perché è viva, perché ti riempie di amore, ti riempie di gioia, riesce a darti felicità con i suoi vicoli, con la sua pizza, con la sua gente.
Founded more than 2,000 years ago, Naples has always lived with the threat of disaster from its neighbour, Mount Vesuvius.
Vesuvius is famous for burying Pompeii almost 2,000 years ago. It's considered one of the most dangerous volcanoes on the planet, with 3 million people living close by. It last erupted in 1944 during the Second World War and is still active today.
Vivere all'ombra del Vesuvio per qualcuno è un'emozione continua, tendenzialmente per i giovani quello è un monte. Per chi invece ha vissuto l'ultima eruzione o per chi l'ha sentita raccontare dai propri nonni è comunque un essere vivente che nel giorno in cui si arrabbierà con la popolazione metterà a rischio tantissime persone.
Building a city on this volcanic landscape has always been a challenge. Geologist Gaetano Sammartino knows what lies beneath.
Allora, innanzitutto c'è da dire che il territorio della città di Napoli è un territorio dal punto di vista geologico molto complesso. Questa complessità deriva da che cosa? Dalla presenza di due centri eruttivi differenziati, che sono i Campi Flegrei, che stanno sul lato, diciamo, posto ad ovest della città di Napoli, e il Vesuvio sul lato posto ad est.
Hemmed in by so much volcanic landscape, Naples really is on dangerous ground, but humans have added to the complications. The Greeks and the Romans dug networks of underground tunnels and cavities, and over the centuries, the city has continued to grow above them.
È una città bucata nel sottosuolo, come se fosse una grande groviera, e questa è anche un'attrattiva turistica incredibile. Infatti si fanno delle passeggiate enormi nel sottosuolo da una parte all'altra.
The fact that Naples has thrived for so long in this landscape isn't just a testament to engineers, it's a miracle.
Early morning on Friday, January the 8th, 2021, an emergency was reported at the city's Hospital of the Sea. Marco Caiano covered the story.
Era una giornata di gennaio mediamente fredda, buia. Alle 6:30 si è sentito un boato enorme e del fumo bianco si è sollevato da quel buco.
Marco approached the scene with caution.
C'era acqua ovunque perché i pompieri continuavano a lanciare dell'acqua nel fosso. C'era un odore acre, c'era tanto rumore di antifurti, rumore delle autobotti dei pompieri.
A giant chasm had opened up in the car park.
Un'emergenza può colpire chiunque e finire 20 metri sottoterra, coperto da alto terreno, magari in auto.
This was one massive crater. We're talking 2,000 square meters of car park, just vanishing into the ground.
This was an absolute disaster. The collapse cut power to a nearby COVID recovery center, forcing it to close.
In the early morning hours, the gaping hole had swallowed 3 cars. The fire department combed the debris with search and rescue dogs. Thankfully, no one had fallen with the vehicles.
La voragine che si è aperta, qualsiasi altra ora del giorno, avrebbe fatto contare i morti, perché quello è un parcheggio che vede gente che entra e che esce in continuazione. In quel momento non c'era nessuno, c'erano solo 3 auto, quindi immaginare l'esplosione, il crollo fatto alle 12.
With With the hospital car park in ruins, Neapolitans wanted to know what had caused the collapse.
Dalle prime voci, quando chiaramente circolavano questi WhatsApp sui cellulari di tutti, si è pensato a un attentato, a una bomba, a una fuga di gas, perché il boato era stato fortissimo.
Witnesses reported hearing an explosion at the same time as the sinkhole opened up. But engineers quickly established that was the roar of the ground collapsing.
In this famously unstable landscape, was nature at fault?
Since the late 1800s, the Naples area has suffered around 200 sinkholes, swallowing everything from trees to vehicles and threatening to destroy some of the city's most historic churches.
Within the wreckage, there was clear evidence that this was no natural sinkhole, but the collapse of a man-made underground room. Vincenzo Nunziata is a structural engineer.
A una certa profondità rispetto al livello del parcheggio c'era questo solaio su cui gravava tutto il peso del terreno e del parcheggio stesso. Quindi il solaio con i suoi pilastri sosteneva questo carico.
Looking at the videos, you see the slab is smashed at the bottom of the sinkhole, but rows of columns are still standing upright in the debris. And for engineers, that suggests a type of failure known as punching shear.
Si vede dalle immagini questi pilastri singoli che come dei funghi che escono dal terreno. Sopra questi pilastri c'era il solaio. Su questo solaio c'era un carico che era il carico del terreno più la massicciata del parcheggio. E probabilmente si è verificato o che il carico era troppo elevato o qualche altra problematica che ha comportato appunto la rottura in appunti singolari.
Punching shear is a danger to all slab and column structures. If the slab is overloaded or the connections are overstressed, the columns literally punch through the slab and everything above it collapses.
That explained how the slab had failed. The next question was why. Although investigations continue, one theory is that excess rainfall had shifted the ground above the slab.
Quando piove in maniera molto copiosa, chiaramente quest'acqua, essendo favorita dalla mancanza del terreno di avere la capacità di infiltrarsi, quest'acqua defluisce in maniera molto veloce e si concentra in aree molto ben definite. Quindi la concentrazione di questi volumi idrici può creare delle erosioni localizzate che possono favorire, diciamo, l'innesco di queste voragini.
And as the weight shifted above, the slab collapsed.
Whether triggered by weakness or excess rainfall, the point is that there were massive unanticipated forces working on the connections with the columns, and the slab failed.
After the collapse, the sinkhole was cordoned off for further investigation, and engineers declared the Hospital of the Sea safe. But the events of that day serve as a reminder that Naples will always be living with extreme forces of nature.
Napoli è una città dove l'uomo l'ha fatta da padrona sulla natura, creando non pochi problemi proprio quando la natura poi si ricorda che deve fare la natura, quindi quando ci sono delle forti piogge, quando ci sono degli acquazzoni, quando ci sono le grandinate, quando c'è il forte vento.
Like any disaster, this was a reminder of the huge challenges engineers face every day as they strive to keep our modern world turning.
When big engineering fails, the cracks can be obvious for all to see. But sometimes the threat can lie hidden from sight for years. Like this story in the UK, a vital flyover that was close to collapse.
This is one of London's busiest roads.
The traffic just came to a standstill.
Near disaster on the eve of the London Olympics.
There was all sorts of people working 24 hours a day, floodlights, the lot.
This hidden fail had potentially deadly consequences.
Concrete cracking and cables snapping. This was really a close call.
London, England's ancient capital, grew from a Roman settlement into one of the busiest cities on the planet, complete with one of the biggest urban headaches, traffic.
London is famous for its traffic. It's one of the most congested cities on Earth, and one of the worst offenders is the A4, the major artery running west from the city centre.
In the 1950s, the London suburb of Hammersmith was a major bottleneck, and the A4 was in desperate need of more capacity.
This part of London was already fully developed and squeezed on one side by the Thames, so there was no room to build a wider road here. Instead, they went up.
In 1959, to carry traffic over Hammersmith, work began on a more than 600-metre-long elevated roadway. Richard Farthing lives nearby.
It was built to relieve all the traffic. Because this is such a major interchange going north, south, east and west, it all had to go around the Broadway. And now the east-west traffic all goes over the top here.
Ever since, the 16-span viaduct has been known as the Hammersmith flyover.
It's vital because there is no other real way by road to get into London.
When it came to construction in this densely packed urban landscape, engineers had to get creative and precast the viaduct in small segments outside of town.
Because of the space constraints, the segments were cast miles away before being shipped to the construction site and lifted into place. A bit like flat pack furniture. But if something went wrong with this structure, people's lives would be on the line.
The viaduct was built from 202 segments, alternating between full-width beams and smaller boxes, working like a skeletal spine of hollow concrete. Then everything was held together by long steel cables, each nearly 3 centimetres in diameter.
The key to this structure was the tension from those steel cables. It held all the individual precast sections together so they could effectively work as one long bridge.
The flyover took just under 2 years to build and opened in November 1961. Ever since, it has been a key link between the city, its suburbs, and the rest of the UK.
When it was built, it was pretty divisive. It goes right through the middle of Hammersmith, but now, of course, it's been here 60 years. It's just part of the furniture.
The viaduct might not be as striking as some of London's other bridges, but when built, the structure really was pioneering. And ever since, it's played a vital part in the capital's road network.
Yet in 2009, routine inspections revealed that all was not well with the viaduct. Structural engineer Mehrdad Mehrabani knows the case.
An engineer went to the site inspection and they realized that there are some problems. So they started intensive monitoring and then realized that the bridge is really going to the state of collapse.
The problem stemmed from a protective coating on the tensioning steel cables inside.
Engineers knew that leaving the steel cables exposed inside the decks risked corrosion from atmospheric humidity, so they were encased in a concrete grout. The theory was that they'd be safely sealed away for life.
But in reality, the concrete was cracking and allowing water to corrode the steel cables. But in this pioneering structure, it was almost impossible to see how bad the problem was.
Breaking open the concrete would potentially make things worse, so first they used acoustic monitoring to listen out for cables snapping.
So in 2010, when they started intrusive monitoring on that, they realized that the speed of the wire losing per day was 1 wire per day, which is very fast.
In just over 3 years, they heard more than 1,000 breakages.
The good news was that the acoustic sensors could pinpoint the exact location of the snapping. The bad news was what they found when they got there.
Now that they knew where to look, engineers physically inspected the cables, and what they discovered was worrying. They found voids in the protective concrete grout and corrosion in the cables themselves.
Any corrosion would compromise the cable's strength.
They realized that these tendons doesn't work anymore, so it is just breaking and failing during the stress and tension. This is going to be some safety issues here.
The structure's integrity was totally dependent on the steel cables maintaining tension. Any reduction could be catastrophic.
Engineers knew the viaduct was severely weakened. And worse still, London was about to be in the world's spotlight, with lives depending on this major roadway. The 2012 London Olympics would bring a massive increase in traffic, as athletes, officials and sports fans crisscrossed the city. So in December 2011, the decision was taken to close the flyover and figure out a solution.
The flyover closing was pretty dramatic because it was done with very, very short notice. We didn't know that there were problems with it, and then suddenly the Olympics were coming along and it got closed in a matter of weeks almost.
The bridge and potentially the Olympics were hanging in the balance.
There is an Olympic requirement to get to a venue in, I think, 45 minutes, and there was no way that they were going to get to the events without this flyover.
The cracked concrete explained the cause of the corrosion, but not why it was so advanced.
The level of deterioration was well above what had been allowed for in the designs. Something must have caused the steel cables to corrode rapidly. The question was, what?
One suspect was a built-in heating system designed to keep the bridge deck ice-free in winter. Keith Whitehouse is a local historian.
The flyover was built with underfloor heating, but the first year it was open, 1962 to 63, the council had a whacking £100,000 bill for the electricity.
With energy costs skyrocketing, authorities abandoned the built-in heating system for more traditional methods like de-icing salts.
Back in the 60s, the plan was for the internal heating to keep the viaduct clear of ice. But when the de-icing salts started to be used instead, not only was water getting in through the cracks, it was now salty, which is a corrosive cocktail for steel.
When it rained, the salt was washed into the, into the structure of the bridge, causing serious corrosion.
The fact the bridge was leaking was compounded by poor drainage, and the steel had been under attack for years.
It's so lucky the engineers realized how serious the problem was before anything failed. But now, the challenge was how to fix it.
With the Olympic Games just around the corner, a solution was needed and fast. But this pioneering viaduct had always been held together from within.
It wasn't possible to replace the cables inside the structure. So instead, they bolted on a kind of exoskeleton of new cables to keep everything properly tensioned in place.
So they used additional tendons outside of the bridge, but because that post-tension cable needed to be completely merged with the existing concrete, that they needed a new technology. So that new technology calls it ultra-high performance fiber reinforced concrete.
Not only is the new fiber reinforced concrete highly crack resistant, by being strapped to the outside, it's also easy to keep an eye on.
Any problem, you can monitor it in real time, and then if there is any problem, you can fix it before it is going to be too critical.
The solution wasn't just ingenious, it also extended the lifespan of the 5-decade-old structure by another 50 years.
Phase 1 of the repair was completed in time to reopen for the London Olympics.
There was all sorts of people working 24 hours a day, floodlights, the lot. It just had to be done.
By August 2015, the project was fully complete and the A4 was flowing smoothly again.
Most of us take bridges for granted. They're just there to do a job. But this is a reminder that in reality, the structure is battling huge forces 24/7, and nothing can be left to chance.
In New York, a construction crane comes crashing down onto a landmark bridge.
There was enough dynamic energy released that the entire crane essentially fell on its back.
Tragedy strikes a Titanic TV tower in Texas.
Oh my God! That scared me to death, because we can't outrun 2,000 feet of tower.
Catastrophe takes out Boston's water supply.
The power of water is immense, and you can see why it was a huge disaster at the time.
And in Sweden, Bruce Springsteen fans nearly bring the house down.
You can see the roof bouncing. It was crazy.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Big engineering requires colossal machines to get the job done. But if things go wrong, the catastrophe, like the equipment, can be massive. Like this disaster in New York State, on a vital Hudson River crossing.
This humongous crane going across two bridges, it's a frightening experience.
A catastrophic collapse that caught everyone by surprise.
I was in shock. I was not expecting this to happen.
A very lucky escape for both workers and drivers.
A collapse of this nature over an active roadway, this is 1 in a million.
New York City, with over 8 million residents, is the most populated city in the US. The 5 boroughs sit at the mouth of the mighty Hudson River, one of the largest natural harbors on Earth. Adrian Brugger is a professor of civil engineering.
We are a few miles up from New York City on the Hudson River. It has been a powerhouse of transport since the colonial times. This river is really the river that made New York City what it is today.
With so much water to navigate around, bridges are a fact of life.
New York City is carved up by water, and Manhattan alone has 21 crossings, some of them the most famous in the country.
But crossing the Hudson is no easy feat.
What makes this river really unique is that it transects the entire state. This river is actually incredibly wide. It presents a significant challenge when it comes to building bridges.
Since the 1950s, anyone heading over the Hudson north of New York City crossed over this, the near 5-kilometer-long Tappan Bridge. But after 5 decades, it was struggling.
The original Tappan Bridge was built in 1955, when traffic was much lighter. By the turn of the century, around 140,000 vehicles were crossing it every day, and it simply couldn't cope.
The need for a new bridge was recognized for decades. And the main goal was not just to replace an aging structure, but also to increase the capacity.
Opening to traffic in 2018, the epic new Tappan Bridge cost nearly $4 billion. Its twin spans now carry around 50 million vehicles a year.
If you look at the structure, you'll see that it's not really one bridge, it's actually 2 bridges. They're almost identical, but we have 2 spans, one for the eastbound and one for westbound traffic, that are essentially what we call statically independent.
Each bridge has 43 piers, 41 of which are anchored to the bottom of the very wide and very deep river.
The only way to create solid foundations for the huge bridge to carry immense loads was to drive hundreds of steel piles deep into the bedrock.
Driving piles through more than 30 meters of mud and clay, all the way to firm foundations, called for a massive crawler crane with an enormous hammer.
You had this absolutely enormous crane and this vibratory hammer, which is this big block of steel that shakes the entire thing vigorously. They actually use this and the self-weight of that whole system to just push the pile into the mud.
The hammer keeps a tight grip on the pile with what's known as jaw plates. As it vibrates, the whole system works with gravity to drive the pile downwards.
These cranes are serious pieces of hardware. The boom on this thing is almost as tall as the Statue of Liberty, and they're capable of lifting around 300 tons.
Freelance photographer David Rocco wanted to immortalize this mighty construction on film.
It was just fascinating to have this right in your own backyard. I was just out there watching the project day by day, waiting for those moments to get the right shots.
But the most incredible images that David captured would be memorable for all the wrong reasons. Tuesday, July the 19th, 2016, the crawler crane was positioned on the newly constructed westbound span, driving piles for one of the eastbound piers.
The pier would stand on 14 steel piles, 3 feet in diameter, driven deep down into the bedrock.
3 piles had already been successfully placed. Diana Cortez from the Occupational Safety and Health Administration knows the story.
They were in the process of driving the next pile with the vibratory hammer.
During the 4th pile, as they were driving it, it went off plumb. So essentially, it was driving crooked.
The crane operator attempted to lift the pile,
but he was having trouble getting it all the way out of the mud.
Right around noon, disaster struck. With traffic moving in both directions, the massive metal boom crashed down onto the old crossing. David Rocco got word that something was very wrong.
I got a beep from somebody on my cell phone that said crane collapsed on the Tappan Bridge, and I said, oh, wow.
David chartered a helicopter and began capturing the catastrophe on camera.
We shot straight across in the helicopter, got there in less than 10 minutes, and I was going to be on top of it, literally, 1,500 feet above it.
From his bird's eye view, the scale of the devastation was clear.
It's just remarkable to look down there and this humongous crane going across 2 bridges and hanging over the other side. That's a sight I'm never going to forget.
Tons of steel were lying across the bridge with traffic at a complete standstill. OSHA official Diana Cortez was in her office when news of the disaster broke.
when I first heard about the crane collapse, I was in shock. I was like, oh my God. Looking at the boom actually across the road and the traffic jam, the people out of their cars, it was quite a scene. It was actually horrific, to say the least.
Despite the devastation, this disaster had narrowly avoided turning into tragedy.
The boom fell totally across the Tappan Bridge. It didn't hit not one vehicle. So it was a miracle.
A collapse of this nature over an active roadway with no major injuries and no fatalities, this is sort of a 1 in a million. This is actually quite amazing that nobody was hurt.
Even the crane operator, though he probably got the shock of his life, escaped unharmed.
In the immediate aftermath of the disaster, the big question was what had caused this gigantic crane to collapse. Diana Cortez led OSHA's investigation.
As the area director, I immediately sent a team to initiate an investigation, also eventually to make some recommendations to prevent recurrence.
Attention quickly turned to the vibratory hammer, which had successfully driven 3 piles on this pier. But with the 4th pile, things didn't go as planned. After 3 minutes of driving, the pile became stuck at an angle.
Now, what happened at that point, in an effort to try to free the pile, instead of just winching up, he actually pushed the boom of the crane up, and the vibratory hammer that was holding onto the pile with essentially a set of jaws ripped free. And this is where things went horribly bad.
This caused the boom to recoil in the upward position, and then when it came down, it caused the boom to structurally fail because of the sudden jolt and collapse and fall right onto the Tappan Bridge.
Investigators needed to determine whether force or failure had caused the hammer to rip loose, so the evidence was salvaged from the riverbed.
After it was pulled back out of the Hudson, they found that the jaws, which looked very much like jaws of, an animal that grabbed the pile, the bearing plate on those, essentially the teeth, was actually a flat bearing plate. This is partially why this jaw ripped loose.
With the teeth corroded closed, the flat back of the bearing plate had been gripping the pile.
The bearing plates secure the vibratory hammer. One of the bearing plates was missing some of its jagged teeth. And also what was found was that the bearing plate was corroded.
Ultimately, the lack of teeth combined with corrosion meant the jaws lost their grip, triggering this catastrophe on one of the state's key bridges. After the disaster, the wreckage was cleared, and just 6 hours later, this vital crossing was partly reopened. Aside from a few buckled railings, neither bridge suffered any real damage.
Of course, this is an enormous crane that collapsed onto this bridge, and the impact was significant and terrifying, but in the end, this is major civil infrastructure that is built for the ages and that is built to absorb gargantuan forces. So even with this crane collapsing on a brand new bridge, the bridge suffered essentially no damage.
The disaster only set the project back a few days, and on September 11, 2018, both spans of the new crossing were fully opened.
This is a lesson on every project. Every piece of equipment needs to be in perfect working order. While it might cost time, ultimately it can prevent catastrophe.
In big engineering, every project brings unique challenges. But even a small change in plan can lead to catastrophe. Like this disaster in Texas, a devastating collapse of a supersized structure.
A TV tower taller than the Empire State Building came crashing down to Earth.
Miscalculations that led to destruction on an epic scale.
People said, okay, we got problems here. It's that last piece that got them.
It took 30 to 40 seconds for the entire tower to fall, which seemed like a lifetime.
The obvious question, what had gone so badly wrong? Houston, Texas has long been one of America's fastest growing cities. In the 70s, oil was driving the boom, and downtown the skyline was soaring too.
Back then, America's favorite pastime was watching TV, and it still is today. But all those huge buildings popping up in downtown Houston were causing havoc on TV and radio signals.
The only solution in true Texas style was to build bigger transmission towers. This site southwest of Houston houses some of the tallest structures in the US, like the Senior Road Tower, standing at a jaw-dropping 600 meters. Former broadcast engineer Bill Cordell oversaw the tower's construction.
Building a structure of this height, 2,000 feet or in that area, comes with real unique challenges in the fact that you have to have special rigging, you have to have special people that know their business. Otherwise, you can get yourself in trouble because those are big boy towers.
Most TV towers are constructed using a tried and true method, the cable and pulley system. hoisting each section before rotating it into place at the top of the tower. Despite reaching higher than nearly every skyscraper on Earth, the tower stands on a base just 45 centimeters wide.
This is the Senior Road Tower base itself. Can you imagine having 982 tons on 18 inches? The amount of compression at this point, you know, as an engineer is staggering. It's staggering. But here it is.
Keeping the tower standing tall demands serious support. Lee Lowry is a senior professor of civil engineering.
After they get a certain height, they can't just stand on their own feet. You have to have some guy wires, some wires holding them in position to the ground.
More than 20 steel guy wires defy the forces of gravity and strong winds to keep the tower standing vertical.
The top guy weighs 10 tons apiece. So you have 3 guy wires that weigh 10 tons that are pulling on the tower just from the sheer weight, and then you tension them. Well, you have to do it very carefully or you'll pull the tower down. In a tower of this magnitude, you have to be very careful.
These towers are extremely vast and highly tensioned pieces of engineering. But they're just the support act. It's all about getting the antenna as high as possible for maximum signal range.
The antenna is like the crown jewel. It has to be built and handled with special care. It's a very pristine thing, a very slow process to get the antenna in place and then test it afterwards.
And crucial to transmitting as far and wide as possible are these, known as microwave baskets.
Those baskets are part of the antenna, and they stick out from the tower pretty far, 2 or 3 feet, that point out towards the horizon.
Microwave baskets send out those all-important signals between the transmitter and the receiver, in this case, the tower and your home.
Completed in December 1983, it began broadcasting 9 radio and 3 TV stations to homes across the city. But this is the second tower on this site. Its predecessor met a tragic end. December the 7th, 1982, the final 18-meter tall antenna section for the original tower was being hoisted into place. Broadcast engineer Bill Cordell asked a colleague to record this crowning achievement.
I had Andy, a good friend of mine, an engineer that I've known for many, many years. He was very good at filming. Well, I had him in the back of my truck looking straight up.
5 workers were on the tower to secure the final piece.
It was supposed to be the cherry on top of the cake, so to speak, because once they put the antenna in place and bolted it in, we were practically done.
Instead, with the antenna more than 300 meters up in the air, what Andy captured was the stuff of nightmares.
Oh my God!
Andy never says anything bad. I heard him that day say, "Oh my God." That scared me to death. And you feel very helpless. They were young men that were 1,700 feet in the air, and you knew what was going to happen then.
The falling antenna severed one of the guy wires holding the rest of the tower in place.
The antenna hit the guy wire over here and was sliding down the guy wire. As it slid down the guy wire, it sheared it, and then that's what collapsed the rest of the tower.
As the entire structure came crashing down, workers on the ground scrambled for safety. Bill was just 100 meters away.
My secretary, who was very religious, says to me, "Run." I said, if the good Lord wants us, he's going to take us because we can't outrun 2,000 feet of tower.
3 workers were injured in the disaster, but tragically, the 5 men on the tower all lost their lives.
It took, 30 to 40 seconds for the entire tower to fall, which seemed like a lifetime.
What had caused this supersized structure to come crashing down to Earth? It seems there was a problem with the lifting plan, which had worked for the main tower sections, But with the antenna, there were complications.
The final piece of antenna had those all-important microwave baskets already attached to the sides.
As the antenna was hoisted upright, there was a risk the lifting cables would damage the sensitive microwave baskets. Lee Lowry was on the team that investigated the collapse.
The people said, okay, we got problems here. This great big basket that shoots out all the signals, and the wire to raise the whole piece with it, it's going to hit them.
The baskets were too sensitive to remove. Instead, the team custom built an attachment to keep the antenna safely at an angle.
The antenna were bolted with what they call U-bolts because they look like the letter U. The cable goes up in the air, and first thing you know, the whole thing starts raising up like this. The extension of this piece of steel far enough down the road so that where you attach the lifting cable will, when it goes up in the air towards the top of the tower, the cable itself doesn't touch the microwave baskets. And it never did.
Hoisting the antenna at an angle prevented the cables from tangling with the microwave baskets. But after examining the wreckage, Lee found evidence that the fix had overloaded the U-bolts.
That's the way I found it. That's where it was. This is a U-bolt. Used to be a U-bolt until it got straightened out by being pulled out of the hole.
Lee and the team calculated that the load on the U-bolts had been underestimated by a factor of 7.
The force that broke the bolt in the first place just pulled the bolt back out of the opposing hole and straightened the U-bolt out pretty much straight. That is the failure. That's the only failure. It's that last piece that got them.
As the antenna was lifted closer and closer to the top, the U-bolts were struggling to cope with the strain and failed. There was nothing anyone could do.
Following the catastrophic collapse, the tower was rebuilt piece by piece. Bill Cordell served as project manager on the new construction.
The second tower, the lifting process was changed quite a bit. It was extremely well thought out and blessed by professional engineers before anything was done. And of course, none of the rigging or U-bolts that they'd used before was even considered.
A year after the disaster, the new 600-meter tall tower was finally complete. While the team still pays tribute to the young men who sadly lost their lives.
The gentleman that filmed it that day, Andy and I talk each year, and we remember and have a great deal of remiss for the young men that lost their lives here.
With massive infrastructure, even the smallest component is crucial. One tiny fail can cause a huge catastrophe. Like this story in Massachusetts that wiped out a vital water network.
This catastrophe triggered a state of emergency for 2 million people.
People were unable to cook, to drink, to bathe.
An underground mystery that had engineers guessing.
Everyone scratched their heads. That's a new pipe. How could that happen?
Boston, Massachusetts is one of the oldest cities in New England and owes its long existence to the Charles River. Bob Zimmerman is former director of the Charles River Watershed Association.
Water is the single most important substance on Earth for life. All of us are dependent on it. Without it, in 2 to 3 days, most of us die.
Like many big cities, Boston relies on large-scale clean water storage reservoirs located outside of the city limits. Fred Tice is a local journalist.
The metropolitan area of Boston requires a lot of water to keep it going. And in the 1930s, a major reservoir was built called the Quabbin Reservoir. And then another big reservoir, the Wachusett Reservoir.
These two reservoirs combined hold enough water to supply Boston with fresh water for 5 years. But to reach the city, there's a more than 50-kilometer journey from reservoir to tap.
A lot of us take clean running water for granted, but keeping it flowing takes a huge amount of engineering. We just don't see it because it's mostly hidden underground.
In 1996, to stay on top of demand, the Massachusetts Water Resources Authority started work on a brand new pipeline.
The Metro West Water Supply Tunnel is the main tunnel that brings the water from the Quabbin and the Wachusett reservoirs to the Boston metropolitan area.
These pipes are a massive 10 feet in diameter. 250 million gallons of clean water a day can flow through them to 31 towns and cities, including Boston.
These big tunnels supply water to millions of people, and should one of them be cut off, all of a sudden you have a big part of the Boston metropolitan area that finds itself without water.
Hidden from view, the underground aqueduct was a great success. But in 2010, disaster struck. 10 a.m., May the 1st. Fred Lasky, executive director of the state's Water Resources Authority, received a call.
My chief operating officer is unflappable. And when he called, there was a sense of urgency. And then when he explained to me where it was, I said, oh no, oh no.
The Metro West Tunnel had burst open in Weston, more than 20 kilometers from downtown Boston.
When I got here, it was gushing. It looked like the telephone pole nearby was going to go. The whole thing was just eroding, churning up all the dirt, all the dirt, all the dirt.
Boston's clean water supply was surging up from underground.
There were 8 million gallons an hour flowing from this site into the river.
The power of water is immense. And you think about a 120-inch barrel of pipe with water coming towards the city under great pressure, and you can see why it was a huge disaster at the time.
Everybody starts to immediately think, well, it can't be that big a deal, right? It's just a pipe. But it is a big deal. 8 million gallons an hour is, get your attention, amount of water, a real issue.
Not only was clean water pouring out, dirty earth was being sucked into the pipes, potentially contaminating everything heading for Boston.
This was an even bigger problem when we found out that people were unable to cook, to drink, to bathe.
About 2 million residents who had to begin to boil their water for drinking water and get as much bottled water as possible.
The following day, the leak was stopped, but Bostonians were still without clean water.
It's front page in the Boston Globe. It's on the news every single night. Every family east of here who has to boil water or go out and buy bottled water knows about it and is concerned about it.
This was national news. President Obama even signed an emergency disaster declaration.
More than 1 billion liters of water had escaped. The race was on to get to the root of the problem.
Everyone scratched their heads. What happened? How could that be? That's a new pipe. How could that happen?
Well, a 10-year-old aqueduct is brand new. And for it to blow out, something seriously bad happened.
As the debris was cleared, it revealed a small but crucial piece of evidence.
The amazing thing is after all the earth had been moved, there was a pond of water. When we pumped that out and the top of the pipe started to surface, we realized that all that water was coming out in a gap between the pipes all the way around of about 1 inch. And it was just an incredible lesson in the power of water.
The source of the leak was clear, the joint between two sections of pipe. But the question was, why had the connection failed? Dr. Zorica Pantic chaired the investigation.
As a panel, we looked actually at the possible scenarios that caused this failure. The one would be the vertical shear, so the pipes moved in the
vertical direction. When we looked at the site, we realized that the pipes are still aligned. So that means that the vertical shear was not a possible scenario. So then we focused actually on the coupling and looked what happened with the coupling.
The two pipes were clamped in place with a two-part steel coupling collar, held together with 8 steel studs more than 2 centimeters wide, secured by 16 nuts. As investigators dug deeper, it was clear the collar was buckled completely out of shape.
This huge 1-ton piece of steel clamped 2 sections of pipe together with a vice-like grip. But it had failed catastrophically. The question was why?
Further inspection revealed that 7 of the 8 studs holding the collar together had broken.
So basically, out of 8 studs that were supposed to be there, only 3 were found, and only 1 was still connected to the coupling.
Examining the studs revealed a flaw.
What we found out is that there were cracks in these studs, both in the valleys and on the hills and the tops of this.
Dr. Pantich's team concluded that the cracking had happened during manufacturing. Once installed underground, the studs were vulnerable to corrosion.
When they were installed, they worked for a while until the environment caught up with them. That caused corrosion along these cracks in the studs. And once those expanded, the studs starting to fail and break.
Ultimately, the faulty studs were simply too weak to do their job.
Huge amounts of water were being pumped through these pipes at high pressure. Without a rock-solid connection, the coupling was doomed to fail.
Millions of residents were without mains water, so engineers worked around the clock to repair and flush clean the Metro West pipeline.
We had one group of people working on addressing the leak and fixing it. We had another whole group of smart people who were dealing with the hydraulics and the water quality issues and how do we get it turned back on to make sure it was safe. Because that would have been a real disaster if there was contaminated water.
On May the 4th, just 3 days after the joint failed, the repaired pipeline was back in action.
When clean water was finally restored, it was a huge relief for residents and a reminder of how dependent we all are on the infrastructure hidden beneath our streets.
To avoid a repeat disaster, a parallel pipeline known as the Holtman Aqueduct was upgraded, ensuring there was always a route for clean water to reach Boston.
We are now in a vault chamber that connects the Holtman Aqueduct to the Metro West Tunnel. And this was constructed after the water main break to create the redundancy that we need to safely operate the system in a major event.
This time clamped solidly together by hundreds of studs.
And you can see the massive size and the strength in these couplings.
The events of May 2010 serve as a reminder of the massive task engineers face keeping our vital infrastructure operational.
It was a big wake-up call because we all face issues associated with infrastructure, much of which is getting pretty old at this point. And as it fails, people are impacted. Nature is impacted.
2 lessons to learn from this, right? One is we take water for granted. We just never think about it. We turn on the tap and there it is, and we use as much of it as we want. The other is how critical, just one little point of failure can be.
When engineering goes wrong, the cause can be plain for all to see. But sometimes it's hidden out of sight. Like this story in Sweden, and a Springsteen concert that really rocked the house.
The whole arena started to fall apart.
Music fans almost brought this structure to its knees.
You can see the roof bouncing like a meter or something. It was very close to a big catastrophe.
But what could nearly take down an entire stadium? Gothenburg, Sweden's second largest city, is home to just over 500,000 people. But for a small city, it has a big music scene.
Say Swedish band, and chances are most of us think of ABBA, who burst out of Stockholm in the 70s. Although less well known, Gothenburg has long been home to a much cooler, edgier music scene.
Johan Lindqvist is a local music reporter.
It's been a music town for many, many years. The music here comes from the underground. We have a lot of metal, hip-hop, reggae music. We have great venues and a lot of vibrant music life.
This is Gothenburg's Nya Ullevi Stadium, named after the Norse god of games and sport. With a capacity of 75,000, the more than 200-metre-long oval is the largest outdoor arena in Scandinavia and has hosted some of the biggest names in music. Lotta Nebel is CEO of the company that runs the Ullevi.
So, this is where the magic happens. And through those doors, you've had rock stars like Madonna, you had Pink, Coldplay. You had loads of famous people walking in and making magic for thousands and thousands of people.
Before the music scene took Gothenburg by storm, the stadium was designed for the Soccer World Cup.
When Ullevi was built, it cost $4 million. The venue was ready to welcome the World Championships in soccer in 1958.
The field is towered over by two 52-metre-tall pylons holding floodlights and helping to support the roof below. The design was unique, but the structure, like many stadiums, was concrete and steel. Professor Göran Kjellfors is a geotechnical engineer.
Ullevi Stadium was designed and built in the 1950s. The main part of Ullevi is made of cast-in-place concrete, and the roof is made of steel beams and lightweight concrete sitting on top of the beams.
This part of Gothenburg sits on clay. It's a great flat surface for a soccer pitch, but the concrete structure of the stadium would need much stronger support.
The solution was a network of piles beneath the seating areas.
Here we see a cross-section of Ullevi with a main structure, cast-in-place concrete. We have the clay layer, we have the moraine, and we have the bedrock. And here are the concrete piles that go all the way down to bedrock, which carries all the loads from the arena.
In the 1980s, Ullevi began hosting concerts, and one of its first acts was Bruce Springsteen.
In '85, Bruce Springsteen was playing 2 nights at Ullevi, and it was his biggest tour up to date. I mean, it was bigger and more popular than ever, selling out big arenas all over the world. So, I mean, there was a kind of hysteria going on, of course.
Stefan Hammerströ was working in the arena at the time.
I was only 18, 19 years working here, so everybody has bought the album Born in the USA, so they knew the songs and they were ready for the concert.
It's like 65,000 people. At that point, that was the biggest crowd at Ullevi for any concert. And I guess there were mostly teenagers there. It was a lot of energy and a lot of jumping up and down.
During the concert, the energy was building up, so it was crazy. We who worked in a kiosk couldn't stand still. You automatically danced in the kiosk.
Towards the end, Bruce played the old classic Twist and Shout.
And people even got more crazy than before. And the whole arena moved like this, 10 centimeters or something. And then you looked up the roof, you can see the roof bouncing like a meter or something. And you saw it from here. So, yeah, it was rocking out the arena.
Thousands of people jumping to Twist and Shout. The whole arena started to fall apart.
For me, it was exciting, but maybe if you think about it after, maybe it was a little bit scary.
The shaking wasn't limited to the stadium. Apartment owners 400 meters away reported ornaments and books falling from their shelves. As the music faded, it became clear that this hadn't been a small shakedown.
After the concert, they had to look at the arena, and they discovered that there were damages done to the structure.
The stadium had previously survived the Rolling Stones, so what had the boss done to cause such trouble? The source of the problem wasn't in the stadium structure itself, but in the ancient ground beneath the soccer field.
Here in the inner field is a lot of clay, and this, when the audience started to jump here, that meant that the clay started to move like this.
Back in the 50s, the pitch, or infield, was built to have 2 football teams and the referee running around on it, not 20,000 plus excited fans jumping up and down.
All that jumping wasn't just pounding the floor. It was also rocking the stadium and its towers.
So the force from the audience goes into the clay. The clay expands like a pulse, and that affects the piles, so they bend out a little. Not very much, a couple of centimeters perhaps, but that will give deformation that then will be transmitted up to the structure and enlarged. So it's a rhythmic pulse coming up also into the structure.
We've all felt the pulses of heavy bass from loud music. Imagine that happening to the clay beneath the pitch over and over, pushing on the piles supporting the stadium and its towers.
The pulses weren't the only problem. The frequency of the jumping matched the clay's natural resonance.
Experts calculated the resonance of the clay was between 1.5 and 3 hertz, or cycles per second. The music and the jumping of the crowd was 2.4 hertz, right in the sweet spot for causing mayhem.
That is close to the resonance frequency of the clay, and then there is no damping, and that's why it's enlarged, and it's going to increase all the time as the pulse keeps going on.
Although fans didn't realize it at the time, the stands were dangerously close to collapse.
Now here we see the concrete structure, and between those constructions there are beams, concrete beams, and they are supported like this. And this is probably about 20 centimeters or so. And during the concert, these started to move up and down and also sideways. And in the inspection after the concert, they found out that the support was very limited and it was very close to a big catastrophe.
These days, everyone jokes about the crowd nearly bringing the stadium down. But the truth is, here, they came frighteningly close to actually doing it.
Ullevi Stadium closed its doors while engineers resolved its structural integrity. Although the building itself was fine, the field needed support to prevent it from bouncing.
Well, the stadium had to be reinforced using over 100 pillars, each having a diameter of 1.5 meters and a length between 20 and 60 meters, because you need to reach solid ground. And as a result, you can see it in the garage. You can actually see the pillars and the size of them.
The network of piles was driven down into the bedrock. Thomas Tayland is Ullevi's construction project manager.
Now we are under the pitch. Here you see it from below, the roof in the garage. And over here you can see every 15 meters you can see the piles. Every one of these piles, they had to stand on the rock. So it's a big job, a lot of concrete.
Once the piles were driven into the bedrock, they were like a network of giant stilts supporting the pitch above. Now, however hard fans jump, the clay below and the stadium won't be going anywhere.
3 decades after that dramatic night, Springsteen returned to the Ullevi.
Are you ready to test this stadium?
And proved the fix really had worked.
This time, the only thing rocking was the music.
In California, Catastrophe cuts one of America's most vital highways in two.
Once I got on scene, wow, a whole section of the bridge was missing.
In Texas, a mammoth refinery explodes with deadly consequences.
You could see the fireball from almost 20 miles away.
In the UK, scientists launch an interplanetary investigation.
We were just watching for that moment that said Beagle 2 was landed, and we waited, and it didn't come.
And in West Virginia, tragedy strikes a vast suspension bridge.
It yanked on the other guy tower, and then the whole bridge collapsed into the river.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. With everything they build, engineers must always consider Mother Nature. Underestimate her, and the consequences can be disastrous. Like this catastrophe in California that shut down a major freeway.
There was over 10,000 people just stranded here. I had never seen anything like that in my entire life.
A desert bridge with a potentially deadly weakness.
I could see a whole section of the bridge was missing, and I could see just the tail end of a pickup truck sticking up.
This is a major highway. It's just so lucky that no one was killed.
America. This vast country depends on a nearly 80,000-kilometer-long highway system. And key to keeping the southern half of the nation moving is Interstate 10.
At around 2,500 miles, I-10 is the fourth longest interstate in the US and connects LA on the Pacific coast with Phoenix, Houston, New Orleans, across to Jacksonville, Florida.
Former firefighter Alex Gregg lives near the I-10 in Southern California.
The I-10 corridor is very vital for travelers as well as for commerce. All goods pass through here on their way either to or from Los Angeles, from the harbors out, or to the harbors going other places. So it's an important link from Los Angeles to all points east.
From here, I-10 runs east, across the Sonoran Desert.
We're in the middle of the desert. This is not what people normally think of when they think of California, but we have a lot of this desert area down in Southern California between Los Angeles and Phoenix.
The road stretches endlessly across flat, dusty ground, but it's also riddled with gullies created by sudden rains.
We live in a very arid terrain. Doesn't look like we get much rain here, but surprisingly, in the summertime, we get what we call monsoon storms that create flash floods.
As I-10 grew, dozens of bridges were needed to cross the gullies, like these across the so-called Tex Wash. Bridge engineering expert Dr. Abul Hassan Astaneh-Asl explains the name.
It is a Tex Wash bridge. Tex Wash means this is a place that water created by washing a path. There is no river here. It's just a place that flood comes, very flash floods, very heavy flood suddenly, and washes this path.
With so many washes to cross, the state settled on a standard formula for bridges.
In California, they were using a lot of concrete to do these things, and they ended up having standard designs for small bridges. So they had this 20-meter long spans, and they would just try to use it many times.
Tex Wash was originally too wide for the standard span, but rather than design special longer bridges, it was simpler to fill in the sides of the wash, making it narrower so the shorter spans would work.
Completed in 1967, the Tex Wash bridges safely carried I-10 for almost 5 decades. But in 2015, a storm was brewing. July 19th, almost 18 centimeters of rain fell on the Chuckwalla Mountains to the south of I-10.
Because of the terrain the way it is, the water doesn't absorb quickly, so it runs downhill rather quickly and becomes a flash flood. It can become a very dangerous situation for people. And the flash flood will be here before you know it, and it's gone before you know it.
A firefighter at the time, Alex Gregg, was on call at nearby Desert Center.
I was on duty that day, and I was the covering battalion chief, so I got called out to a bridge collapse on Interstate 10, just west of Desert Center.
Traffic was already beginning to back up.
Once I got to just past Schoharie Summit, the traffic really came to a standstill, and everybody was stopped. Because the traffic was backed up so that far, I knew we had a serious situation on our hands.
Victor Garcia's family runs the only rest stop on this remote stretch of I-10.
I had never seen anything like that in my entire life. There was easily over 10,000 people just stranded here.
Alex and his team of firefighters made it through the chaos.
I could see a whole section of the bridge was missing, and I could see just the tail end of a pickup truck sticking up, knowing that there was a truck stuck down in there and people were trapped inside. I knew time was of the essence.
The race was on to rescue the driver of the pickup.
We got a rope system put together, and then I put my trained firefighters on it. He was pinned in the vehicle, so we had to use our extrication tools, also known as the jaws of life, to go down there and pry the truck open in order to get him out. Once we got him out, he was extremely relieved, especially once we got him back up on top, away from the fallen bridge.
With the bridge down, traffic was going nowhere.
It was still raining that night, so it was mass hysteria. We were getting overwhelmed. We ran out of everything. We ran out of food, ran out of gas, ran out of everything.
Authorities set up diversions, and by dawn, both the traffic and the rain were gone as quickly as they had come.
The next morning, it was dead. Nothing. The freeway was shut down. No one was passing through. You could hear, crickets.
After the storm passed, everyone wanted to know what had caused this catastrophic failure. Abul Hassan was called in to investigate exactly what went wrong. On the surface, it was simple.
What happened that day for Texwash Bridge was because of this unusual flood, which experts actually rated it as 1,000-year return flood.
Any structure would struggle in the face of a 1,000-year flood. But here, narrowing the gully so the standard bridge length would fit had made things worse.
When the wash was narrowed, the shape was altered too, so water had to change direction not once, but twice to flow under the bridge. First as it hit the roadway, then again to curve under the bridge.
You have to realize the pressure of water that's coming down. Try to tell water that when you get to this road, I-10, it's important, please turn right. That cannot be done in engineering. You tell the flood, when you get here, please turn left, because my bridge is there. Wow, I can't turn left because it's too small for me. Whole volume of water coming. The water, it gets a lot of turbulence and the velocity goes up.
The turbulent, fast-flowing water eroded the bridge foundations on the outside of the bend. It's what's known as scour, and that end of the bridge dropped into the wash.
And yet, it turned out, reshaping the wash wasn't the only mistake made here. As Professor Astane Assel discovered, the foundations were missing a crucial element: piles.
So if this is pile and foundation is on it, if the soil under the foundation is washed, the pile will still be there. But in this case, they didn't put the piles under the foundation. So the water came and washed the soil, my hand is foundation, and it just dropped.
And there was one final fail that channeled the water straight into the foundations: the so-called wing walls, which were at the wrong angle.
Wing walls in bridges are the walls that you put at the end of bridge and beginning of bridge. They're usually parallel to the path of water, so the water passes by them like a wall, so it doesn't hurt the foundation. In this case, the wing walls were here. What good it's gonna do, other than when the flood comes, hits the wing wall actually and washes the bridge. So these two fingers as a wing wall don't do any good for flood. They should be here, like this. So the flood goes through here.
By narrowing and redirecting the wash, engineers created the perfect storm for scour. Combined with weak foundations and misplaced wing walls, this bridge didn't stand a chance against the epic flood.
We're extremely fortunate that we didn't have more cars fall into that opening other than just the one, and everybody else was managed to stop. It could have been a whole lot worse.
With I-10 out of action, drivers were forced to take long detours. A new bridge was needed and fast.
Time of the essence of getting the freeway open, there was no way that we were going to reopen the freeway anytime soon because the bridge was totally destroyed and had to be completely rebuilt.
The $5 million rebuild took 2 months, but finally the bridge reopened, complete with heavily protected foundations, connecting California and Arizona once more.
This failure is a reminder of the challenges engineers face every day working against Mother Nature. If it wasn't for that 1,000-year flood, who knows how long that bridge might have lasted.
I came away with a better appreciation for the movement of water. Even in the desert, you just never know when Mother Nature might get you.
When it comes to big engineering, checking every detail is crucial, no matter how small. Because if just one thing goes wrong, the results can be catastrophic. Like this disaster in Texas that rocked an industry to its core.
The 911 lines were being swamped with anxious calls.
A refinery explosion that was felt more than 20 kilometers away.
A seismic event that registered 3.5 on the Richter scale.
Changes had to be made to keep this from ever happening again.
It has the power of 2.5 tons of dynamite.
Houston, Texas, a thriving metropolis thanks to one industry: oil. Massive industrial complexes run along the banks of the Houston Ship Channel, which flows into Galveston Bay and the Gulf of Mexico. Local journalist TJ Olds knows the area well.
So the Galveston Bay region is so important to the oil industry for all of America when it comes to the oil refining and chemical processing that happens here. It is massive.
The 10 major refineries in the region process more than 2.5 million barrels of crude oil per day. And it's turned into more than just gasoline.
So a lot of people consider oil as, oh, that's just fuel for our car. That's not true. It's a lot more than that, particularly is in every plastic product you have out there. So it's part of our lives. It's in your homes, it's in your cars, it's in your office, it's everywhere.
This 260-hectare complex has been at the heart of the industry for decades, producing one of the most widely used plastics today, polyethylene, found in everything from packaging to surfboards. Kenneth Block is a process safety supervisor.
In the late 80s, this particular plant that we're standing in front of provided approximately 1/3 of the global supply for high-density polyethylene.
When we think of plastic, we picture a clean, stable solid. But the raw ingredients started life in a seething mass of natural gas and crude oil.
Refineries take crude oil and begin by heating that crude oil up, separating it into different components. These processes contain a mixture of flammable substances that, if released into the atmosphere, can cause an explosion and fire.
The volatile components are processed inside 45-meter tall towers, where the liquids flow through vast oblong loops of pipe, known as loop reactors. Flammable ethylene gas is fed into the reactor and dissolved in a cocktail, including isobutane, hydrogen, and hexane, which are also highly flammable.
The mixture spins around the loop where it's massively compressed at 40 times atmospheric pressure, forcing the ethylene molecules to join together or polymerize into polyethylene.
The solid polyethylene particles pass out of the reactor into 6 vertical tubes called settling legs, before collecting in a flash tank below. Over time, the legs become blocked, requiring regular maintenance.
The material coming out of the reactor, polyethylene particles, fluff is what they call it, this would tend to accumulate inside the settling leg and form a large cylindrical plug, essentially choking off flow. So that plug would then have to be removed, or else it would interrupt production.
Like any production process, keeping things running smoothly is crucial. That's easier said than done when you're dealing with highly pressurized, explosive chemicals.
October the 22nd, 1989, 3 of the 6 settling legs on one of the loop reactors had become clogged. With the reactor still running, the 3 blocked legs were shut off using 20-centimeter ball valves located at the top.
The loop was still full of a swirling whirlwind of flammable chemicals, so properly sealing the legs for cleaning was absolutely crucial.
The first leg was successfully unplugged and reconnected. The following morning, while working on the second, disaster struck. A massive explosion rocked the plant.
You could see the fireball from almost 20 miles away. It has the power of 2.5 tons of dynamite.
The force of the blast was unprecedented.
I do remember my parents telling me that at the time of the explosion, they felt the earth move, and that was between 10 and 15 miles away from where we're standing here.
We had debris that was found several miles away from the center of the blast. So that just tells you how powerful this was.
The shockwave shook the community.
It created a seismic event that registered 3.5 on the Richter scale.
Fires raged for nearly 10 hours before emergency crews were able to bring them under control.
Where we're looking at right now, this area in the background was just a form of blackened, twisted metal.
Among the devastation and wreckage, over 300 people were injured. Sadly, 23 more lost their lives. With similar facilities around the country still in full operation, authorities immediately began looking for the cause of the explosion.
Investigators knew the blast happened when the settling legs were being cleaned, so the most likely cause was an unintentional release of flammable gas.
The accident involved the release of 85,000 pounds of a flammable hydrocarbon mixture at the bottom of the reactor, and this formed a vapor cloud, which then contacted an ignition source about 90 seconds later.
The big question was, why had the gas escaped from the reactor? Investigators found that the problem stemmed from inside one of the settling legs, with a 20-centimeter ball valve intended to control supply.
In normal operations, these ball valves are open and closed from the control room with compressed air, but the pneumatic system can be overridden using a manual lock on the valve.
Following protocol, before removing the legs for cleaning, the lock was activated.
The block valve was closed. The air actuator hoses that would be used to open and close the valve were removed, and then the valve was physically locked into position.
But there was a problem when the hoses were reattached.
The biggest mistake that happened here was hoses. Now, they had been taken off for safety precautions when the maintenance was being done. When they were reconnected backwards.
Connecting the air hoses incorrectly proved to be a fatal error.
There was nothing to stop these 2 hoses from being reconnected the wrong way round, and no way to know that anything was wrong before the system came back online.
Tests done after the investigation determined that this particular valve design could be worked in reverse, and that making the mistake of fastening the air supply line to the discharge actuator side would actually force the valve open instead of closed, even though the switch was in the closed position.
Although the reactor's control unit registered that the ball valve was securely closed, it was actually open.
A valve that was needed to be closed during maintenance was inadvertently open and released the entire contents of the reactor in a matter of seconds.
Vapor was released, highly volatile vapor. And that was the beginning of the problems, because as that comes out, it gets ignited, then you have a massive explosion.
While it was too late to stop this devastating tragedy, changes were made to prevent a disaster like this from ever happening again.
The events that occurred here on October 23, 1989, accelerated the development and implementation of process safety standards, things like designing couplings that will only connect one way.
So any facility you go in nowadays, you'll see the sign that says so many days since the last injury. That's because the standards are there. They're being followed in many ways. Safety is a priority.
Handling massive amounts of volatile chemicals will always be dangerous. But it's crucial that after an accident like this, new safety systems are put in place to reduce the risk in the future.
When epic engineering goes wrong, the problem can be clear as day. But sometimes we're left completely in the dark. Like this vanishing act that was out of this world.
The descent to Mars, the 7 minutes of terror, people's careers are on the line.
When the engineers hadn't first heard back from the lander, we just didn't know what had happened.
A true engineering enigma.
This sparked a decade-long interplanetary mystery.
What's out there? And are we alone? Questions that have long gripped the human race. Astronomers like Hannah Banyard from the UK's Royal Observatory are helping to find the answers.
Astronomy in general is really important, not only to the astronomers in the scientific community, but the wider public, because it helps us understand our own place, not only in the universe, but on Earth.
One planet more than any other has long been in the spotlight. Mars. Dan Kendall from the UK National Space Centre explains why.
Mars is a very barren planet, but we know enough about it and we've studied it enough to know that in the past there may have been water on Mars, it might have had a thicker atmosphere.
We know that it had lakes of liquid water, it had oceans of water, and water is one of the key signs of life. So when we're looking for life on another planet, Mars is really where we want to go to.
The problem is getting there.
Mars can be 400 million kilometers from Earth, but astronomers calculated that in 2003, the planets would be less than 60 million kilometers apart.
The European Space Agency realised that there was going to be this moment where Mars and Earth were closer together than they had been for more than 60,000 years. So they came up with the idea of the Mars Express mission.
Mars Express was designed to map the planet's surface from orbit. But British astronomers saw an opportunity to add an extra piece of hardware that could land on the Martian surface.
A team of academics got together and started thinking about whether maybe a British lander could be included on that mission as well, to take that chance to investigate the surface of Mars and look for the biosignatures of life.
That's how Beagle 2 was conceived.
HMS Beagle was what took Charles Darwin around the world in the 1830s and led to the origin of species. He learned so much about life on Earth, and the name Beagle 2 is all about the fact that this mission was intended to tell us so much more about life on another planet.
In the 70s, NASA sent 2 Viking landers to Mars. They found tantalising clues that there might once have been life there. Beagle 2 was far more advanced, and the team hoped that if there was life on Mars, Beagle 2 would sniff it out.
One major challenge was finding room for the Beagle within the existing Mars Express orbiter. It would have to be both small and lightweight.
Beagle 2 was about the size of a bicycle wheel and it looked like a barbecue, but it was loaded with scientific power.
In front of me we have a model of Beagle 2. When it landed, it would open up like a pocket watch, and then these solar panels would each in turn open up to make it larger. So they packed a huge amount into an incredibly small space.
Base camp for mission control was located here at the UK's National Space Centre. Chief Executive Chas Bishop explains.
The idea came about to put the Lander Operations Control Centre in front of the public. They were getting access that probably hadn't been granted before. So, you know, there was a little bit of a risk there that, you were seeing a space mission, warts and all.
On June the 2nd, 2003, Mars Express with Beagle 2 on board launched from the Baikonur Cosmodrome in Kazakhstan.
I can remember the launch very clearly because a launch really does make the hairs stand up on the back of your neck because it is risky and people's careers are on the line.
Liftoff was a success, but there was a long way to go.
The journey to Mars is 7 months. The calculations involved in just reaching orbit are staggering, let alone getting the lander through the atmosphere to a safe touchdown.
Just before Christmas 2003, Mars Express made it successfully into orbit, and Beagle 2 began its perilous descent, right on schedule.
The descent to Mars, the 7 minutes of terror, as it's been called consistently with Martian missions, that when it enters Martian atmosphere, to get down to the surface is exceptionally difficult.
The atmosphere on Mars is about 100 times thinner than on Earth. The plan was for parachutes to slow it down before a cocoon of airbags inflated in the hope of a soft landing.
Any number of things could go wrong, burning up in the atmosphere, not quite getting the trajectory right, missing your landing area. But it's only when you get to Mars that you find out whether or not it's going to be successful.
Beagle's command team waited anxiously for the first communication from the Red Planet.
We were watching expressions. And every now and again we'd get a briefing, but we were just watching for that moment where you see the expressions that said Beagle 2 has landed. And we waited, and it didn't come.
With nothing but radio silence, Beagle's fate was a mystery.
When the engineers hadn't first heard back from the lander, the scientists knew that perhaps there was just a minor problem that could have been solved. But then 2 months later, when it was declared lost, there was definitely a sense of disappointment because we just didn't know what had happened.
Well, I can remember at the time there was a lot of speculation as to what might have gone wrong. All of the speculation assumed that that descent and landing has in some way failed.
Roughly half the missions to Mars have failed, so Beagle 2 wasn't the first. But with the evidence lost and silent, the team was left guessing as to what had happened.
Perhaps the parachute hadn't deployed correctly. That obviously could have been catastrophic for the mission. Maybe there was a fault with the heat shield that meant that the whole package might have burnt up on entry into the Martian atmosphere. Or, of course, landing at quite a high speed, relying on these gas bags to protect the lander. It would only take the gas bags not to inflate correctly, or the landing itself to be heavier than perhaps expected.
Beagle 2's fate remained a mystery for more than a decade.
Between 2003 and 2015, sadly, Beagle 2 was very much seen as something that had been a good attempt but had ultimately failed. But then something happened in 2015 that changed the narrative completely.
NASA spotted something mysterious on the Red Planet.
I got a call. Chas, hot news. We might have some images of Beagle 2 on the Martian surface. And they showed us the long shot, and we squinted. Could it be? It's a bit of a dot, difficult to see, and closer in. And you thought, actually, maybe. Then there was the final shot, and there it was, with that clear disc in the middle. and the solar panels. And it was at that point they said, that is Beagle 2, it's landed.
So when Beagle 2 was discovered, it meant a lot for the British scientific community and the Beagle 2 team, because it meant that their plans for how they landed the spacecraft were successful.
Beagle 2 had landed, but why did it fail to phone home? Scientists pored over the images of the landing site.
Further study and more photographs, the scientists determined that only 2 or possibly 3 of the 4 solar panels on the spacecraft had opened up. The ones that didn't, however, blocked the communications antenna. So that's why we could never receive a signal from the lander. But that doesn't mean that it didn't actually function.
It might have done something. It might have done something brilliant. But with that antenna trapped, we will never know. Now, how frustrating is that?
The question remains, why didn't the other panels deploy? And was that all that stood between success and failure?
It's possible that malfunctioning airbags and parachutes led to a bumpy landing, damaging Beagle's solar panels and antennae, meaning that Beagle could never phone home.
So some scientists think that the lander had actually started to perform some of the science experiments because there was an auto mode, essentially, that if the lander didn't hear any instructions, that it should begin doing the experiments it was programmed to perform. And so if it did do that, that data will be still recorded on the craft, which could be retrieved in a later mission.
How close was that mission to being entirely successful? 1 solar panel. And who knows, it might be a speck of dust. It might be something so trivial that kept that final panel furled. And we won't know, unless we go. And who knows, we might one day, something or someone might go and take a look and say, oh look, now we know. But until then, we won't know.
Beagle 2 didn't complete its mission, but key lessons were learned.
We've certainly shown that it landed, the parachute worked, the gas bags worked, everything worked. It had even started deploying itself. It's incredibly difficult to get to Mars and succeed, but for the final section, not quite to work, perhaps because of a harder landing than they expected. Who knows? We don't know at this stage, but it was a really incredible achievement to put a UK lander on the surface of Mars.
And whatever Beagle's fate, its technology has contributed to future Mars missions.
One of the instruments on Beagle 2, the mole, was actually used as the inspiration for NASA's InSight lander, which is on Mars now. That's got a similar tool on it, which is used to dig up to 1.5 meters underground to help measure the thermal properties of the planet.
So Beagle 2 certainly wasn't a waste or a complete failure in so much as certainly things were learned, lessons were learned about how things were done and things that could be improved upon in the future for missions back to Mars, but other missions around the solar system.
Today, our quest for answers on Mars continues, with NASA's state-of-the-art Perseverance rover now leading the charge.
Perseverance is a hugely exciting moment in Mars exploration. It's got an arsenal of sensors to look for signs of life and to establish if humans really could one day colonize the red planet. And with the tiny helicopter Ingenuity, we've seen the first powered controlled flight on another planet. Incredible.
When it comes to engineering, every component, no matter how big or small, is vital to success. Even a tiny fault can cause a major disaster. Like this catastrophe in West Virginia, a fatal collapse on a vital river crossing.
It was just a shock, a total shock. Nobody expected that bridge to fall.
A tiny flaw on a massive structure that triggered one of the worst bridge disasters in US history.
The fact that a bridge of that magnitude was able to collapse in less than a minute is staggering.
And a tragedy that forced a nationwide change in safety regulations.
It affected everybody. It's just something you just won't forget, the tragedy that happened that day.
The mighty Ohio River runs nearly 1,600 kilometers across America. A constantly moving border that divides the Midwest from the South.
The Ohio River flows through 6 states, and it's the source of drinking water for more than 5 million people. It also transports more than 230 million tons of cargo every year.
For centuries, the river has been a vital source of life for small towns that have sprung up along its banks. None more so than Point Pleasant in West Virginia. Journalist Jim Ross knows the town well.
This is beautiful downtown Point Pleasant, West Virginia, one of the oldest communities in this part of the Ohio Valley. This town is really built around the river. Historically, this has been an area that has built boats. It has serviced boats. It still does. Its identity is tied to the river and it's tied to its history.
And Point Pleasant has always had strong ties with its neighbors on the other side of the water.
It is very much connected with the neighboring communities over in Ohio, Gallipolis in particular. People cross the river to shop, they cross the river to work. Although they're in 2 different states, West Virginia and Ohio, people here tend to think of themselves as being one community.
Till nearly 100 years ago, this old railroad was the only crossing bridging that gap. So in 1927, work began on a solution to connect the 2 communities by road, with the Silver Bridge.
The Silver Bridge took its name from its metallic aluminum paint, but that wasn't the only thing that made this crossing stand out.
Opening to traffic on Memorial Day 1928, this 2-lane crossing was no conventional suspension bridge. Professor of Engineering Gregory Michelson explains.
The way a suspension bridge works is the roadway is supported by a series of suspension cables that cross 2 guy towers on either side of the river.
With most suspension bridges, the main cables are made of thousands of narrow wires, bundled into strands, all working as one giant cable. But the Silver Bridge was different.
What made this bridge unique was instead of suspension cables, a series of I-bars were used as the main supporting elements. So an I-bar is basically a flat bar of steel with 2 holes drilled at the ends.
The giant bridge swapped suspension cables for a series of I-bars, working like 2 bicycle chains stretched across the river. 2 I-bars were paired to create each link, while smaller bars supported the road below, all secured with vast steel pins through the eyes. For nearly 40 years, the Silver Bridge carried up to 4,000 vehicles a day. But the crossing that brought the communities closer together would very nearly tear them apart. Friday, December the 15th, 1967, West Virginia schoolteacher Peggy Huber was heading for the Silver Bridge, making her way home to Gallipolis, Ohio.
Traffic that day was extremely heavy. A lot of people were Christmas shopping, and 2 semis went by and waved to me in the car.
Shortly before 5 p.m., with rush hour traffic backing up, Peggy was stuck, unable to merge.
The bridge was completely full of traffic, and I was upset that the semi-truck drivers wouldn't let me in line. And we got caught at the light going on to the bridge.
But those truck drivers may have saved Peggy's life. At approximately 5 p.m., the 4-decade-old bridge dramatically failed.
I heard this terribly loud noise, and when I looked up, the bridge was falling.
The entire suspended section of the bridge was completely destroyed in less than a minute.
It was full of cars and people, and it just looked like Tinker Toys falling right into the river.
Of the 37 vehicles on the crossing, 31 went down when the bridge collapsed. The 2 trucks were among them. Local journalist Jim Ross was just a child when he saw the devastation.
It was really eerie seeing a couple of piers out in the water, no bridge on them, a roadway with a double yellow line going straight down into the water. looking at where the bridge used to be, it was unlike anything we'd seen, and we hoped unlike anything we would ever see again.
Peggy realized how close to disaster she had come.
Really just that stoplight. My goodness, why was I stopped and not on that bridge? It does make you think about your life different. It was just lucky.
But not everyone was as lucky as Peggy. Of the 64 people who went down with the bridge, tragically, 46 lost their lives. This was one of the worst bridge disasters in US history and sent shockwaves across the nation straight to the White House.
This was so huge that the president, Lyndon B. Johnson, assembled a bridge safety task force to mount an investigation.
In the wreckage found on the Ohio side of the bridge, investigators located their first clue, a broken eye-bar.
This massive eye-bar would have been about 30 meters above the water. When it cracked, it was the same as if the main cable on a conventional bridge had failed.
When this single link snapped, the whole bridge lost balance. Professor of Engineering Gregory Michelson explains.
It started with that eye-bar collapsing, which led to that span sort of tilting over a bit. And then once that span tilted over a bit, it yanked on the other guide tower, and then the whole bridge collapsed into the river.
The catastrophic collapse revealed a weakness in the bridge's original design.
There's no doubt the Silver Bridge was a unique and innovative design, but it was also what's known as fracture critical.
Meaning that if one single part fails, the entire structure can collapse.
While the Silver Bridge used a pair of eye-bars to create each link, other similar bridges had multiple plates joined together for additional strength.
So the idea of having multiple eye-bars in parallel is that you're not applying the load to one member, you're applying the load to multiple members at the same time. So if one of those eye-bars sees failure or sees cracking or sees corrosion, there are other eye-bars to pick up the slack.
But with the Silver Bridge, when one of the two eye-bars cracked, the other didn't stand a chance.
If that bridge utilized multiple parallel eye-bars, for example, the bridge would probably still be standing today.
With the bridge loaded with traffic, and after 39 years of wear and tear, that one small link in the chain brought the entire bridge down, like a house of cards.
That explained the sudden collapse, but not what had caused the eye-bar to fail in the first place.
Investigators examined the broken ends of the eye-bar and found evidence of a tiny flaw from the original casting process. Hidden out of sight, it had gone unnoticed for years.
Lying undetected, covered by the pin's head, the crack was slowly corroding, getting weaker, through a phenomenon known as fatigue.
When you take that corrosion and you add the phenomenon of fatigue, those cracks grow and then they propagate. On top of that, the bridge was designed in the earlier part of the century. Well, fast forward a few decades and we see a lot more vehicular traffic, a lot more semis on the road. So all of those led to a perfect storm which caused the collapse.
After the tragedy, a new crossing around 600 meters long was built just over 2 kilometers south. This time constructed as a conventional steel through-truss design and named the Silver Memorial Bridge.
This bridge opened to traffic on December 15, 1969, 2 years to the day after the Silver Bridge fell.
As a direct result of the disaster, Congress passed new legislation to ensure regular inspections of all of America's more than 500,000 aging bridges.
It came at a terrible cost, but the disaster did force us as a nation to think about this part of our infrastructure whose safety had really been neglected.
A mural serves as a reminder of the tragic event that took place that fateful December day.
It was really traumatic, and I mean, even to this day, you know, I have to think when I'm crossing a bridge, it's just something you just won't forget, the tragedies that happened that day.
In Arizona, a railroad inferno takes down a vital river crossing.
It was all engulfed in flame. I was directly under the bridge as it was collapsing.
In California, a trailblazing building cooks up a storm in downtown LA.
There would be blinding light reflecting off of the building into freeway traffic, and that was a big problem.
In Ohio, disaster unfolds as a driver and her vehicle are swallowed whole.
Her car just crashed and fell straight through it.
And in Sweden, tragedy strikes a cutting-edge warship on its maiden voyage.
The most powerfully armed warship in the world had managed an operational career that was less than an hour long.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. In big engineering, strength must always take precedence over style, because no matter how solid a structure looks, everything has its limits. Like this railroad catastrophe in Arizona, on a historic river crossing.
Hundreds of tons of rail cars crashed down onto the road below.
I actually heard the bridge as it was collapsing around me.
A disaster that made one of the hottest places in America even hotter.
It was one of the biggest fires I think I had ever seen. It looked like the apocalypse.
Tempe, Arizona, just east of Phoenix, basks in the heat of the Valley of the Sun. Bianca Bono is a local TV reporter.
Here in the valley and here in Tempe, we are definitely known for our extreme heat. We are in the heart of the desert, and during the summer months, we hit triple digits almost every single day. It's the hottest area in the entire country.
Every desert town needs an oasis, and Tempe has this more than 3-kilometer man-made lake, which is the beating heart of the city.
365 days a year, any time of the day that you go to Tempe Town Lake, you are guaranteed to find people, whether it's running, cycling, paddleboarding, kayaking, rowing crew. It is so busy.
Tempe was actually founded as a crossing point over the river, first by ferry and then by bridge. Over the decades, dozens more bridges have been built here.
None more important than this one, built in 1912. The Union Pacific Salt River Bridge is key to moving goods in and out of the city across the waterway.
This bridge is definitely iconic, and it's as old as Arizona's statehood. So Arizona is relatively new to the United States. It became a state in 1912, which is the same year that this particular bridge was built.
At almost 400 meters long, with 9 steel spans, the Salt River Bridge was a through truss design, like most rail bridges of its day.
Today, the Salt River Bridge still carries around 7 million tons of cargo a year, including corn, grain, and lumber, worth around $14 billion.
You see trains that are longer than a mile. It's just so important to transport things from Texas to Arizona to California. It's hugely significant.
Early morning on July the 29th, 2020, a 97-car freight train was heading from Tucson, Arizona to Phoenix, across the Salt River Bridge. Investigative reporter and local resident Camille Kimball was out for her morning ride and approaching the bridge.
When I start my day off by riding on the river, it's just wonderful. I was just at the tail end of my ride.
As Camille was going under the bridge, the 11,000-ton train was directly overhead.
I could tell that there was a train above me because you could hear it, cha-ching, cha-ching, cha-ching.
Shortly after 6 a.m., Camille's regular morning ride turned into a nightmare.
Suddenly that pleasant chink, chink, chinka sound disappeared, and this loud crashing sort of noise. I thought, man, this is loud. And where I was at that point was right here, right under this bridge, exactly between the trestles.
The more than kilometre-long train derailed suddenly and without warning, bursting into flames, taking part of the 108-year-old bridge down with it.
Within moments, where I was standing between these two trestles, directly above it, was a lumber car. It was ablaze, and all the fire was falling down. And soon it was all engulfed in flame. The grass, the path. I was directly under the bridge between the trestles as it was collapsing.
Camille got out just in time.
I'm getting kind of hyperventilated a little bit just with going back to that experience because it was pretty terrifying.
News crews rushed to the devastating scene. Reporter Bianca Bono was stunned by what she witnessed.
It was one of the biggest fires I think I had ever seen. It looked like the apocalypse. And then to see that part of that bridge had actually collapsed, it was quite shocking.
But the fire wasn't done yet. 3 of the cars were carrying a highly flammable chemical solvent, one releasing over 9,000 litres onto the ground below.
The flames spread like fingers all across the bridge to the center of the bridge and to the middle of the lake. Fire itself would just fall into the lake. It was a tremendous sort of hellscape.
As fire crews fought to bring the blaze under control, the entire town was waking up to a major disaster.
This area was so flooded with first responders and people that had just honestly rushed to the scene to get a look at it because they couldn't believe what they were seeing on TV. The smoke and flames, not just from that side of the lake, but the entire valley could probably get a glimpse of what was happening here.
12 cars had derailed, and around 50 meters of bridge collapsed in the raging inferno. Amazingly, despite the destruction, no one was killed or seriously injured.
I was incredibly lucky. If I had circled around a tiny bit or something, which I often do, that flame would have got me. I was literally moments away from being the one person who died in that accident.
Being here that day, it really was an unforgettable event, and there are certainly visuals that I will never forget.
When the flames died down, people wanted to know what had caused this disaster. But answers wouldn't be easy to find, because the remaining evidence was a twisted, burnt-out pile of wreckage.
The investigation is ongoing, but there's little doubt it was the fire that brought the bridge down. The question is, why did the train derail in the first place?
One theory is that Tempe's extreme summer weather may have played a part.
We are seeing temperatures of around 115, 118, which is near record-breaking heat in this area. So, of course, there are experts that have said that heat can certainly play a role.
While the aging track should have coped with desert temperatures regularly exceeding 38 degrees Celsius, this intense spike may have caused the rails to deform. Professor of Engineering and Construction, Anthony Lamano explains.
A possible reason is track buckling in high temperatures. And we can model this with an example of a straw. So as a track heats up, it wants to expand, but it can't because there's more track on either side. If you have a lot of stresses in something that's long and narrow, it tends to buckle. That would clearly cause a derailment.
And as reporters like Bianca Bono discovered, this wasn't the first derailment at this location.
Just about a month prior to this incident, there was another derailment in that almost identical spot there. It was much more minor in comparison, but it was in that exact location. It was very surprising for us to learn that a derailment had happened and we didn't know about it.
The line was repaired and reopened just 2 days after the first incident.
They came back a few weeks later to do another examination, and again, they deemed it to be safe and reopened it. So there were 2 inspections of that location that were done between the first and the second derailment.
However, it's possible these repairs played a part in the second, more catastrophic event.
A research study found that rail buckling is more common after major maintenance work, like the repairs to this line, making derailment much more likely too.
But with the rails damaged by the inferno, it's a hard theory to prove, while the location of the crash might suggest a different story.
Built structures like bridges tend to have much more solid foundations than the ground around. And as trains go from flexible to hard foundations and back again, there can be an increased risk of derailment.
So the idea behind this theory is the track is behaving differently under the train on the bridge than it does under the train on the ground. That is one of the leading factors to derailments for trains when they approach and go onto the bridge, and then when they come off of a bridge onto the ground. The stiffness change can cause problems, and that could be one of the causes of failure in this instance.
But if the track isn't to blame, could it simply have come down to the age of the bridge?
One of the possibilities of failure with a steel truss bridge is steel fatigue, where repetitive loadings of a steel member can cause the steel to fail. An example of this would be a paperclip. We've all played with a paperclip. We open the paperclip up, still together, close it back down. Maybe that's 1 train crossing, maybe that's 1,000 train crossings. But if we do it too much, back down, eventually the steel fails.
Only time will tell whether the heat, the track, the bridge, or just bad luck was to blame. But with 2 derailments in the same place, only a few weeks apart, chances are something was wrong.
While the blaze cut off a major rail route, crucially, almost 2/3 of the bridge remained intact and structurally sound. Just 4 days after the collapse, a 45-metre damaged section had to be demolished. Then crews got to work on the rebuild.
Engineers certainly pulled out all the stops, and incredibly, they had this iconic bridge rebuilt and reopened in just 15 days.
While the fire-resistant capabilities of the bridge will undoubtedly be scrutinized, whatever the outcome of the investigation, hopefully both engineers and the industry will learn from the disaster that struck this desert town.
As engineers, it's important to look at problems and find out why they happened so we can learn from those mistakes and figure out how not to let it happen again.
This bridge is as old as the state of Arizona. It's been here for more than 100 years. If you come here today, you would have no idea what this bridge in this area went through that day.
With pioneering architecture, engineers are always pushing the boundaries. But sometimes those boundaries push back. Like this oversight in California, a design masterpiece that was dazzling its downtown neighbors.
There would be blinding light reflecting off of the building into freeway traffic, and that was a big problem.
A glaring mistake that had locals hot under the collar.
There were stories about traffic cones melting, trash cans being lit on fire.
And an ingenious solution to take the shine off this standout structure.
Sometimes when you push the limits, there's a danger you can go a little too far.
Los Angeles, California. What was once a small town founded by the Spanish in 1781 has grown to become a world-famous metropolis. Local journalist Kate Dioma is a long-standing Angelino.
Los Angeles is an international city with multiple characteristics. We have the Hollywood glitz and glamour, we have the laid-back, the valley lifestyle, we have the beach vibe, Los Angeles is a one-of-a-kind kind of place.
And one part of LA has become a beacon for daring design, downtown.
Architects recently, in the last few decades, have really taken on the challenge of living up to the Hollywood glamour in the architectural sense, really getting on board with showing off. A lot of new structures going up that are really making a statement. And arguably, the one that kicked it all off was the Disney Concert Hall.
Since opening its doors in 2003, the $260 million concert hall has been home to the LA Philharmonic Orchestra and combines world-class acoustics with eye-catching architecture.
It was a major deal when this was opened. It was a grand gala. The street was closed off. It was a major celebration of this new architectural landmark in Los Angeles.
This stunning, internationally acclaimed building has rightly become an LA icon. It's covered by 6,500 steel panels, no two the same in shape or size.
Ensuring every panel would fit together seamlessly with its counterpart called for some serious creativity.
The solution was as bold as the design. They took three-dimensional software used in the production of French fighter jets to create buildable construction plans, panel by panel.
Senior technical designer Kais Al-Rawi is an expert in computer-aided design.
The Walt Disney Concert Hall is one of the first major projects to utilize computational software that have been taken from other industries such as the aerospace and automotive industries and applied into architecture and engineering.
But this shining star of the Los Angeles skyline would soon be making waves for all the wrong reasons. Shortly after opening in October 2003, trouble began.
So they finished this beautiful building and they discovered the surface was so reflective, it was causing all kinds of problems.
As Professor of Architecture Mark Schiller explains, the concert hall was once again making headlines.
There was an explosion of newspaper articles with catchy titles like Disney Hall is glaring back at you. Whose bright idea was this?
Neighbors also complained that this bold building was shining too brightly.
Everyone loved it except for the neighbors because it was really super reflective and the sun reflections were shining into the neighboring apartments and causing a heat wave.
The examples that were given by people who lived around the building were that the temperature in some of the surrounding apartments would bump up 15 degrees Fahrenheit within a period of 15 minutes.
It's reported that their air conditioning bills were through the roof, and in the afternoon they had to keep their blinds down even though the sun was behind them just to combat the reflections from the concert hall.
It wasn't just heating up the neighbors. Nearby traffic was being dazzled too.
There's a freeway that runs right behind the building, the 101 freeway. There would be blinding light reflecting off of the building into freeway traffic, and that was a big problem.
This shiny new building, with thousands of highly reflective steel panels, was unintentionally harnessing the power of the sun.
The County of Los Angeles, they began receiving stories about things like spontaneous combustion of a trash bin or a melted traffic cone. Like some people said, death ray. It didn't kill anybody, please, but it was dangerous and it did melt things, and it was this ray.
There were even rumors of bystanders roasting hot dogs on the street. Whether true or not, they quickly became legendary.
It seemed that the trailblazing new concert hall was out of tune with the California sunshine. The big question was why? Mark Schiller was brought in to investigate. He discovered the problem was as clear as day.
The building has glare. There's two kinds of glare. There's the visual glare, but there is also thermal glare or solar glare. And that is where we are getting concentrations of sunlight and temperatures are going up very rapidly.
The glare was attributed to specific panels in the building's unique exterior. Senior technical designer Kais Al-Rawi explains.
Glare from reflectivity occurs due to a combination of the geometry of the project as well as the material that is used. The geometry itself directs the solar rays in a specific direction, and particularly when they are converging solar rays. And then the material itself is what intensifies that reflection.
What we have is some surfaces that are highly reflective, that are convex, and they cause visual glare. They make people squint. They might interfere with traffic. The other kind of surface that is so dangerous is the concave surface. And this is because it concentrates all of the light that falls on that surface down into one spot. As the sun goes by like that, that spot goes by underneath like that.
Think of those concave panels like a mirror. If that mirror is placed in direct sunlight, it can focus the sun's rays into one spot and potentially start a fire.
Mark and his team studied the impact of these hotspots in detail.
This little thing will measure the temperature, and you set it, and it records every 15 minutes or whatever you want.
To monitor the heat, the tiny sensors were installed around the building in holes drilled in the pavement.
We found that the temperatures were getting into the 140, 145 degree range. Some people say that that would be hot enough to cook an egg. Well, actually, you could cook an egg on that.
Even though state-of-the-art technology was used to design the building, it didn't predict this flaw.
I believe at the time of the design of the Disney Concert Hall about 25 years ago, the digital simulation and analysis tools were fairly limited, and it was fairly challenging to perform a digital simulation that showcases the reflectivity. Today, we're able to do digital simulations both to check the geometrical reflections and as well to check the intensity of those reflections in comparison to the environment around.
People have asked us, did you feel those rays? Yes, absolutely. While we were working on the building, if you walk through one of those focal points, you know it right away.
Thankfully, there was no serious damage, but it was still something that needed to be fixed.
The question was how to solve the problem without impacting the concert hall's unique aesthetic. The first job was to identify the panels that were a potential danger to the public.
This is an example of the material that's on the building, and it's these surfaces that can cause the problem. So we found the surfaces that were like that, and we tested how we could treat them. This was a film which did not change the look or color of the building too much, but it still was too much of a problem. And so what we found was we had to find some other method.
While there's no doubting the design was cutting edge, the solution was definitely old school.
We took the panel and we began to test ways of solving the problem by modifying the texture. So we used hand sanders. We used an orbital sander, and we used a linear vibrator sander. We tested different densities of sandpaper.
In testing, they found one solution that solved the issue. But the only problem was now they had to apply it to around 400 square meters of panels.
What we actually ended up doing was putting somebody in a bosun's chair on the side of the building with a hand sander, and they sanded the portions of the surface that were causing the problem.
What they had to do basically was manually take the shine off the building.
It just took enough of that off so that the nature of the building was not changed. And that was our intention. Solve the problem without destroying the art of the building.
Now, more than 15 years later, while the concert hall may have lost a little of its gloss, it still continues to shine as a beacon of groundbreaking design and development in downtown LA.
When the Disney Concert Hall was built, it really was the birth of the renaissance of downtown Los Angeles. I think architecture that can be enjoyed is a wonderful phenomenon. So I think what the designers learned from this is that it's great to do a flashy building as long as it's not too flashy.
When engineering goes wrong, catastrophe can strike in plain sight. But some fails lie hidden just beneath the surface.
Incredible, and that is oil.
Like this disaster in Ohio, which shocked a whole city.
Her car just crashed and fell straight through it.
An engineering fail that took out a highway.
There was pieces of concrete shearing off and falling all over the place.
And a race against time to save a driver trapped not on, but underneath the road. Toledo, Ohio, sits at the western tip of Lake Erie. Founded nearly 2 centuries ago, this modern metropolis grew from humble foundations. Tom Henry is a local journalist.
One of Toledo's nicknames is Frog City. It's based on our connection to the Great Black Swamp, which was a major historic swamp in this part of the country.
Frog City is famous for its automotive industry and glass manufacturing. Yet, it was the fertile farming ground that paved the way for success.
But wet ground and growing cities don't always mix. July the 3rd, 2013, 12:15 p.m. A school principal was driving home on Toledo's North Detroit Avenue.
She was just like anybody else driving along, and you can see how busy it is now. She saw somebody in front of her go over, something just looked a little different.
As the principal drove over the same spot, the road beneath her suddenly gave way.
Her car just crashed and fell straight through it. She was free falling down many feet, as many as 20 feet.
A giant sinkhole had opened up, swallowing the vehicle. The driver was trapped, and water from a burst main was pouring on top of her car.
Is there water filling up in the hole?
Yeah, it's filling up the hole. She's moving a little bit. If you guys can hurry, she's raising her hand.
They're coming lights and sirens.
Firefighter Lieutenant Pat Lanahan got the call.
And I was pretty shocked to hear a sinkhole, especially in a residential area like that, and a car involved as well. It was quite shocking. We got the run, we jumped in the rig, and we headed out the doors.
As water continued to gush out, Pat and the team swung into action.
You could clearly see the driver was in distress at the bottom of the hole with a large volume of water. She was obviously very distraught at the situation.
With a terrified driver and water now coming into the back of the car, time was of the essence.
She was afraid of getting out of her vehicle until she knew it was safe. She had said, "Sweet Jesus, Jesus, Jesus." She kept hoping that faith would get her through it.
In danger of sinking further, and with the situation deteriorating, the rescue team needed to get her out fast.
There was pieces of concrete shearing off and falling all over the place.
Thanks to the quick actions of Toledo Fire and Rescue, the driver made it out unscathed.
Once we got her out, that was a huge thing for us, and a big relief once we got out and no one got hurt.
She was lucky to survive the impact in the first place. That must have been a very horrifying event.
With a gaping hole in North Detroit Avenue, the people of Toledo demanded to know what had happened.
The broken water main seemed like an obvious clue, but investigators quickly ruled that out as collateral damage from the collapse.
The problem lay much deeper, with 2 old sewer pipes that had ruptured.
Like a lot of old cities, a lot of our infrastructure is aging, and some of it's well over 100 years, with roads, water lines, sewers. You know, it's difficult to keep up with a lot of this.
When something is out of sight, it can also be out of mind, especially when it comes to sewage. but in old cast iron pipes, it can create a slime layer that produces toxic gas.
That gas was hydrogen sulfide. Water engineering expert Soroush Zamanian explains.
When the hydrogen sulfide from the sewage have a chemical reaction with the oxygen in the sewer system, it forms a chemical component known as sulfuric acid, which is a very highly corrosive chemical and can reduce the thickness of the pipe.
Sulfuric acid had been corroding the inside of these pipes for about a century. 2 key sewer lines had been getting weaker and weaker, and it was all hidden from view.
But corrosion alone hadn't triggered the collapse. When these pipes were installed, there wasn't much traffic around, and vehicles were much lighter.
These days, roads everywhere get heavy usage from trucks and just the sheer volume of traffic. That heavy pounding makes its way deep underground and can damage the pipes even further.
Nearly 100 years of corrosion combined with increasing traffic explained the failed pipes. Yet there was an additional mystery. When the pipes were originally installed, they were firmly supported by compacted earth. But when the sinkhole opened up, it revealed a vast hole where the dirt should have been.
As more and more cracks formed, the sewage flowed out through these weak spots, washing away the ground beneath the road in a process known as exfiltration.
Exfiltration of sewage occurs around the pipe and it washes out the soil particle around the pipe. And this loss of soil particles around the sewer system in a long term can result in formation of large sinkhole.
Over time, both the liquid and material were washed away, leaving the massive void under the road just waiting to collapse. So engineers quickly went to work repairing the pipes and rebuilding the road.
There was a challenge because of how wide and how deep it was from an engineering standpoint, but they did a pretty remarkable job in fixing it. It took about 5 or 6 days.
This was a very narrow escape. The collapse was so quick and so huge, it's amazing other vehicles didn't end up in the hole.
Across the US, there have been multiple sinkholes like this. So the next question was how to prevent them.
I think one of the take-home messages is that you really need to investigate your infrastructure. You need to stay on top of it. You know, what's beneath your feet, what you don't see, just because it's out of sight shouldn't be out of mind.
In 2002, the city pledged more than $500 million to inspect up to 160 kilometers of pipeline every year in a project called the Toledo Waterways Initiative.
It was a horrible incident. It ended up in a positive manner in that we were able to get the patient out of there with no serious injuries, but we hope that this never happens again.
In big construction, engineers are constantly innovating with bigger, bolder, and grander designs. But if things go wrong, the catastrophe can be just as massive. Like this disaster in Sweden, an ancient warship with a fundamental flaw.
Ship design was basically trial and error, and here there was a major error.
The Pride of the Navy sunk less than 1,600 meters into its maiden voyage.
The most powerfully armed warship in the world had managed an operational career that was less than an hour long.
And a tragedy that turned to triumph with a resurrection more than 300 years later.
This was no quick fix. Even today, engineers are in a constant battle to save this historic wreck.
Stockholm, Sweden's capital, founded nearly 800 years ago, it's made up of 14 islands connected by over 50 bridges. Surrounded by water on all sides, it's also known as the Venice of the North. Historian Dr. Fred Hocker has lived and worked in the city for over 15 years.
Stockholm was established to be the main city, largely because it's very sheltered from the wind from almost all directions. And it's sheltered in a strategic sense. It's very difficult for an enemy to get all the way up here to threaten the city.
By the 17th century, Sweden was at the peak of its power, controlling areas of Denmark, Finland, Germany, and even Russia.
Sweden was an aggressive imperialistic power. We were the bullies of the Baltic. The king was trying to build up the navy, and for that he needed not only more ships, but new kinds of ships.
In 1625, as a symbol of Sweden's growing maritime might, the king commissioned this, the Vasa.
This was the first double-decker warship in Sweden's history and still holds a special place for the nation.
Today, around 1 million people a year visit its museum, where Fred Hocker is director of research.
Vasa was cutting edge. The basic configuration of Vasa, 2 full decks of heavy guns, would end up being the fundamental backbone of most of the big navies of Northern Europe.
At around 68 meters long and over 48 meters tall, the sturdy oak ship was fitted with more than 64 cannons. But, as one of the ship's modern-day carpenters, Robert Jonsson, explains, the Vasa was about more than just firepower.
It was not only a warship, but also a symbol of big Sweden, also the dream of big Sweden. So we were a major project, the finest builders.
But a fundamental flaw meant this trailblazing weapon of war was journey-bound for major disaster. Sunday, August the 10th, 1628, the Vasa set sail. For the citizens of Stockholm, this big ship was a big deal.
When the ship took off on its maiden voyage, everybody in Stockholm was watching. The banks on both sides here were full of people, because this was the most powerfully armed warship in the world.
Crew members' families were on board for the big day and would swap place with 300 soldiers before the ship headed out of her base on the edge of the Baltic.
Conditions were calm as they headed out of port.
After they set sail, they were coming down along these bluffs. And this little dip in the bluffs channels all the wind from the southern part of Stockholm into a big gust that blows straight across here.
Around 1,500 meters out, a gust of wind caught the mighty ship.
As the ship got really right out in front of the middle of this gap, the main strength of the wind took the sails, and it heeled the ship over.
Water began rushing in through the open gun ports. As ship's carpenter Robert Jonsson explains, the Vasa was now in serious trouble.
Imagine looking out and seeing water pouring in. Feel the fear of seeing what is happening with all this water and chaos.
The Vasa was sinking.
People were scrambling to get out of the below decks part of the ship and get off the ship. And then right about here, where we are now, the ship went under the water.
What began as a celebration had ended in tragedy.
We have quite a few skeletons found on board the ship. A lot of people couldn't get out of the ship.
While the exact passenger numbers aren't known, and many did manage to escape, sadly 30 people died, most trapped deep inside the ship.
They're all clustered near the feet of ladders. Once the ship started to tilt over, it's very difficult to climb a ladder that's leaning to one side.
But why had the pride of the Swedish Navy vanished in front of people's eyes, just over a kilometre from shore? Unbeknown to the public, it seems a major concern had been raised before it ever set sail.
Crucially, the captain told the Vice Admiral that the ship was unstable. He even gave a demonstration. Just 30 men running back and forth on the upper deck was enough to make it roll.
As ship's carpenter Robert Johnson explains, this instability was all down to its revolutionary double-decker design.
The Vasa is well constructed, but their dimensions are a bit wrong. The problem with the shipbuilder, he had never built a ship with 2 gun decks.
While advanced for its time, it turned out that being ahead of the game was part of the problem.
In the 1600s, the use of accurate mathematical models to predict a ship's stability was still more than 100 years into the future.
The mightiest warship Sweden had ever designed was built using a system of trial and error.
There were no drawings, just people saying, this is the width and this are the dimension, and then with up to the craftsman to put it together. No drawings, just knowledge, what to do and when to do it.
In their ambitions to build big, the Vasa had been designed too tall and narrow, causing her to be top-heavy.
Every ship has to balance certain forces. It has to balance gravity, pushing the ship down, and buoyancy, pushing it up, in such a way that the ship wants to stand upright. And in Vasa's case, gravity is acting much higher on the ship than the buoyancy keeping it afloat is. And so when it heels over, gravity wants to keep pushing it over. Or as one of the people at the inquest said, the ship doesn't have enough belly.
Vasa's center of gravity was simply too high, and once water started pouring into the gun ports, there was only one way the ship was going: down.
The Vasa's sinking wasn't the end of the story. More than 3 centuries later, salvage experts attempted to raise it from the bottom of the sea, in a titanic feat of engineering.
Navy divers dug tunnels under the ship and used steel cables to suspend the hull, like in a basket, before slowly lifting it free of the mud, little by little, over more than a year.
On Monday, April the 24th, 1961, with thousands of spectators once again lining the shore, more than 300 years after she sank, the Vasa finally rose again from the darkness.
What's even more incredible is that they managed to seal the hull enough to make the 3-century-old wreck float again. The King of Sweden even went aboard to celebrate Vasa's resurrection.
Divers spent 5 years recovering thousands of scattered pieces while scientists got to work preserving the ship. Museum conservator Johanna Sandström explains.
The gun ports had fallen off, the top deck was almost gone, and all of the sculptures had fallen off. So she was meticulously pieced back together into what we see today, and she's been called one of the world's largest jigsaw puzzles.
Saving Vasa would be no easy task. Every piece had to be preserved, no matter how long it took.
She was sprayed for 20-odd years with a substance called polyethylene glycol, which is a water-soluble wax. So she was sprayed continuously, and after that she was air-dried slowly for 10 years before she took her place in the new museum built for her.
On June the 15th, 1990, after nearly 30 years of painstaking preservation, the Vasa was finally ready for the public to see her again in all her former glory.
Amazing, 97% remain of Vasa. And people who come in this museum, one word that occurs is wow. History everywhere you look. A sunken ship is taken up and is so well preserved. That is surreal, but it's real.
And with a dedicated crew constantly working to keep the Vasa in ship shape, this maritime marvel should be around for years to come. In Miami, a major disaster leaves a nation in mourning.
The side of it was completely gone. It was the shock and the awe because you have no idea what just occurred.
In Canada, a gaping hole opens up in the middle of the nation's capital.
It was massive. It was water just rushing down here. It basically looked like you were looking inside of Niagara Falls.
In California, one of the world's most famous bridges is making a big noise.
There are reports from as far away as 8 miles. What is going on here?
And in the UK, an iconic London bridge in imminent danger of collapse.
There was nearly a riot on this side of the river. The impact was absolutely tremendous.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. In everything they build, engineers must consider the relentless forces of nature. Any weakness can be exposed with devastating consequences. Like this disaster in Florida, a tragedy that struck a beachside community and made global headlines.
Champlain Towers, it collapsed.
A condo building that was devastated in the middle of the night.
I thought it was a storm. The ground shook. Thunder does not make the ground shake.
One of the deadliest catastrophes in American engineering history.
Some of the officers were actually in the garage trying to help people out. I'm amazed and proud of those 3 young men and what they did when they got here.
This building went straight down. I mean, it was just flattened.
The 4 unit, the 3 unit, the 2 unit, the 1 unit. If you were there that night, you didn't make it.
Miami, Florida, famed for endless golden sand, is also home to beachfront communities like Surfside. Wendy Rhodes is a local journalist.
This is the beach in Surfside right here. Surfside is a very small, quiet family community for people to come and just relax and enjoy the beautiful nature and beaches that Florida has to offer. It's really quite lovely.
Surrounded by sand and surf, an uninterrupted view is a must. To achieve that, builders use a technique known as flat slab construction. Structural and forensic engineer Joel Figueroa Valinas explains.
A flat slab structure is basically built out of columns and walls supporting floors. There's essentially no beams. It's a very simple, very quick method of construction, and there's no need to construct secondary walls. There's no need to construct additional elements. The integrity of the building is primarily relying on the connection between that column and that floor.
Effectively, the floor slabs are the beams. So steel reinforcement strengthening the slabs and connecting them to the columns is crucial to supporting a structure like this.
Built in 1981, Champlain Towers South was similar to many of the neighboring condos on the block. Former resident Steve Rosenthal enjoyed the elevated and vibrant 136-unit neighborhood.
It's a wonderful community, it really is. I knew all my neighbors, or most of them, in Champlain Towers. It's just beautiful and wonderful. I had the ocean as my background. It's everything you could want.
But in 2021, this tight-knit community's world was about to come crashing down in one of the deadliest disasters America has ever seen. Early morning on June the 24th, Steve Rosenthal was in bed in his 7th floor apartment.
It was about 1:15 in the morning. I heard the loudest thunderclap I ever heard in my life.
Surfside resident Nicholas Balboa was also having trouble sleeping.
I decided to take my dog out for a walk, and I heard this loud sound. At first I thought it was a storm, but then I heard it again, and this time the ground shook. Thunder does not make the ground shake.
This was no thunderstorm.
The bed began to shake. The room began to shake. I ran out of bed, go to the living room. Well, it's just all dust. Can't see anything.
Although Steve didn't know it yet, the whole center of his building had collapsed.
I go to the front door, I open up the door, and I get hit with a plume of smoke. Like a sonic boom, it just knocks me back.
Seconds later, the entire eastern side also came crashing down. Capturing the only known photograph from inside, Steve was now trapped in his 7th floor apartment.
Everything that's behind that rubble, all gone. And the destruction just stopped like 2 feet from my door.
Emergency services raced to the scene. Surfside Police Captain John Healy was among them.
We train all the time, and I don't think any training could prepare you for what you're about to see.
Some of his officers were already on site. Body cam caught their reactions.
Captain, hey, the Champlain Towers, the building, it collapsed.
The front of the building was still standing here, but the side of it was completely gone. It was the shock and the awe because you have no idea what just occurred.
55 of the 136 condo units had been reduced to rubble, leaving the rest of the tower potentially unstable. Fire Rescue Battalion Chief Brandon Webb knew time was against them.
The pool deck had collapsed into the garage. That exit wasn't there anymore, and the debris was blocking the door. So the only way out of the building was either from an upper floor by ladder or through the parking garage that was flooded and partially collapsed.
Some people, like 7th floor resident Steve Rosenthal, were trapped on their balconies.
The fire engine cherry picker is now rescuing people, starting with the corner units. Even when you're in the cherry picker, you're thinking, well, is the front of the building going to collapse on us?
While the fire rescue team was evacuating people from above, Captain Healy's officers were searching down below.
Hello? Where are you? Are you okay? What? Are you okay? Is anybody down there injured?
Some of the officers were actually in the garage trying to help people out. A portion of the building that was still standing but partially collapsed, trying to help people. So when I see that, I'm amazed and proud of the courage of those 3 young men.
We had gotten the people off the balconies, we had gotten the surface trap people out, but we had identified that there were still people in the building. We could see flashlights on the upper floors. They started their way up with fire crews, doing targeted searches of the remaining building.
As news of the tragedy quickly spread, journalists like Wendy Rhodes were stunned by what they saw.
It was a horror show. It literally looked like a dollhouse that had been split open, and you were looking inside the dollhouse with all the furniture.
Nicholas Balboa heard a boy crying for help. He quickly alerted the rescue team.
When we found him, he was in his PJs, right? You know, everybody knows what home is, right? That's where you're safe. And for it to just completely fall out from beneath you randomly in the middle of the night is just, I couldn't imagine. I absolutely couldn't imagine.
The boy was rescued, but sadly it was too late to help his mother.
I wish I could have done more, but you know, she didn't make it. To be 15, you know, he needed his mom still.
The search continued around the clock, but as the days went by, the odds were increasingly slim.
I knew it was bad news. I think everybody knew it was bad news. This building went straight down. I mean, it was just flattened. So we knew from the beginning that the odds of
finding survivors was going to be pretty low.
After 32 days of searching the wreckage around the clock, the final victim's body was found. In total, 98 people had lost their lives in one of the worst construction disasters the US had ever witnessed.
They were my neighbors. Of the 98 that perished, I probably knew 60 of them for sure. The 11, the 10, the 9, the 4 unit, the 3 unit, the 2 unit, the 1 unit. If you were there that night, you didn't make it.
The world was watching and they wanted answers.
Everybody's question was, what happened? How could this have happened? What went wrong?
The National Institute of Standards and Technology, a federal agency with expertise in analyzing building failures, launched an immediate and far-reaching technical investigation. For experts like forensic structural engineer Joel Figueroa Valinas, the security camera footage was a major clue.
My first thought was, this has to be a flat slab building, and the reason for that is because of the way the collapse was very clean and vertical. It just came straight down. In flat slab construction, the joints of the slab connect the columns. One of the downsides is reduced redundancy. There's not a lot of belts and suspenders in that type of construction.
Just one failed connection with a column can be catastrophic.
Once one of those floors fails in their entirety, gravity takes over. So the building essentially comes down as fast as gravity can bring it down.
The type of structure explained the speed of the collapse. The big question was what had caused it to fail in the first place. Eyewitness accounts alerted engineers' suspicions to one area. Mehrdad Sassani is a professor of structural engineering.
Some people saw that the pool deck, which was the roof of the parking garage, collapsed a few minutes before the building collapsed.
Although not visible from the CCTV footage, a failure from below fits with the way the structure fell.
At the first view, one might think that the collapse started from the top, but the motion starts from the bottom and propagates up rather than starting from the top, propagating down.
Any failure in that pool deck or garage area would have potentially initiated a collapse, and it's dragging those elements down to the ground with those other elements that have already failed.
An earlier engineering report, released in 2018, had identified potential problems in the slabs between the pool deck and the garage. Soon after the collapse, footage emerged proving that water had been seeping into the reinforced concrete slabs, which were fundamental to the structure's strength.
Reinforced steel is great until water gets in. But once it starts to corrode, rust can expand the metal up to 7 times its original thickness, cracking the concrete in the process.
Which makes all of that reinforcement potentially deficient to carry the structural loads and even to stay interconnected with the other concrete elements.
Over time, if just one of those connections in the parking garage failed, it could lead to a phenomenon known as punching shear.
Punching shear failure occurs when the slab is overloaded and/or when the connections don't have enough strength.
Once one weakened column failed, the weight of the slab could have proved too much for its neighbors to bear.
The load that was carried by this column now needs to be carried by the surrounding columns. That transfer could lead to significant amount of horizontal force applied to the structure.
Those columns holding up the deck would essentially punch through the slab. Without any support, the next floor then drops and so on, causing what is known as a progressive collapse. This type of failure can come with practically no warning, and the results can be devastating.
But it may not have just been a leaky pool deck. Huge planters around the sides, many not on the original plans, were adding thousands of kilograms in extra weight.
So it could be overloaded there is a balance between the load and the capacity.
The year before the disaster, there was evidence that concrete was crumbling away from the steel reinforcements. This could have been a warning that the extra weight was weakening this entire area.
Whatever the eventual outcome of the investigation, one thing is certain. This terrible tragedy shocked not just Miami, but the whole world. Ten days after the collapse, the surviving Western Tower was deemed unsafe and demolished. Residents living nearby began to question the structural integrity of their own buildings.
These people, they need answers. They need to know that they're safe in their own homes, and when they go to bed at night, their building isn't going to collapse.
Political leaders called for immediate inspections of other older condo complexes. And while the investigation is still ongoing, potential problems of any kind in any building have to be examined and dealt with.
If we as engineers are to learn anything from this, is that there are three main things to have a durable structure. One of them is design, the other is quality control during construction, and the third is maintenance. And if any of those are missing, then we should really revisit how we're doing this process.
And for the 98 Surfside residents who sadly lost their lives, their memories will never be forgotten.
I saw a side of humanity that I've never seen. And I hope I'm never in such a tragedy that I have to, see it again. I hope I can see it on a daily basis and that it doesn't take something this horrible to bring us together as one people.
You learn a lot about your friends and the community when a tragedy like this happens. People have stepped up for me, and life goes on. It has to.
When it comes to bridges, engineers are constantly striving to make them bigger, better, and stronger. But any change, no matter how small, can have unintended consequences. Like this story in California, a major safety upgrade that made a big noise.
If there's a problem, it's going to be far worse on a suspension bridge than on just about any other kind of structure.
One of the world's most famous bridges was blowing in the wind.
When it started howling, people clearly wanted to know why.
San Francisco, California, the city by the bay, is regularly voted as one of the most beautiful places on Earth. Gabe Moline is a local journalist.
Otis Redding in 1967 sat on a dock right over there in Sausalito and wrote "Sitting on the Dock of the Bay" while he was looking at this beautiful city right before him. I just think that's an incredible image.
For 80 years, this stunning cityscape has been dominated by the Golden Gate Bridge, one of the most famous structures on Earth.
The Golden Gate Bridge is easily the most iconic landmark in San Francisco. Everyone who visits here wants to see it, wants to walk across the bridge. It's photographed probably 1,000 times an hour, if not more. You can't imagine San Francisco without it.
Every year, 40 million vehicles cross the more than 2,700-meter-long bridge, while 10 million visitors flock just to see it.
These statistics are staggering. And if you attach all of the wires and the main cables end to end, they would stretch more than 3 times around the world.
And it was all to connect San Francisco with the north across the deep and wide Golden Gate Strait.
At its narrowest point, the channel is nearly 2 kilometers across and more than 100 meters deep. Add in earthquakes and high winds, and building a bridge here was one serious challenge for bridge engineers.
Dr. Stephen Ressler is a former US Army and civil engineer.
It really was the deep water of the Golden Gate that required that the principal structural supports all be very close to the shoreline, and that a single long span would arc out across the body of water without any intermediate support down below. That was really an act of amazing vision.
Initially conceived in the 1870s, this vision took decades to become a reality, with construction finally starting in 1933.
So the Golden Gate Bridge opened in 1937. It took 4 years to build. At the time, it was the longest and tallest suspension bridge of its kind.
The bridge has been named as one of the wonders of the modern world by the American Society of Civil Engineers.
The vast bridge stands seemingly solid as a rock, but it depends on a constant, careful balance of forces.
This part of California is well known for earthquakes, but in addition, at the Golden Gate, the bridge was going to be subjected to tremendously powerful winds.
Despite the picture-perfect views, this location is hostile, so the Golden Gate was designed to withstand sustained winds up to 112 kilometers per hour.
I mean, just on the other side of us, it's all open ocean, it's the Pacific Ocean. And there's just a gigantic wind tunnel that comes right through, right across the bridge.
When the wind blows on a suspension bridge, particularly one that's very long and slender and thin, the tendency is for vibrations to begin occurring. Those vibrations sometimes are in an up and down mode like this. More dangerously, the vibrations can be in a torsional or twisting mode like this.
Thanks to major strengthening upgrades, the Golden Gate has endured storms for more than 8 decades.
It can get really, really windy across there. I've driven across that bridge when it's scary to drive across the bridge because you're just white-knuckling it on your steering wheel, you know, being kind of pushed around by the wind.
But in the summer of 2020, the bridge was at the eye of a very different type of storm. In early June, on a windy summer's day, local resident and musician Shirin Jafari was admiring the Golden Gate.
My family and I were actually walking by the Golden Gate Bridge, and we heard this beautiful sound of something like a didgeridoo. And we really thought that someone was playing an instrument.
But there was no instrument. Raymond Bergstrom Wood was out exercising.
I was biking up here, and the second I got to the bridge, it was just very loud. It's sort of like a whistle with multiple tones. I could tell that it was coming from the bridge, but not really where. In my eyes, it was like the Golden Gate Bridge was singing.
The strange sound soon started to spread across the internet.
I took a 1-minute video and I uploaded it, and it instantly went viral.
I took a video and posted it online. About an hour later, my phone was just exploding with response from all over the place.
There are reports from as far away as Daly City from people that can hear this sound. That's like 8 miles. It's kind of like, and I said to myself, how could this happen? What is going on here?
The noise was making world news, but at first its cause was a mystery.
This is one of the world's most famous bridges, so when it started howling, people clearly took notice and wanted to know why.
Although still standing very proud, the Golden Gate Bridge was now also very loud. It soon emerged that the howl resulted from a major safety upgrade program known as the Bridge Wind Retrofit.
The objective of this ongoing project was to improve the wind load resistance of the structure such that it would be capable of withstanding a 100-mile-per-hour wind at some time in the future. It's a good, logical, reasonable step to take to account for the ever-changing nature of our climate.
The The job list included adding safety nets and streamlining the structure.
This bridge is so iconic, it feels like it's been there forever. But in the 1930s, this was at the very cutting edge of engineering knowledge. So any changes have to be very carefully thought through.
One key improvement was replacing the decades-old guardrail along the pavement. Professor of Engineering Abul Hassan Astanayasal explains.
So the old guardrail has very wide members. You can see these members here, and very small opening. So the whole area that is open is only 40% of area. 60% is solid, and wind puts a lot of pressure on that 60% solid. So they decided that let's take this out and put a new guardrail on the west side, which is much more open. So now the wind can pass through it and the wind pressure would drop.
The act of slimming down those vertical slats so that they present less area to the wind could actually have a fairly substantial effect on lessening the amount of force that the bridge feels in a heavy windstorm.
But this clever fix to protect the bridge turned out to be the source of the strange sounds.
When the wind passes through this new guardrail, now the wind is trapped with the roadway. And the top member, this handrail, has a very special curved, streamlined profile. So the combination of air getting into the bridge area and combined with this handrail profile is creating the sound that's very much similar to the sound of flute.
The drone left many wondering, should engineers have predicted the noise? Not so, says civil engineer Stephen Ressler.
Is it reasonable to expect that engineers who were designing a railing, purpose of which, in this case, was reducing the amount of wind force applied to the structure, is it really realistic or reasonable to expect that engineers would have looked beyond those principal purposes and asked the question, well, is this railing going to create an unusual sound?
With no signs of the sound stopping, in late summer 2020, bridge authorities announced that they were actively working to resolve the now famous drone.
Engineers have been wind tunnel testing to pinpoint exactly which bits of rail are making the noise. The hope is that the Golden Gate Bridge will once again be as quiet as it had been for the first 8 decades.
With the investigation still ongoing, the bridge's strange music continues to divide the critics.
There are certainly people that are very, very mad that they have to put up with this sound who live nearby. But there are some people who really like it. There are some people who harmonize along with it.
And when engineers do finally fix the drone, for some, the silence will be golden. With big infrastructure, engineers can dedicate years to just one project. But make just one mistake, and the consequences can be devastating. Like this story in Canada that struck at the heart of the nation's capital.
I was in shock. I was in awe. Everyone was fleeing.
A huge hole opens up in the middle of downtown Ottawa.
It was massive. It was water just rushing down here. It basically looked like you were looking inside of Niagara Falls.
One of the capital's most historic streets was on the brink of destruction.
Once a road started to go, nothing was going to stop it.
Ottawa, Canada, established on the banks of the Ottawa River, was a remote logging town before being hoisted to fame as the nation's capital in 1867. Stefan Keys is a local news anchor.
Ottawa has really come into its own from small lumber town to a city of 1 million people. Federal buildings and public servants and high tech, and we're really also very much an academic city as well.
A thriving capital city needs public transportation to match. But until 20 years ago, Ottawans depended almost exclusively on buses.
So there are actually lanes just dedicated to buses and roads dedicated just to the bus system. But it made the roads very congested.
In 2012, construction began on the new Confederation Line, an all-electric light railroad running east to west.
It was huge for the city. It was a game changer. We felt like we'd finally be like a Toronto or a London. We weren't just going to be this little small town that everyone forgets about.
For much of its length, the line would run on the old bus route, but in downtown, it would go underground.
So they dug very deep below ground, and it was going to go from east to west to start and open up in phases.
Large stretches of the tunnel were bored through solid limestone. But beneath Rideau Street, one of Ottawa's most historic roads, the ground was much softer. Kamal Hussain is an assistant professor of engineering.
Ottawa is built on soft ground. It's also called quick clay or Leda clay. So it's basically very unstable foundation material, and you don't know how far you will go to get a bedrock.
Normal clay is very sticky and holds together very well, but quick clay is much weaker and unstable. It can easily liquefy when wet, and is famous for causing landslides in countries from Norway and Russia to Canada.
Here, the clay filled a hidden underground valley and was a major headache for tunnelling.
Because the ground was so soft, engineers used a special technique to stabilise the tunnel walls. Essentially, they surrounded the earth they wanted to dig out with steel rods or pipes to help support the roof. It's known as a pipe umbrella.
Steel rods or pipes are driven forward into the soil around the intended tunnel section, like a long tunnel-shaped umbrella, working like a kind of skeleton to help support the roof when the material is removed. Despite the soft ground, by summer of 2016, work was well underway. Jeff Elliott's office was nearby.
This was going to be the first light rail transit underground train system in Ottawa, so people were excited about it. It was a big thing for the city.
On June the 8th, tunnelling was approaching the new station when Jeff got a surprise.
The power went out in the building, so I knew something was going on. So I grabbed my phone and went up to the rooftop. You could see from this area down here, the road was just gone.
The huge sinkhole was destroying Rideau Street.
The sinkhole immediately started to swell with water. I was in shock. I was in awe.
It was massive. Lots of water rushing through. It started right about here and then progressed down and eventually went right across to the other side of the street, where it ended up sucking in some of the light posts that were here.
The growing hole swallowed a minivan, slicing Rideau Street in two.
The hole didn't just take down the road, it broke water pipes and electricity cables, as well as rupturing the gas main, which risked triggering an explosion. So nearby buildings had to be evacuated.
All the buses that were usually going down here had to be rerouted to another street. And then in addition to that, the intersection behind us here was also blocked off, so anybody trying to come down through the main core here had to find alternate routes.
Ottawa and its light rail project were in chaos.
Everyone was looking forward to this. It had been a long time coming, but before we even had a chance to see what the train would look like, then there's this major engineering question mark. This was big for the city.
People were shocked. They wanted to know what was going on in the middle of downtown Ottawa, how something like this could happen.
The first suspect was the gushing water main, but investigators ruled that out as the result of the collapse, not the cause. It seems the problem was the clay-filled valley, which was saturated with groundwater and weaker than expected. Engineer Kamal Hussain explains.
I'm demonstrating how water can destabilize different type of soil. So I'm pouring water into the soil sample. You can see how this sand cone is spreading all over the ball and it became destabilized. With the rain and surface runoff, the water can erode that soft soil. That erosion creates gaps. This gap can eventually turn into sinkhole.
Although the pipe umbrella system helped stabilise the ground, it just wasn't enough to prevent the saturated quick clay from slipping between the rods into the tunnel below. That opened up a massive void beneath the road, and the rest is history.
The dramatic collapse occurred on June the 8th, but with Canada Day just 3 weeks off, the road had to be fixed and fast.
Luckily, no one was really injured in that incident. They drained all the water out the best they could, and they just started filling it. They started filling it with asphalt, piling on, then cement on top.
The minivan couldn't be salvaged, so it was left inside the crater, while workers filled the hole with concrete and reconstructed the road above. Finally, in September 2019, 3 years after the disaster, Rideau Station opened to passengers, and Ottawa was fully on the move once more.
It was like Ottawa residents were winning the lottery. They couldn't wait to hop on this thing and ride it.
In big engineering, careful maintenance can be just as crucial as construction, because sometimes lurking within, a minor problem can become a major catastrophe. Like this bridge in the UK, a historic crossing in danger of imminent collapse.
The impact was absolutely tremendous. It was devastating.
Potential disaster lying hidden in plain sight.
Corrosion had gone unchecked for decades, putting the entire structure at serious risk.
One of London's most famous bridges could have fallen down.
The city couldn't take any chances. They had to shut it down fast.
London, England's capital, was founded as a small town back in Roman times and expanded along the banks of the River Thames, which is the beating heart of the city.
Some of London's most historic buildings are situated on or around the River Thames, not least the 35 bridges that cross it, some amongst the most famous in the world.
And one of London's most eye-catching, lying around 10 kilometres west of downtown, is this, the Hammersmith Bridge.
Morning, Captain.
As Keith Whitehouse, chair of the local Historical Society, explains, when it opened, it caused quite the stir.
Hammersmith Bridge was built in 1887. It was the first suspension bridge on the Thames, and when it opened, there was hordes of people turned up, royalty, dignitaries, to make a big splash of it.
Not only is this bridge unique in London, it's the only one of its kind in the whole of the UK.
The bridge is more than 200 metres long, with ornate iron towers sitting on concrete piers below. But what really made it stand out from the bridge crowd was that it was all connected with these massive eye bars.
Here, instead of cables, a series of eye bars were used as the main supporting elements, essentially like a giant bicycle chain attached to the large cast iron pedestals that hold the whole structure in place.
This historic crossing is aptly known as an eye-bar suspension bridge, with each end of the eye-bar chain sitting on roller bearings at the pedestals.
The steel roller bearings allow the bridge to move horizontally under heavy loads, reducing the stresses on the towers.
For more than a century, it's been a big hit with Londoners like local resident Jane Bain.
It's so iconic. I love the bridge. I think it's wonderful. I can't imagine not waking up every morning and looking out of the window and seeing the bridge there. It's just magical.
But while the bridge may be magical, a problem lying hidden inside put it in danger of disappearing forever. After more than 130 years of standing proud over the Thames, Hammersmith Bridge was struggling to cope with the rigours of modern life.
The bridge was originally designed for horse and carts, so even far-sighted engineers couldn't have predicted that it would have to cope with over 20,000 vehicles a day.
Council was due to repair it, but they did a much more thorough structural survey using modern technology. They discovered there were some cracks in the pedestal, so for safety reasons they decided to close it to traffic.
While still open to pedestrians, around a year later, a much bigger problem was found that could have closed the bridge for good. New sensors inside the bridge alerted engineers to a rapid and sudden increase in the size of the cracks in the cast iron pedestals that were essential to the integrity of the entire bridge.
Engineers believed there was a clear and present danger to pedestrians and cyclists, and immediately closed the bridge.
At 5 p.m. on August the 13th, 2020, without warning, the 133-year-old bridge was completely shut down.
There were people that had come across the river and couldn't get back home again.
Rush hour commuters were stranded and tempers were rising.
There was nearly a riot on this side of the river. Hammersmith had to send marshals out saying to people, look, I'm sorry, but you can't cross.
With around 16,000 pedestrians walking across and hundreds of boats travelling under this bridge every day, authorities weren't about to take any chances.
While there's no way of knowing for sure, local politicians believe that by closing it down, they averted a potential catastrophe in the capital city.
Some believe the cracks may have been caused by a process known as dynamic loading. Professor of Engineering Armawadi explains.
The dynamic load arises from the repetitive loading of the traffic. A lorry comes over the bridge, you have a high stress in certain regions, it leaves the bridge, and then suddenly the load is completely changed. And so you have a lower stress in a particular part of the bridge. Over time, this loading repeats, and so the stresses on the bridge go higher, they go lower, they go higher and lower, and so on. But over time can actually cause fatigue cracks to open up.
An inspection found that the bridge was also suffering from corrosion that had been ongoing for nearly 7 decades. The roller bearings, vital to the bridge's flexibility, had corroded and seized up, meaning the bridge was having to cope with much more force than it was ever designed for, causing cracks in the pedestals known as microfractures.
Microfractures can indeed be catastrophic. If the cracks open up and cause fracture of the local abutment, then this may change quite considerably the way that the forces and stresses are transferred from the deck to the foundation. And this may compromise other parts of the bridge which may not have been compromised initially.
And with cast iron, cracking can be a serious problem.
Cast iron is brittle and can shatter, so although these fractures were tiny, there was a serious concern that the bridge could collapse into the River Thames.
A government task force was set up to find a solution for this historic crossing. Still in the early stages, the long-term plan is to fully restore, repair and reopen the bridge to both pedestrians and traffic by 2027. Just 11 months after first closing, it was declared safe enough for pedestrians and cyclists.
When the bridge reopened, it was absolutely magical. I was just so happy. Went up there, and it was so nice. Such a happy day.
While it won't be cheap, with some estimates topping £100 million, many think it's well worth the effort.
As well as preserving this treasured bridge for generations to come, ultimately this is about safety, no matter how long it takes. And as engineers often say, the devil is always in the detail.
In Sweden, tragedy strikes as a landmark bridge is destroyed in seconds.
They were just standing there witnessing the entire thing unfold.
A massive construction disaster at a New Jersey casino.
When it popped off, bam, it hit the next floor. And bam, the next floor. And bam, the next floor.
In California, a catastrophic dam failure rips through a community.
It just opens up and the water just gives way with all of its force.
And in Chicago, a pioneering skyscraper hits unexpected turbulence.
The engineers said, Houston, we've got a problem.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Engineers are constantly creating bolder structures through innovative designs. While they might look stunning from the outside, sometimes a weakness can be lurking within. Like this disaster in Sweden, the catastrophic collapse of a vital crossing.
Such a large ship, it just caused the entire bridge to collapse.
Devastating destruction in the dead of the night.
Drivers had no idea that the bridge was down.
An event that ripped through the heart of an island community.
There were so many things that went wrong. It was a tragedy.
Sweden, its rocky coastline boasts more islands than any other country on Earth. The nation's access to water is key to its success.
For hundreds of years, the Swedes were a maritime powerhouse, trading all over the world. Today, they still export everything from cars to petroleum to flat-pack furniture, a lot of it by sea.
The nation's west coast borders the North Sea. From there, ships gain easy entry to the Atlantic Ocean and major shipping routes. Journalist Ruben Dieleman knows these challenging waters well.
This is the west coast of Sweden, which is a very rugged terrain. During wintertime, it can be extremely icy, cold, foggy as well. And that makes it all the harder for ships to pass through these narrow passages.
Ships aren't the only vital traffic. People and businesses also rely on a network of bridges. Like this one on the island of Tjörn, the only road connecting it to the mainland.
There are about 30,000 people who live on this island and who are very much dependent on the mainland. So this is their lifeline, I would almost say.
But this isn't the first crossing here. Its predecessor, completed in June 1960 and known as the Alma, was revolutionary.
Sweden has a long history of engineering. At the time of construction, this was the longest arch bridge in the world.
With an almost 300-meter main span, the bridge's steel tube structure relied on an ancient design feature, the arch. Mario Ploss is a professor of structural engineering.
The Alma Bridge is strong, and it's also effective in the sense that the vertical loads from the self-weight and the traffic are transferred to the support of the arches through the shape of the arch, so that it only gets normal forces along the arch that carries the whole weight of the entire bridge.
For nearly 20 years, the bridge stood out as a symbol of Sweden's success. But this eye-catching crossing was on a collision course with disaster. January 18th, 1980. In the early hours of the morning, the cargo ship MS Star Clipper was traveling north towards the Alma Bridge.
It was a very cold, very icy, dark, and foggy night. You couldn't see a thing, basically.
Maneuvering under the bridge can be tricky in normal conditions, but here, ice had built up all around the ship.
To safely sail under the arch, the 33.5-meter tall vessel needed to turn sharply to port, lining up with the center of the shipping channel.
Such a large ship underneath a relatively small bridge through a narrow passage on top of those weather conditions was very, very difficult to navigate.
At 1:30 a.m., disaster struck.
Instead of steering for the center of the bridge, it steered for the island side and crashed straight into the arch that held the bridge up.
The force of the impact was so huge that the main span came crashing down almost instantly onto the ship and into the water.
The crash knocked out the ship's radio, so no warning could be sent.
In the ice and fog, the approaching vehicles had no idea that the bridge was gone.
In the confusion, it was 40 minutes before the authorities closed the road. Meanwhile, local resident Rita Cordenius was waiting up for her husband.
I was at home looking after my daughter, and I stayed awake because I was thinking this is strange, this is not normal. And then I listened to the radio. And then I could feel, oh, that's why he is not coming.
7 vehicles had fallen from the bridge, and tragically, all 8 people who fell with them lost their lives. Sadly, Rita's husband was among them.
It took so long time before they could stop the people. Too late. I prayed and hope I can get through this. And I did.
With the community cut off and the nation in mourning, the Swedish government launched an immediate inquiry.
It was a major disaster, a pretty impactful event for the entire region, because their entire lifeline, their vital connection to the mainland was cut off.
It was pretty obvious what had happened. The big question was why the impact caused such a catastrophic collapse.
It was clear that bad weather was a key factor. But the report highlighted potential weaknesses in the structure itself. Professor of Engineering Mario Kloss explains.
The big mistake with this bridge was that it was not designed for being hit by a big ship. There was no protection against it, and the bridge was not designed to withstand it.
This is a fatal flaw with any arch design.
So an arch bridge like this is very good in carrying its vertical loads, but it's rather sensitive for a side impact, particularly a bridge like this that consists of a steel tube, because suddenly it becomes much weaker than it was before.
Think of this steel like an empty can of soda. If you try to crush it from the top, it's pretty difficult. But when you apply just a little pressure from the side, there's very little resistance.
Now, imagine a 16,000-ton ship hitting that can from the side on. It's going to do a lot of damage.
The impact in one area was enough to buckle the steel tube, undermining the strength of the entire bridge.
You can compare it with a chain. So if you break one link in the chain, then the chain won't work anymore. It's the same with the arch. If you remove one part or destroy one part of the arch, then the arch doesn't work anymore, and then the whole arch goes down.
It was also discovered that the steel arches were lacking what's known as stiffeners. Steel plates riveted within the hollow tubes to give the arches extra horizontal strength.
So inside the steel tubes where the loads came down, there were some stiffening plates, but in the longitudinal direction along the arch, there were no such plates inside the tube section. And this made the tube more vulnerable for side loads.
While stiffeners would have made steel tubes stronger, ultimately being struck by a ship of that size would probably have brought the bridge crashing down anyway.
This vulnerability, combined with bad weather and bad luck, triggered one of the worst disasters in Sweden's history. In the immediate aftermath, the community was left reeling and isolated.
With the bridge destroyed, thousands of islanders' lifeline to the mainland have been cut off.
Suddenly was no bridge there, and you had to go by ferry with long queues every day.
A new, stronger, safer bridge needed to be constructed fast. Designed to be higher and longer than its predecessor, the new crossing also needed to bolster itself against ship impacts.
The solution was both ingenious and simple. They eliminated the risk of collision by making sure there was nothing in the water to ever crash into again.
The new bridge opened on November the 9th, 1981, just 17 months after the disaster. And the islanders' lives were once again on the move. While the footings of the original bridge remain as a memorial to that tragic winter's night.
Even though it's 40 years ago, it's still very much embedded in local people's memory, and these footings serve as a reminder for future generations as well.
In engineering, every last detail must be checked and double-checked. If just one thing slips through the cracks, the results can be catastrophic. Like this disaster in New Jersey, a gambling hotspot where the house came crashing down.
Massive decks made out of thick, strong concrete collapsed like horizontal dominoes.
Sudden destruction on an epic scale.
The columns were like a popsicle stick that had been wiped clean.
Engineering errors with catastrophic consequences.
It went in a second. Boom, boom, boom. It was chaos.
Atlantic City, New Jersey, a legendary town known for its beaches, boardwalk, and gambling. Joe Walnut is a former casino reporter.
We're on the world-famous boardwalk in Atlantic City. The first casino opened in 1978, and it was a godsend for the city. And millions of people have been coming here to walk the boardwalk, swim in the ocean, visit the grand hotels.
In 2002, with competition becoming fierce, one of the oldest casinos on the boardwalk decided to up its game.
Two Las Vegas Strip casino giants decided they were going to build a $1 billion casino resort over in the Marina District of Atlantic City. Understandably, other casino operators said we have to protect ourselves because if you don't keep up, you get left behind pretty quickly. Tropicana committed $245 million to expanding their property considerably.
The plan would rival the huge mega resorts in Vegas. It included a 500-room tower, entertainment complex, and a 10-story parking garage with more than 2,000 spaces.
To speed up construction on the garage, each of the 10 stories would be created off-site as large reinforced concrete slabs just over 6 centimeters thick. Once at the construction site, each story was attached to concrete columns, creating a thin foundation for each level. Temporary steel props, known as shoring, would support the slabs, while concrete was poured above, creating a thicker, stronger 25-centimeter thick floor. When it comes to gambling, time is money. But in engineering, safety must always come first. Early morning on October the 30th, 2003. Construction workers were pouring the concrete on the 8th floor of the parking garage.
The pressure was on, the job was running behind due to bad winter weather, and the deadline was fast approaching.
Just 3 hours later, at 10:40 a.m., disaster struck. Former casino reporter Joe Walnut was in the newsroom when word of the catastrophe came in.
We got notice from one of the editors that the Tropicana garage had collapsed.
While still under construction, the top 5 levels had failed suddenly and without warning.
What I saw was something that you never expect to see in life. Just these massive parking garage decks, thick, strong concrete, collapse like horizontal dominoes.
The devastation was huge. Tons of freshly poured concrete slid down over collapsing slabs, through stairwells and an elevator shaft.
Construction accident attorney Bob Mongaluzzi also witnessed the devastation.
When I got down here, this was cordoned off, multiple blocks in every direction. These slabs had literally collapsed off of the columns.
Fire and rescue teams were desperately searching for survivors among tons of twisted steel and concrete.
It was chaos. There were firemen, policemen, ambulances, helicopters.
I've never seen so many flashing lights or first responders in my life.
You knew instantly that this was a catastrophic event. There was going to be a lot of guys working that pour, and my heart sank.
Despite rescue crews' tireless efforts, 21 workers were injured in the disaster. And tragically, 4 lost their lives.
There was no warning that day. It went in a second. For those who survived in floors below, they talk about how they heard this cracking and crash and then looked up and then just saw the entire floor, like the sky, falling down.
The catastrophe left the city reeling.
This was the worst construction disaster since casinos came to Atlantic City. People wanted to know just what had gone wrong.
These were all local men. You know, people were shaken by this, and it was devastating.
Principal engineer David Peraza was brought in to investigate the disaster.
They were about halfway through when all of a sudden P8 and 5 more levels under it collapsed, and the slabs fell like a trap door opening up.
For investigators, the evidence was clear. A key element was missing.
There were no reinforcement bars connecting columns to the slabs. It was as if the columns were like a popsicle stick that had been, wiped clean. No clear connection.
Under building code regulations, steel reinforcement bars should have run through the floor slab, all the way into the supporting column's core. A connection vital for securing the parking levels into place. But here, they were missing.
In effect, it staples the concrete together. The fact that there wasn't any reinforcing steel attaching the slabs to the columns meant that they were vulnerable to separating from the columns.
Further investigation revealed there had been a change to the original plans.
Picture on the left here, this represents what the original design was. So you see that you have a column that is 2 feet wide, and framing into it is a beam that is 2 feet wide, so that all of the reinforcing bars that were in the beam were forced to go right through the column automatically.
However, on the amended design, the dimensions were changed, meaning the reinforcing steel was no longer automatically connected to the columns.
The column is now only 1 foot wide, and then you've got a wide beam that has 8 or 10 bars in it, but they're not going through the column.
This new design meant that no reinforcement bars went into the column from any direction.
Basically, you had this concrete slab just sitting like this, overlapping onto the column. When they're pouring hundreds of thousands of pounds of concrete, that concrete starts to flex and it just popped that off. And when it popped off, bam, it hit the next floor, and bam, the next floor, and bam, the next floor.
There were also reports of a problem with the metal poles or shoring, used to hold up the floors while the concrete was drying.
Each floor supports the one above as the building grows taller. Crucially, the concrete below has to fully cure before it is strong enough to take the load from above.
The investigation found that shoring on the lower levels had been removed before the concrete above was fully stable.
What they found was that these poles were bending. Normally, they have a little thing at the top, like a wing nut. You hit it like that, and then you could loosen it and pull it out. Here, the pressure was so intense they couldn't do it. They were taking sledgehammers to knock it out.
With the structure already compromised lower down, pouring concrete for the 8th floor proved too much, and the whole garage collapsed.
Here, it seems there was a combination of factors, from errors in the steel reinforcement to insufficient shoring, that ultimately led to the collapse.
The disaster hadn't just destroyed a parking garage, it had destroyed lives.
There's always going to be pressure to bring projects in on time and within budget. But whatever setbacks there are along the way, health and safety always has to come first.
With lessons learned, construction resumed. And in November 2004, a year after the tragedy, the project was finally complete.
To have something like this happen was just out of the blue, and hopefully it's something we'll never see again.
You know, Atlantic City is really a small town, and there's not a person in this city that wasn't affected by this collapse. Everybody, and it still reverberates today.
I think ultimately it's a story of Atlantic City's resilience. This was a black eye for the city, but it overcame that and it continued to prosper.
In engineering, where we build is just as important as how we do it. Get either wrong, and catastrophe is inevitable. Like this disaster in California that devastated a community.
They had gone past the point of no return. You can't stop it.
A fault that brought a dam to its knees.
It just kind of opens up and the water just gives way with all of its force.
Once it sprung a leak, things were only going one way, down.
Los Angeles, California. For more than a century, its stunning climate and landscapes have drawn more than just filmmakers. Today, Greater LA is home to almost 20 million people. Conservationist David McNeil is a lifelong resident.
People ask me what is quintessential Los Angeles, and sure, we have movie studios, we have Hollywood, we have the beaches, we have the mountains. We reinvent ourselves all the time, and that's the unique thing about it. You see buildings get torn down and new buildings go up. You see history get erased and new history created.
LA is the second largest city in America, but it's essentially built on a desert. And with an ever-growing population, there's always been a massive demand for water.
The climate zone for Los Angeles is arid, and everything that you see that's green is kind of brought in or irrigated.
LA's growing thirst for water outstripped supply more than 100 years ago, with the city long depending on aqueducts and dams.
The infrastructure, dams, in Los Angeles in particular, are the one water source essential for everyone's turning on their water and having running water in their homes.
In the 1940s, the hunt was on for a new dam site within the city of LA, but planners were short on options. Engineering professor Jonathan Stewart explains.
If you look at a map of the city of Los Angeles, there's a very large basin. It's called the LA Basin. It's mostly flat. And flat's not all that great if you're managing a water system.
Reservoirs work best when they're higher than the area they're built to supply, so gravity pushes the water to people's homes. In the flat LA Basin, choices are limited, but there was one clear contender, the Baldwin Hills.
Baldwin Hills, this uplifted geological unit right in the middle of the LA Basin, is the perfect site for a dam and a reservoir because it's on top of a hill.
Completed in 1951, the more than 7-hectare hilltop reservoir was contained on 3 sides by compacted earth dikes, with a 70-meter high dam sealing a 200-meter wide ravine on the north face.
This reservoir would be good news for water supply, but the flip side was that around 1,600 people would be living downstream of the dam. So in a state known for fault lines and earthquakes, engineers really had their work cut out.
The engineers who designed Baldwin Hills Reservoir knew that the faults were here. They also knew that the geologic strata that would be underneath the reservoir was very poorly suited to retaining water in this space because it's sand and silty sand.
Building on erodible, potentially shaky ground was hardly ideal. But the need for water was so strong that engineers came up with an ingenious solution. Beneath the entire structure, they installed a 6mm thick layer of asphalt reinforced with cotton.
This asphalt layer was designed to flex with the movements from the faults below, while keeping the reservoir watertight, preventing erosion of the soft ground.
The 1/4 inch asphalt layer is really a vital part of this liner, because that's the last line of defense, keeping the water from the reservoir out of the foundation.
The dam provided LA with fresh water for over a decade, but in 1963, just before Christmas, tragedy struck. December the 14th, 11:15 a.m. A routine inspection revealed a problem.
The watchman was inspecting the dam and he noticed something early in the morning. And then he notified the appropriate people.
A small crack had opened up in the dam wall and water was escaping.
We had a fissure that began to open in the abutment here on the east side of the old dam. It's just a small crack.
The crack might only have been small, but with a dam like this, any crack was very bad news.
A news helicopter soon arrived, beaming out the first ever live aerial footage of any breaking story.
Right here now, as we come up over the Baldwin Hills Reservoir, we can see the main break in the reservoir itself.
Engineers on site knew that you can't stop it. They had gone past the point of no return.
Draining the reservoir would take 24 hours, so authorities ordered an evacuation of everyone downstream.
Basically, you got people up who, if they weren't already out shopping or doing their thing, hey, pack your stuff up, get your belongings, get your dogs, get the heck out of Dodge.
As residents fled, the condition of the dam was worsening.
The hole has opened up from what it looked like about 6 feet tall, 2 feet across, to this hole that's 40 or there goes a large chunk of the inner cement here in the Baldwin Hills Reservoir.
The size of the flow grew rapidly to the point that a chasm opened up in that crack.
You see the whole thing collapse and just kind of opens up, and the walls burst open and the water just gives way with all of its force.
More than 1 billion litres emptied in just 90 minutes. 65 homes were destroyed and hundreds of others damaged.
The water rushed out, devastating homes all along the way. Bicycles, cars, televisions, whatever was going down there was just rushing down the Walnut Creek.
Despite the quick actions of engineers and the mass evacuation, tragically, 5 people lost their lives.
I only could imagine the kind of memories that were washed away, people's personal possessions coming home and just seeing the devastation and thinking, my God, I've got to start again.
Angelenos demanded to know what had caused the disaster.
Investigators knew where the cracks had started. The question was what had caused them in the first place.
There had been no earthquake, and the dam's liner was designed to cope with the soft ground.
Investigation showed that the ground below had moved more than predicted during its 12-year lifespan for entirely unexpected reasons.
Baldwin Hills has got a long history of oil. Los Angeles is built on oil. I mean, the reason this city boomed the way it did was because of the oil.
But extracting this commodity came at a price.
The extraction of the oil and gas, starting in about 1917, caused regional subsidence, meaning it settled by about 9 feet from about 1917 to the time of the failure here in 1963.
These days, the potential for oil and gas extraction to trigger serious ground movement is well known. But when this dam was built, engineers didn't understand how bad it could be.
The excessive settling had cracked the concrete and split the flexible liner, allowing leaking water to erode the earthen embankment.
Once that particle is gone, that soil is a little bit more open in its structure, which means the water can go a little bit faster, and it's going to be a little bit easier to pick up the next particle, and the next one, and the next one, such that once you pick up the first one, you start a cascading series of events that you're going to erode the soil in the foundation.
Once the foundation was compromised, the dam was doomed.
The tragic events of that day left the city facing a tough decision, whether or not to rebuild the dam.
The failure was a disaster. It killed people, it traumatized the community. To go back and rebuild something in the same spot would not have been very popular.
Not only was a rebuild unpopular, it wasn't even an option.
They realized that their assumptions about the stability of the faults here was not correct. And from the technology they had at that time, they genuinely did not believe that they could safely build a reservoir here again.
With the city's water needs met by other dams, in the true LA spirit of reinvention, the Baldwin Reservoir was torn down and the site was repurposed for recreation.
This was just an abandoned old site, empty, really deep, pretty much dangerous location. It's been filled in with grass, trees, sycamores, and oaks. Now we have this wonderful park.
Engineers are constantly striving to build stronger and taller structures. But pushing the envelope comes with big risks. Like this epic project in Illinois, a trailblazing tower that was heading for trouble.
The engineers said, Houston, we've got a problem.
A problem that threatened to rock the residents.
The turbulence is very high and the wind's all very mixed up.
And a solution that had engineers thinking outside the box.
So what could have been a penthouse that would have easily gone for $10 million is nothing but air.
Chicago, Illinois, now a thriving commercial and cultural hub. It has its roots in good old-fashioned hard work and was dubbed by one poet as the city of the big shoulders. Journalist Blair Kamin specializes in architecture.
Chicago's part of the middle of America, and it has its own distinctly Midwestern character. It's pragmatic, it's tough, and yet it has a tough beauty, especially in its skyline.
Chicago is famous for its skyscrapers, but it's not just about being the tallest. Each one was intended to stand out from the crowd, its own unique masterpiece of architecture.
Structural engineer Dr. Shankar Nair has worked on the city's skyline for 5 decades.
We have a very distinctive skyline. It's quite unlike any other skyline in the world. Chicago is known for very masculine buildings, after all. Sandburg called it the city of broad shoulders, and that is reflected in our architecture.
In this tough city, big engineering shines through.
The engineering in our buildings is very prominent. The most obvious example is the one we're going over right now, John Hancock. You just look at it and you know how it works. You see those big X's on the outside, and that is what holds the building stable. It looks strong, and it is strong.
From the late 1960s, Chicago's bold, straight-edged skyscrapers climbed ever higher. But in 2016, a new tower started to take shape that was designed to break that mold. Looming 101 stories over the lake shore, this super-tall, curving structure boasts epic views from the lake to the city and beyond.
It's very different from the tough, muscular, structurally expressive buildings of Chicago's past. It's more about fluidity.
As you can see, this is 3 separate towers, increasing in height as you go from east to west. The tallest one is on the west, and each of those towers has an undulating shape. The organizing principle for the shape is that these undulations constitute frustums of a pyramid.
A frustum is a pyramid with the top chopped off. There's one on the back of every US dollar bill, to the left of the word one.
These towers are made up of alternating upright and inverted frustums, creating a zigzag outline, but proportioned so that the building looks to undulate.
It's really an illusion. The glass is not curving, the columns are not curving, but it has that fool the eye. And it's magnified by the fact that these stacks create these beautiful reflections and geometric interplay, and that makes it a very unique skyscraper in Chicago.
The elegant tower isn't just designed to look good from the outside.
If you're buying a home in a skyscraper, it's all about a great view from all over the apartment. So the narrower the tower, the better. But narrower also makes the building more vulnerable to the forces of nature, particularly the wind.
The architects were one step ahead. Although the 3 towers look to be aligned, each is slightly offset from the next, spreading the tower's footprint like the trunk of a tree, with a concrete spine locking everything in place. This stabilizing trick allowed the West Tower, although super skinny, to become the 3rd tallest skyscraper in Chicago. From day one, plans were under constant scrutiny, like all modern skyscrapers, that included wind tunnel testing.
The engineering of tall buildings is art and science, and testing a design in wind tunnels is crucial.
Peter Burke is a wind engineer.
There's no practical way of subjecting a building to its peak wind loads at full scale. The only way we can do that is in a scaled model experiment. We need to simulate the air moving over that object, and that air is not smooth at all. It's actually highly turbulent. The turbulence and the wind speed are both varying based on the altitude above the ground. So this is a very complicated environment.
In 2017, with construction still at ground level, testing flagged some unexpected problems.
In the middle of the engineering process, the engineers said, Houston, we've got a problem. If this tower is built exactly as it was designed, we're going to have swing and oscillation and units that are not marketable.
The obvious question, were the city's infamous winds to blame?
Chicago is known as the Windy City, but in reality, it's no windier than most other places. That nickname came from a reputation for boasting, being windy about what an amazing city it was.
Chicago is not a particularly windy city, not in meteorological terms. The design speed for which we design buildings here is substantially lower than the speed in New York, Boston, and many other cities.
The problem here was simple: the tower's extremely slim design.
When air or wind flow interacts with a tall, slim building, the wind has to move around the building. What happens when it does that is it often sheds off the building's corners or edges. There's also a strong wake behind the building, and the turbulence is very high and the wind's all very mixed up. Those two things both interact with the building, causing the building to sway back and forth in strong winds.
In reality, most skyscrapers sway. The big question is how much.
In most cases, occupants of a building never feel its motion. The motion's there, but they don't feel it. But if the accelerations of the building were too high, then they could feel it, and that's very undesirable.
The tallest one, the one that goes all the way up to 101 stories, is very skinny compared to Chicago's other towers. So that means it's much more like a reed that can kind of blow around in that high wind up there.
When the news came out, the Chicago Department of Planning and Development was reported as saying internationally accepted limits would be exceeded, with people feeling ill and possibly afraid for their safety.
If there's too much wind sway, particularly at the upper levels, people can feel almost seasick. Chandeliers can rattle, there can be whitecaps in the toilets, and if you're paying millions of dollars for a condominium penthouse, that's not what you want.
Something had to be done, and in typical Chicago fashion, the solution was bold.
So what they did was, on the 83rd floor, they decided to leave the floor empty. Where, normally you could sell a condominium for about $10 million, but it's empty because that lets the wind blow through the tower.
Around 300 meters above the ground, 2 floors of the tower don't have any windows, just vertical grates surrounding them. It's known as a blow-through floor.
What that does is it lets the pressure from the front and the back equalize a little bit better over that section of the building, and a jet of air to blow through, and that helps break up that turbulence.
Instead of pounding like that against the building, which would make it sway, the wind could just go right through. That would reduce the amount of sway, and then it would make all the other condominium spaces in the building marketable. So it's giving up a little to make a lot.
Adding the blow-through floor seems like a radical idea, but it had radical results too, reducing the problems from the crosswinds by about 25%.
Yet, calculations revealed the blow-through floor alone wouldn't be enough to steady the sway.
There's another engineering trick in this building called the Tune Liquid Sloshing Damper. And there are 6 of them. And what these things are giant pools with tens of thousands of gallons of water. When the wind blows the building one way, the water sloshes in the opposite direction. And that creates an equilibrium. It balances the building.
Nearly all designs evolve along this way. That's nothing new. But if this hadn't been fixed, it would have been a financial disaster.
In 2020, the new tower, with its sway significantly reduced, was finally completed.
With all the testing that happens these days, the swaying would have been spotted long before it became a real problem. But it's still a good reminder that unique designs will always come with unique challenges.
It's still a very beautiful tower, one that's very unique, and that really adds something to a storied and celebrated skyline.
In Ohio, tragedy strikes one of America's busiest highways.
I could see a big slab of concrete, but it still really had no idea what exactly happened.
In California, a catastrophic dam collapse causes a tsunami of destruction.
If you had been standing here when the dam failed, you would have been washed away.
In Italy, a vital bridge comes crashing down.
The entire bridge toppled like a line of dominoes.
And in Massachusetts, the world's tallest academic library starts cracking at the seams.
When you have something of that scope and something like this happens, people are going to say, what are we going to do about this?
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. In every step of big engineering, from design to construction, the devil is in the detail. The same is true when it's time to bring things down. Like this catastrophe in Ohio, as highway disaster strikes in the middle of the night.
While the bridge actually did fall, it's sitting on the highway. It's not something, even in a lifetime, you might expect to see.
A routine demolition that went tragically wrong.
Deconstruction is possibly the most delicate phase. You need to be careful because you may take the whole thing down.
And caused chaos on one of the nation's busiest highways.
It was a catastrophic pancake collapse. This had an effect on a lot of people for a very long time.
Cincinnati, Ohio is a melting pot. A mix of East Coast, Midwest, and the South. But the crossroads isn't just cultural.
Some of America's most important trucking routes pass through Cincinnati. With around $400 billion of freight crossing the river here every year, a lot of it on one of the nation's busiest highways, Interstate 75.
Bill Reinhardt is a local reporter.
I-75 stretches from Michigan all the way down to Florida, from Detroit to the Gulf of Mexico. It passes through Cincinnati, it passes through Atlanta. 3% of the annual gross domestic product of this country traveling north on 4 lanes and southbound on 4 lanes. That's not a lot of space for a lot of gross domestic product.
In 2010, work began on an infrastructure project to widen and modernize a nearly 30-kilometer stretch of the I-75, including vital overpasses like this one, the Hopple Street Interchange. A local police officer for nearly 20 years, Don Whirling, explains.
The Hopple Street I-75 connection right here is the main artery that takes you up to the University of Cincinnati, all of our major hospitals. So it kind of connects east and west, and it connects a lot of people coming from the suburbs, coming from Kentucky, coming from downtown. So the Hopple Street overpass is very, very important.
But this isn't the first overpass at this location. It was built to replace this shorter, narrower bridge constructed in 1961.
The overpass needed to be widened. At the same time, the interstate also needed to be widened to accommodate growing flows of traffic. So what they did was got rid of the old overpass and built a new one, and then simplified the on and off ramp.
The old bridge might look very basic, but the structure relied on a careful balance of forces.
The old Hopple Street Bridge was built in 3 sections. A 12-meter west span and a 14-meter east span, each projecting nearly 3 meters over the roadway. Balanced or cantilevered over the columns, the 2 ledges supported the longer center span, creating a 28-meter wide gap for traffic. With balance being key to the bridge's structural integrity, demolition was far from simple. Associate Professor of Engineering, G.A. Rosati, explains.
The deconstruction phase or the demolition phase is probably the most dangerous phase in the life of a structure because you're taking away parts that contribute to the stability of the structure. When you come to the bridge, you start removing the deck. You need to be careful with that.
Monday, January the 19th, 2015. The demolition crew was on the second night of the job.
The idea was to remove the concrete from the east span, then continue all the way across before removing the steel structure. That way, the road below could be kept open for as long as possible.
An excavator with mechanical jaws had chewed the concrete from the east span and was working its way towards the middle of the bridge.
Around 10:30 p.m., disaster struck. Captured on grainy CCTV, the entire center span suddenly collapsed.
The Hopple Street Bridge just collapsed over 75. We're going to need heavy rescue, and we're also going to need to shut down 75 South.
Police officer Don Whirling was working the night shift when the call came through.
My boss calls us and he tells us that we need to gear up, that the bridge fell. So we got our gear together and we headed out there.
What should have been a routine demolition was now a major disaster.
We need to stop the traffic. Don't let the traffic come off that ramp. How many injured people do you have down there?
Tons of concrete fell around 6 meters. An excavator, its operator, and foreman all went down with the bridge.
I don't think your mind can actually grasp it until you see it. It's not something, even in a lifetime, you might expect to see.
As word spread about the catastrophic collapse, reporters like Bill Reinhardt rushed to the scene.
I could see a big slab of concrete with an excavator on top of it, but it still really had no idea what exactly happened.
It was a close call for traffic, with one truck driver crashing into the debris.
One semi slammed into it. That driver had some minor injuries. He was treated and released. That was it.
Not everyone was so lucky, although the excavator operator survived the fall. Tragically, the foreman died in the devastation. But with the road open at the time, the injuries and death toll could have been much higher.
On the camera, we can see cars actually going under the bridge. By some miracle, there's a break in traffic, the bridge collapses. There could have been a dozen cars underneath of it when it came down.
While the city was in shock, one of the busiest highways in the country was at a standstill.
I-75 southbound is a major artery, and to cut it off at any point interrupts a lot of traffic and a lot of commerce. Traffic was kind of a mess. People had to find other ways to get where they were going.
Residents and travelers alike wanted to know, how could a routine demolition go so disastrously wrong? From the wreckage, investigators quickly established that the type of bridge played a central role.
So with a cantilever bridge, balance is everything. Not just during construction and operation, but demolition too. And taking it down from one end had caused serious problems.
Associate Professor of Engineering, G.A. Rosati explains.
During deconstruction or demolition, you need to make sure that the rest of the structure remains stable. So by starting to remove the loads at one end, the bridge became lighter at that end. That end of the bridge started lifting up.
As the excavator was removing the concrete chunk by chunk from the east span, it was leaving the girders exposed. But without heavy concrete to hold the steel beams down, they began rising from the pier.
The previous night, the team noticed the girders lifting up off their bearings. The demolition was immediately shut down until a solution could be found.
They tried a fix by basically using rods and anchored bolts to basically affix the ends of the girders of the bridge back to the abutment so that it would not continue lifting.
But the bridge was so far off balance, the fix wasn't strong enough. With most of the concrete now gone, the girders on the eastern span tilted up, breaking the bolts that held the end of the center sections. As the girders fell, the bolts on the west end failed too, and the whole span dropped to the road.
Ultimately, the bridge lifted on one end, twisted, and that was sufficient to drop the support of the middle span. It slid, lost the support on the opposite end, and basically fell down onto the highway.
It's a bit like being on a seesaw. If one person jumps off, their end flies up, and the other person will crash to the ground.
With hindsight being what it is, they should have started removing all the weight from the middle and then started working from both ends to maintain symmetry of the forces as much as possible. The biggest issue that caused ultimately the failure was starting from just one end that caused that seesaw effect.
With the main artery blocked, getting I-75 south reopened was a major priority.
With more than 150,000 vehicles needing to use this road every day, teams worked tirelessly to get this vital route up and running again.
Just 2 days after the disaster, on January the 21st, 2015, the debris from the old overpass was cleared and I-75 reopened. Hopefully, when it comes to demolition, nothing like this will ever happen again.
The tragedy of the Hoppel Street collapse is an opportunity for learning. And unfortunately, one of the best ways of learning is to learn from mistakes.
There's a reason they do a lot of the heavy work at night. It's because the traffic is lessened. For this to happen when it did, I don't want to say fortunate, but it could have been a lot worse.
When building big, engineers need to work hand in hand with Mother Nature. Underestimating her power can result in devastating consequences. Like this disaster in California, a catastrophic collapse of epic proportions.
The dam actually failed. It released about 12 billion gallons of water, a gigantic wave down that canyon.
An unstoppable tidal wave of devastation and destruction.
A 100-foot wall of water coming down faster than anybody can run, destroying everything in its path.
And a tragedy that shook the entire nation to its core.
This was the deadliest civil engineering failure in the United States.
Los Angeles, the city of angels, now America's second largest metropolis. The home of Hollywood wasn't always a West Coast powerhouse.
LA originally had a population of just 300 or so, but boomed when oil was discovered in the 19th century, attracting people from all over the country.
As the city grew, so did its need for water, but in this arid landscape, that was in short supply. Archaeologist and Angeles National Forest manager Dave Peebles explains.
The limiting factor was always water. In this area, you could have a drought that, a drought for a year is nothing. So they really had to come up with a strategy to support that type of population density.
To quench the city's thirst, in 1913 they opened this, the LA Aqueduct. A plan as bold and ambitious as the man behind it.
LA's Mulholland Drive is world famous. It's named after William Mulholland, a self-taught engineer who became a Los Angeles legend for bringing water to this thirsty, dry city.
William Mulholland came up with the idea to transport water from Owens Valley. And that's about a 233-mile stretch of aqueduct that they constructed. Monumental construction.
Diverting water from high up in the Sierra Nevada mountains, this was a highly efficient and truly remarkable piece of engineering.
Back then, this gravity-powered engineering marvel delivered more than 80% of LA's water. And today, more than a century later, it still provides water to millions of folks from Los Angeles.
But by the 1920s, the aqueduct alone couldn't keep the city hydrated. So Mulholland came up with another bold plan. to build 7 dams, creating huge storage reservoirs, the largest of which, around 60 kilometers northwest of LA, would be the St. Francis.
Right now we're standing on the site of the St. Francis Dam. If you would have been standing here, 100 years ago, you would have saw a gravity arch dam, about 200 feet across the span, and then it would tie into this east-west ridge, concrete that ran along for about 500 feet along that way.
Standing around 62 meters tall, the St. Francis Dam was known as a curved concrete gravity dam that relies on its weight and internal strength for stability. As Water Department Director Stephen Cole explains, it was designed very much like this sister dam.
We're at the Mulholland Dam, built in 1924, exactly the same as the St. Francis Dam. It's a concrete gravity arch dam. The gravity is how much weight the dam has, and the arch is the actual layout of the dam. And that arch actually helps resist the forces of the water as it pushes against it.
The St. Francis Dam was made of giant concrete arches, stacked on the ground like steps. It looked like a vast curving staircase that sealed the canyon, creating the huge reservoir.
Opening in May 1926, the St. Francis Dam held around 54 billion litres of water, enough to supply the city for a whole year.
The dam was the end-of-the-line storage of that overflow that you weren't using, so you could bank and store for those dry times that would eventually come.
But what happened next had Angelenos wishing for drier times. Early morning of March the 12th, 1928, the dam keeper called designer William Mulholland urgently.
The dam keeper had reported leaks, muddy water, which is a real danger sign for dams. Mulholland came out and made a decision that that was nothing out of the ordinary.
The rest of the dam was inspected and given the seal of approval. But just 12 hours later, at 2 minutes to midnight, disaster struck.
That's when the dam burst.
Around 54 billion litres of water flooded the valley below. A more than 40-metre-high wall of water came crashing down.
Faster than anybody can run, destroying everything in its path.
As it picked up speed, it took out the dam's powerhouse, along with most of the workers inside.
It completely took it off its foundation. I mean, that pretty much cut off any of the communications that would have been able to happen.
Without power or the ability to communicate, no one downstream of the dam knew that a massive torrent was heading their way.
The force of that water was tremendous. The wave went all the way to the ocean.
The death toll was enormous, and while exact numbers remain unknown, the latest figures suggest that sadly more than 450 people lost their lives.
The death toll, we're still assessing it. The dam keeper, he's the one that initially reported the leaks to Mulholland. His son and his wife were all killed.
As Professor J. David Rogers explains, the scale of the tragedy was unprecedented.
This was the deadliest civil engineering failure in the United States during the 20th century.
With the devastation nearly total, there were few clues left behind. But investigators determined one major cause was a last-minute design change to give the dam greater water capacity.
They extended the height of the dam during construction twice by 10 feet without doing any other kind of engineering tests or analysis.
That seemingly small increase had major consequences. Stephen Cole from the LA Department of Water and Power explains.
When you raise the height of the dam, you also increase the pressure, pushing on the dam both horizontally and also what's called uplift, which is water that percolates through the ground, through the rock foundation, and is actually trying to lift the dam up. So the higher the water surface, the more pressure you have pushing the dam up, and the more pressure you have pushing the face of the dam too.
He didn't add width to the base, so he had a more dangerous dam than he realized and then uplift force creates instability.
The increased height wasn't the only issue. There was a problem with the construction of the dam itself.
When concrete sets, it expands or contracts with temperature changes. So normally, flexible joints are built in to minimize cracking. But here, that wasn't done.
The dam developed 4 huge cracks, but because the reservoir was full of water at the time, these could only be sealed on the outside wall or downstream side, using a flexible grouting.
The cracks showed up early on, and by early 1928, Mulholland decided to chink those shrinkage cracks on the downstream face because he was losing water through them.
Chinking is a flexible sealant that's normally used on log cabins or wooden ships. But this was one of the largest dams in the world and made of concrete, so this was uncharted territory.
If you're gonna seal cracks, you have to seal them on the upstream side so that that water doesn't get internally into the dam.
But with the cracks sealed on the downstream side, water was getting in, and the pressure was building up inside the dam.
I think that was his greatest mistake he made in the project, because now you had the full reservoir hydraulic pressure build up internally, and that's not a good thing. You need drainage, not blockage. Had he not grouted the dam on the downstream face, the dam might have survived.
To make matters worse, the dam was built on unstable ground.
For me, I think one of the major issues for the dam was the geology of this area. It's really complex.
Some of the challenges, I think, were the bedrock material that the dam was founded on, and the abutments of the dam, which are the sides of the dam, what they're pressing up against. The arch effect relies on the pressure of those abutments to hold the dam in place, and so that may have been a big contributor.
As the pressure built, the thinner, weaker layers of rock gave way first.
There was a huge bedrock landslide that took the left side of the dam and carried it down across the dam and up the other side and send this huge turbid flood downstream.
Regardless of what ultimately triggered the failure, the investigation cited both engineering and geological errors.
When all these factors combined, the result was one of the biggest engineering catastrophes America had ever witnessed, on a dam that was less than 2 years old.
Following the disaster, William Mulholland took full responsibility. He never worked again, and new safety measures were quickly put in place.
The impact it had on the profession was huge, and that was because of the awful outcome. It had a huge impact on dams engineering worldwide.
St. Francis actually helped start the State Division of Safety of Dams, which was an agency that now regulates how we do our dams and maintains the safety of our dams. So that was the one shining light out of that.
What little remained of the original dam was dynamited. Today, nearly 100 years later, the site serves as a reminder of the hundreds of people who tragically lost their lives.
One of the greatest disasters in California history is finally being recognized here. It's just been declared a national monument. It's also been declared a national memorial. The second one in the whole state that's designated for the significant loss of life that happened.
Some fails strike while construction crews are still hard at work, but others can lie hidden for years before they trigger a catastrophe. Like this disaster in Italy, a catastrophic collapse of a vital crossing.
The entire concrete and steel bridge came crashing down in seconds.
Devastating destruction that rocked an entire community.
Cioè, l'ultima cosa che potevo pensare è che venisse giù improvvisamente e non ne rimanesse niente.
And an amazing escape for one very lucky driver.
In quel momento l'unico pensiero che mi è venuto in mente è che fosse finita, che fossi morto.
Tuscany is one of Italy's most popular tourist destinations and also one of the country's most rustic areas. Nowhere more so than the northern edge of the region, with hilltop communities forming near the River Magra, where people not only need to live off the water, but cross it too. Local journalist Emanuela Rossi knows this area well.
Siamo tra il mare e l'Appennino, le montagne, una terra di transito, è sempre stata una terra di transito. L'acqua è la vita, i fiumi sono stati chiaramente la via di trasporto per una terra che comunque è difficile, quindi sono fondamentali, sono sempre stati fondamentali, sia per l'agricoltura che per la comunicazione.
For centuries, the only way to cross the river was by boat. But in 1906, construction began on a pioneering new 260-metre-long bridge between the towns of Caprigliola and Albiano Magra.
This revolutionary bridge was one of the first in Italy to be constructed with reinforced concrete. Now used everywhere, at the time, this was cutting edge.
When it opened in October 1908, the 5-arch span of the Albiano Bridge was welcomed by people across the region.
Il ponte di Albiano era fondamentale perché unisce l'ultimo pezzetto della Toscana al di là del fiume Magra e non ci sono alternative, quantomeno non alternative adeguate.
But more than a century later, this crucial crossing would be in for a rough ride. On Wednesday morning, April the 8th, 2020, local delivery driver Andrea Angelotti was preparing for the busy day ahead.
La giornata è partita come una giornata qualsiasi, una calda giornata. Fortunatamente sono partito regolarmente dalla filiale, ho fatto un attimo una fermata breve, insomma, lungo la strada e poi mi sono diretto verso le prime consegne.
Around 10:25 a.m., Andrea was halfway over the Albiano Bridge when his day took a disastrous turn.
Mi sono visto il tratto di strada davanti a me che si è come impennato e poi mi sono sentito cadere, praticamente mancare proprio il sedile sotto di me. Mi è mancato e poi mi sono ritrovato. Inizialmente mi sono sentito proprio appunto cadere.
It wasn't just a feeling. Hundreds of meters of bridge suddenly collapsed, taking Andrea and his van with it.
Ma sarà durato, io penso, 2-3 secondi, anche se io lo dico di averla vissuta a rallentatore.
The catastrophic collapse caught everyone by surprise. First responders and Red Cross volunteers like Ivan Velardi were shocked by the devastation as they rushed to the scene.
Siamo arrivati qui e c'era un nuvolone di polvere incredibile, non si vedeva più niente. A che ci siamo guardati e abbiamo detto allora è successo davvero.
There had been no warning and no chance to escape.
E poi quando sono appunto arrivato giù ho realizzato quello che era realmente successo, che ero precipitato nel greto del fiume insieme a tutta la struttura del ponte.
Andrea was conscious but lying injured next to his van. Ivan raced down to the wreckage.
Arrivato nel letto del fiume, la prima cosa che ho notato è stato il furgone. Sono fiondato lì sul ponte, ho scavalcato, sono salito sul pezzo di ponte crollato e lì ho trovato Andrea lì disteso sull'asfalto.
Injured but still alive, Andrea was quickly airlifted to hospital.
In quel momento l'unico pensiero che mi è venuto in mente è che fosse finita, che fossi morto, perché quando mi sono sentito proprio mancare proprio il furgone sotto il corpo, poi invece fortunatamente una volta atterrato ho realizzato che sì, molto dolorante, però l'avevo scampata.
Another driver had also gone down with the bridge, but amazingly he too survived with only minor injuries.
This could have been so much worse. Luckily, this normally busy bridge was practically empty with only 2 vans on it at the time.
Beh, mi fa un effetto emozionante riguardare il ponte. Sicuramente adesso riguardandolo così ho la sensazione proprio che abbiamo sfiorato una grande tragedia. Proprio il lockdown ci ha permesso di non piangere vittime o avere una situazione molto più grave.
The 260-meter bridge had collapsed in seconds, with just 2 vans on it. Investigators needed to determine what had caused this devastating disaster. It appears the warning signs were already there.
According to reports, cracks in the deck near one of the abutments had been visible for years and was slowly getting worse.
The investigation is ongoing, but it's possible the cracks were a sign of movement happening within the bridge. In this type of crossing, the culprit could have been the very design features intended to prevent damage inside the structure itself. Giant hinges.
These aren't like hinges on a door, which lets it swing fully open and shut. These were there to allow small movements in the concrete structure, helping to prevent cracking as traffic passed over and the river pushed past the piers.
Professor of Structural Engineering Pietro Croce is on the investigation team.
We have 3 cylindrical hinges in order to allow the hinge to face the external forces. The rotation capacity is limited to very small angle because we are subject to movement which are very, very small. In bridges, this is enough. If all is okay.
But here it seems everything wasn't okay. Something was moving the hinges much more than they could cope with.
What was wrong was the collapse of the hinges, located near the abutment due to excess of rotation. When you require too much rotation, the hinge is prone to collapse.
What was causing the rotation? It's suspected that the ground on which the bridge stood for over a century wasn't very stable.
The construction of the bridge was interrupted when the riverbed was found to be weaker than first thought. This could mean that over time the soil around the foundations moved much more than first anticipated.
One of the possible cases is a movement of the abutment, and in that way you have the collapse of the first arch and then the second arch and the progressive collapse of the whole bridge.
With a bridge like this, the movement of just one support could explain why the whole thing came down. But even if the original foundations were strong enough, the river itself could have been eating away at them all along.
Fast-moving water can erode or scour away soil around a bridge pier, undermining its integrity. Now, this can be a serious problem where a river is prone to flooding, like this one.
The reason can be due to several causes. The final result is exactly the same. You have a collapse of the hinge and then collapse of the arch and, as a domino effect, collapse of the whole bridge.
With the bridge down, a crucial crossing that had stood for more than a century was gone.
Questo ponte unisce 2 regioni, 2 province, 2 comuni, cioè era un ponte essenziale, quindi in realtà ha messo in ginocchio i 2 piccoli paesini che stanno agli estremi del ponte.
While work has yet to begin on its replacement, the disaster may have highlighted an underlying issue with this country's aging infrastructure.
Another investigation found that Italy has around 1,000 viaducts and bridges which haven't been assessed in years. Any one of them could need maintenance to avoid a catastrophe like this from ever happening again.
For Andrea, while the road to recovery may be long and winding, Hopefully, he's on the right track.
Niente, si vede che io penso che potevo morire in quel momento lì, però sicuramente non era il mio momento. Io le sto passando di tutti i colori. Non per questo, insomma, ci arrendiamo, insomma, andiamo avanti. Ho la mia famiglia, fortunatamente, che mi aiuta, che mi sta molto vicino e vediamo, insomma, di superare anche questa.
When engineers innovate, every last detail is crucial. But sometimes pioneering structures bite back. Like this story in Massachusetts that had students running for cover.
People noticed that looks like some bricks were falling.
The world's tallest library was cracking at the seams.
I am just completely blown away by the sheer size and the magnitude.
This tower's fate was hanging in the balance.
Amherst, Massachusetts is a small town of 40,000. But for most of the year, the population nearly doubles thanks to its 3 colleges, including the University of Massachusetts. Aaron Rubenstein is the head of Special Collections and University Archives.
The university was founded in 1863. It was part of the Morrill Land Grant signed by Lincoln, and the idea was to build agricultural and technical colleges across the U.S.
A century later, the university was thriving and growing both in size and academic prominence. There was an ever-increasing need for a state-of-the-art library, but finding the space for it required some book smarts.
To have enough space for books and people, experts suggested the library would need a floor area of around 5 football fields. But in an already crowded campus, spreading out would be impossible. The only way to build would be up.
Completed in 1973, at a mammoth 28 stories tall, this towering library was the tallest in the world. Journalist Ron Charmless knows what makes this library so impressive.
As a structure, it's nearly the length, if you put it on its side, of a football field, 286 feet, 28 stories, 5.9 million volumes. It's one of the sites that people want to see when they come to visit UMass Amherst.
In the 90s, the library tower was renamed in honor of a prominent Massachusetts scholar and civil rights activist.
W.E.B. Du Bois was born in Great Barrington, Massachusetts in, I believe, 1886. And he was ahead of his time as a racial pioneer. And I think naming this library after him, making it such an impressive structure, speaks to that.
Although the tower looks to be made of solid brick, it's just a facade. Max Page is a professor of architecture.
The Du Bois Library is in some ways a very simple building. It is a tower made out of structural steel with a facade, an exterior, attached on. In this case, it was a brick facade purely for beauty.
The facade is made of prefabricated panels about 9 meters high, with a layer of bricks already fixed in place. The panels are then hung on the outside of the building, kind of like picture frames.
The 28-story tower was constructed of steel and concrete, covered with hundreds of these brick-covered panels, each weighing almost 3 tons, supported from below by 12-centimeter deep L-shaped braces.
The facade really is attached and hangs on to the main structure, and that's where those very heavy-duty brackets played the role, because they were built into the main structure of the building and held up the facade, the 30 feet of bricks.
Every once in a while, when I come in the front door and I look up, I am just completely blown away by the sheer size and the magnitude.
But just 3 months after opening, this record-breaking library's hardback cover was beginning to crack.
this glorious opening of this tallest library in the world, and then people noticed that looks like some bricks or parts of bricks were falling. There was a little concern about it, but it wasn't really until several years later that finally someone said, we worry this is a real problem, like maybe the building will fall down. So that's when there was a huge investigation into it, and the library was then closed.
This was shocking. The library was only open for 5 years before people feared that it would fall down.
Engineers scoured the facade for clues to explain the crumbling.
When the investigation took place in 1979, and an initial engineering firm said that this could be really catastrophic, they moved a library books out, they said no one could go in, they put a fence around it, and they also put down bales of hay all around the library so that if the bricks fell, they wouldn't bounce and explode and hit people nearby.
No clear cause was found, and rumors began to circulate.
There are a lot of myths surrounding the Du Bois Library. One of them is that they didn't account for the weight of the books when they calculated its structural strength. It's not true. They absolutely did account for the weight of the books in the structure of the building.
One rumor had it that the library was sinking into soft ground because of a nearby pond, hence the cracking exterior. Again, this wasn't true, but clearly something was going on.
I think people were worried that those small brick pieces meant it was just the beginning, and that in fact the whole facade, which is all brick, all 28 stories, would come crashing down, or maybe the whole building was flawed.
Further investigation revealed that the problem wasn't with the whole wall. In fact, just a few bricks were cracking, known as spalling.
Spalling is a generic term for when bricks come under stress and buckle and ultimately kind of break apart.
And that spalling was only found where the brick panels rested on the braces.
It's at the intersection, at this brace, this intersection where there's lots and lots of compression. It's the bricks right around that kind of intersection point, around these braces, is where the spalling has happened.
This stress was factored into the original plans.
Part of the design was to allow the 6,000 pounds of brick that rested on this brace to have a little place to move as it expanded and contracted with the seasons. And so what they were supposed to do was have something called a soft joint, some kind of material that was just a little bit flexible so that as those bricks expanded, they would have somewhere to go.
But for reasons that remain unknown, instead of being flexible, the joints were hard.
There was nowhere to go when the expansion happened during the warm weather, and so that over time, it pushed out, and some of the bricks were kind of the release valve for the pressure of all this weight on this one spot.
This finally solved the mystery of why only bits of brick were being found. The whole wall wasn't failing, just the bricks around the braces, which were gradually being broken apart by the stress.
By 1983, engineers concluded that the worst of the spalling was over, and they declared the building safe once more.
Some repairs had been done, further investigations made it clear that the problem wasn't quite as bad as originally thought, and that the danger going forward was very minimal. So the state and the university was comfortable with the idea of allowing the public back into the library.
The only practical solution to repair the damage was to remove the broken bricks and patch up the cracks.
Repairs have been done on the facade to minimize the spalling, and so there's almost no reports of bricks or pieces of bricks falling from the facade of the Du Bois Library.
Just in case, a perimeter fence keeps people at a safe distance from the wall.
I actually have no fear about it. Once I learned a little about the history, I am happy to walk in there. There's no danger at all. And I'm actually glad that there is this heroic tower on campus.
Today, this is still the tallest academic library in the world and continues to be a beacon for the students and the university. In California, Catastrophe strikes one of America's most vital intersections.
To witness that much steel collapse in a fiery mess, it's scary.
In Australia, a demolition disaster in the nation's capital, Canberra.
Any event involving explosive is inherently a dangerous thing.
Tragedy in Illinois as a pioneering stadium collapses.
The scene was chaotic. The devastation was total.
And in Michigan, a crucial shortcut cracks at the seams.
It was one of the worst segments of road that I've ever driven on in the United States.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. With big construction, engineers try to prepare for every possible outcome, but sometimes the most unlikely fail can strike the hardest. Like this disaster in California, a catastrophic collapse on a major freeway.
A tanker truck spewing flames, smoke throughout the Bay Area, absolute disaster.
A raging inferno devastates a supersized structure.
To watch a road that you've been over 1,000,000 times just fold like a taco, no words can describe it. It was really shocking.
And a race against time to get this vital road back up and running.
This interchange carries more than 250,000 vehicles a day. They needed to get this route open again, and fast.
San Francisco, the city by the bay, sits at the tip of a 65-kilometer-long peninsula surrounded by water.
For decades, the only way north from the peninsula was by ferry. But all that changed in the 1930s when the city added not one, but 2 iconic bridges.
Bart Ney is the California Department of Transportation's Chief of Public Information.
We're in the Bay Area. We have always built the future. 2 massive and historic bridges. The Golden Gate Bridge in San Francisco and the San Francisco-Oakland Bay Bridge here on the East Bay. All of the roadways here sort of feed towards the Bay Bridge, which is the gateway to San Francisco.
Although the Golden Gate gets all the attention, in reality, the 7-kilometer-long Bay Bridge is the area's workhorse, carrying well over 1 million vehicles a week.
And the unsung hero is this winding labyrinth of roads, the MacArthur Maze, connecting the Bay Bridge with 3 major freeways. Peter Hartlob is a local journalist.
It's the most essential stretch of highway in the Bay Area. You're going to use it to commute to work. You're going to use it to go to grandma's house. I mean, it's something that everybody knows and uses.
It's a rather complex and robust piece of engineering that takes 3 major arteries, Interstate 80, Interstate 580, and Interstate 880, through the East Bay and distributes them onto the Bay Bridge so you can head into San Francisco.
Originally completed in 1936 to coincide with the opening of the Bay Bridge, over the years the maze has evolved to truly earn its name.
We're approaching the maze. There's a flyover over me here. I think this goes to San Francisco. We've got one coming over here. I think it goes to Oakland. I'm not sure. I've lived here almost all my life. I still get lost on the MacArthur Maze. It is an absolute just bowl of spaghetti.
If you look at it from above, it's almost like looking at somebody's heart. There are so many arteries coming in and out of this distribution center.
While the maze might look like a gigantic mess, the engineering behind each intertwined section is very carefully designed for an area that's famous for earthquakes.
It was built extremely robustly and built to last. It was also built with the thought that this is earthquake country and there would need to be some flexibility in it. And that's why over the years, the MacArthur maze has done well in earthquakes.
The maze stood firm against huge tremors that decimated the Bay Area. But in 2007, it was struck by something entirely unexpected. April 29th, a tanker truck loaded with gasoline was heading into the MacArthur maze, en route to a fuel station in Oakland.
It was the early hours of Sunday morning. Very little traffic, very quiet on the roads.
Just before 4 a.m., the tanker hit a guardrail and overturned, spilling thousands of litres of gasoline. Thankfully, the driver escaped before the truck exploded. The unfolding disaster was caught on camera. Caltrans Communications Chief Banijay was at home when he heard the news.
I was in bed, I was asleep. It was 4 o'clock in the morning. And I was called by the Bay Bridge project manager. He said, turn on the news. He said, it doesn't matter what channel, just turn on the news.
Just 20 minutes later, as the fire and heat intensified, the top span of the maze suddenly gave way.
To witness, that much steel collapse in a fiery mess, it's scary.
Journalist Peter Hartlob knew a major catastrophe was unfolding.
We saw, just incredible flames, smoke throughout the Bay Area. You can see it everywhere, and we knew something huge had happened.
Fire crews fought for hours to control the blaze. By morning, the devastation was plain for everyone to see.
I didn't think it was possible to melt a steel freeway like that. And to watch watch a road that you've been over 1 million times just fold like a taco, no words can describe it. It was really shocking. It looked like a war had happened.
Incredibly, despite the intensity of the inferno, no one was seriously injured in the disaster. But with the Bay Area's most important intersection decimated, drivers prepared for chaos.
When we saw what was going on in the East Bay, we knew this meant shutdowns for a long time. It was a huge, huge thing on people's minds from the beginning.
We're literally under the maze, the part that collapsed. A major truck thoroughfare. You'll see trucks moving across here as we're talking. There goes one. This is the heart of traffic in the Bay Area. If you lose the maze, then you're going to have gridlock throughout this entire part of the state. The big question was, why had a structure that stood strong against some of California's most powerful earthquakes been destroyed by a truck fire?
Evidence in the wreckage showed that the structure had endured unexpectedly high temperatures.
There was so much volume of fuel here that it produced temperatures that the steel never should have seen.
Professor of Engineering Abul Hassan Astane Asal investigated the collapse.
When the temperature goes up, reduces the strength of steel. These are the bumps due to buckling of steel because it has lost strength. This was about half-inch thick plate.
As the heat intensified, the steel plate girders supporting the concrete roadway began to twist and bend, not only altering the shape, but crucially the strength of the steel.
Steel is an amazing material. We use it all over the place in bridges because it's so resilient. However, one of the things about steel is that you can mold it into different shapes, but it takes an immense amount of heat to do that, and you don't normally see that type of heat out on the freeway.
It's estimated that the blaze reached 1,000 degrees Celsius, around double the heat that the steel was designed to withstand.
1,000 degrees is around the same temperature as a volcano, burning within all this concrete and steel. But the intense heat wasn't the only problem.
Investigation revealed the exact location of the inferno made things far worse. Against the odds, it was directly below one of the main connections supporting the roadway above.
See that truck going across? The truck probably began its fall right about there on that curve, and it landed right there against that support. So it was literally the worst possible place for fuel to ignite because it was right underneath the steel.
Steel, it's good until about 500 degrees Celsius, like 1,000 degrees Fahrenheit. But at that point, it loses strength rapidly. So just one truck at one location, two of them collapsed.
We have an overturned truck that is spewing out something as hot as molten lava right under the freeway that everyone here uses to get to work, to get to grandma's, to get to soccer practice. Absolute disaster.
With traffic gridlocked and the economic impact estimated at around $6 million a day, officials knew they had to get this vital interchange back up and running fast.
This was quite easily the biggest traffic disruption we had ever seen in the Bay Area. Thousands of vehicles go through this area at any given hour. Time was absolutely critical because time means money, and delays in traffic affect everything.
Officials estimated the maze would take at least 50 days to repair. But what actually happened was nothing short of remarkable.
Less than 48 hours after the collapse, demolition crews removed the mangled section. And within days, construction was moving full speed ahead.
Girders are coming in, stuff's going up incredibly quickly.
Some steel came from Pennsylvania and it was fabricated in Arizona.
Just to get the girders up here, they've got two guys in a truck so that one guy could sleep and one guy could drive, and all they're doing is stopping to go to the bathroom.
Those people worked around the clock. And there was a giant welcome message on the steel when it arrived here from Arizona to the people of Oakland.
Just 26 days after the collapse, and crucially with increased levels of fire protection, the repaired MacArthur maze reopened to traffic.
While modern fireproofing and thermal protection might help reduce the risk of collapse, if you're facing a freak accident and the flames as hot as a volcano, there's not much more you can do.
For me, it's not about the accident. For me, it's about how quickly this got done. Everybody coming together from places outside the Bay Area, and just an absolute miraculous amount of time.
The maze is still doing its job. It's still doing the thing it was designed for in the 1930s. It's getting people to their destinations, it's getting trucks where they need to go in the East Bay, and it's keeping America strong.
In engineering, safety and planning must always go hand in hand. Get the design wrong and safety goes out the window. Like this catastrophe in Australia, where a routine detonation turned to tragedy.
Everybody was looking forward to it. It was going to be something that we should tell our children about.
Thousands watching as a hospital demolition ends in devastation.
It wasn't what we were supposed to be seeing at all. Big chunks of metal flying into the lake.
And a blast that sent shockwaves across the nation's capital.
When you're using explosives in front of a huge crowd, you have to get things right.
Canberra, Australia, sits on the banks of the Molonglo River, surrounded by the Australian bush. This inland city was founded in 1913 to serve as the newly independent nation's capital. Journalist Emma MacDonald is a Canberra native.
Canberra is a very unique city because the government decided to launch an international competition to have Canberra designed. The plan at the time was a sort of futuristic city, really geometric. There's no very, very tall buildings. It's been kept at a low level. Some people love it, some people loathe it. I love it.
Canberra is one of the great planned cities of the 20th century. Every detail was meticulously sketched out, from its state buildings to its boulevards. And like every major city, Canberra needed a major hospital to support it.
Built in the 1940s, for 5 decades the Royal Canberra Hospital served the city from the shores of Lake Burley Griffin. But in the 1990s the ageing hospital was closed and its lakefront buildings scheduled for demolition. As journalist Verona Burgess explains, the decision wasn't without controversy.
Practically every family in Canberra had a connection with it. Somebody had been born there, somebody had died there, somebody had had their lives saved there. So it was a very big emotional and political topic when the government wanted to knock it down.
In an effort to get the public on board, the government invited spectators to attend the event.
It was the hospital that I was born in, and when it was demolished, the government touted it as a family day out. It was meant to be, you know, seeing a little bit of history come down. It was meant to be a safe, wonderful adventure for the family.
The plan was for the steel-framed buildings to be brought down with explosives.
In a controlled implosion, the structure should collapse within its own footprint. At least that's the theory.
Explosives engineer Dr. Graham Mackenzie explains.
The key to do it is take the columns out at the bottom of the building to start it moving down. Then each of the floors in turn, the columns supporting the top will be blown, then the next floor columns will be blown. So what's happening is the building's moving down. If it's off-centre, the building will go sideways. You want it to go straight down.
In a controlled implosion, the placement of the charges and the timing is key.
The concept is you use the minimum amount of explosive to facilitate the best progressive collapse. If you use the minimum amount, there's less likelihood of fragmentation, there's less likelihood of people being hurt.
Sunday, July the 13th, 1997, Demolition Day. Boats and huge crowds descended upon Lake Burley Griffin.
One of the largest crowds in Canberra's history, more than 100,000 people, gathered to witness the final stages of the demolition.
A 200-metre exclusion zone was enforced. Journalists Verona Burgess and Andrew Campbell were among the crowd.
I was at the Canberra Yacht Club, which directly looks across the lake, and it was quite a festive occasion because the government had wanted to make it a community event.
I was based here just on the bridge. There was a level of excitement and there was an air of anticipation in the crowd. Everybody was looking forward to it. We'd been told it was going to be something that we should remember and tell our children about. There were people literally only a few hundred metres away from the actual explosion site.
Shortly before 1:30 p.m.
It was 2 sets of explosions, basically. The first one was a very small one, and then the second one much larger.
It was not anything like what we'd expected. You expect to see the building kind of collapsing in on itself and just a big cloud. But what happened instead was we started seeing bits spurting out the side of it.
For Verona, it was clear something had gone very wrong.
These bits of concrete and metal are flying into the lake. This isn't right. This can't be right. This isn't what it was supposed to be.
Instead of imploding, the blast shot shrapnel over the lake as far as 800 metres, 4 times the distance of the exclusion zone, directly at the crowds.
And then this big piece came sort of hurtling towards the yacht club, and I think that was when I realised this is actually a disaster.
While 9 people were injured, tragically 1 girl, standing about 400 metres away, or twice as far as the exclusion zone, was struck by debris and died instantly.
It was terrible. It was awful to think that this little girl had just lost her life for no reason.
We were there for the implosion, and we didn't anticipate that it would turn into a tragic event.
I still can't talk about it without just feeling so sad. It was just a hideous, terrible, terrible thing to happen. Everyone was in shock and it was just awful.
Canberra's citizens were demanding answers.
We all wanted to know who was at fault, and I think the most obvious was the local government, who'd literally told us all to come down and see it, and had hyped the event as being such a public spectacle.
There's little doubt that without a crowd there would have been no tragedy. But for the official inquest, one big question was why this routine demolition had turned to disaster.
The inquest found a number of failings, from too much explosive to incorrect cuts in steel columns. The list goes on. When all these things combined, it explained why this demolition went disastrously wrong.
The key problem was uncontrolled debris.
I don't believe that the right explosives were used. I don't think they were protected from producing fragmentation. The safety distances for the public were totally inadequate. There's a lot of hope and prayer. There was nothing else.
The coroner's inquest discovered that the original plan had been to use around 130 kilograms of explosives. In reality, almost 500 kilograms were used, a seemingly huge miscalculation.
That's around 3.5 times the amount of explosives required. That's massive.
Inspectors also discovered that there had been a last-minute change to the blasting configuration on the day of the demolition.
There was still a working hospice not too far away, with patients who were unable to leave. So the explosives were placed so that the blast was in the other direction, which was towards the crowd.
This change meant the exclusion zone was now inadequate.
The possibility of fragmentation for steel flying large distances is high. The safety distance that applied to steel structures or anything to do with steel is much, much farther away.
An army major giving evidence to the inquiries said that for a blast like this, the standard exclusion zone is around 1,000 meters, which is almost twice as far away as the main crowd was standing.
We were technically in the blast range, as it turned out. Parts of the hospital ended up at the National Library on the other side of the bridge.
Following the disaster, the inquest made a number of recommendations that it strongly suggested should be followed in the future.
One of the key proposals was that for all future demolitions, fully independent explosive experts and structural engineers should be consulted at every stage of the process.
A memorial acts as a permanent reminder of the tragic event that took place that day in the nation's capital.
An implosive demolition as a public spectacle is fraught with danger. Safety has to be paramount. That way, tragedies like this can hopefully be avoided in the future.
In engineering, every step from design through construction has to be rock solid. One mistake can bring everything crashing down to earth. Like this disaster in Illinois, a pioneering stadium brought to its knees.
I noticed right away that the roof had pancaked down.
Engineering errors that shook a community.
You knew you had serious injuries, and some of these people were our neighbors and friends.
The burning question, what had gone so catastrophically wrong? Chicago, Illinois lies at the heart of the third largest metropolitan area in America, with around 10 million residents. It's also home to one of the world's busiest airports, Chicago O'Hare.
Since the mid-70s, O'Hare has handled more than 500,000 flights a year, with tens of millions of passengers heading into Chicago. All of those people coming and going created an economic boom along I-90, which is now known as the Golden Corridor.
For O'Hare's neighboring community Rosemont, the golden opportunity transformed the town. Todd Wessel is a local journalist.
You can't be any closer to O'Hare Airport than Rosemont. There are several cities that actually abut or touch Rosemont property, but the uniqueness of Rosemont is that it has an expressway-like road that goes in and out. It is really the only entrance in and out of O'Hare Airport, and thus the development of Rosemont.
Rosemont might be small, but thanks to the Golden Corridor, it punches well above its weight.
Rosemont is probably one of the most unique towns in the entire country. It's a town of 4,200 people, but it is home to a 20,000 seat stadium, convention center, luxury theater, and it's an entertainment destination for a lot of people in the Midwest and the Chicago area.
In 1980, this small town gained a major new landmark, this vast multi-purpose arena, originally known as the Rosemont Horizon.
The stadium has hosted everything from ice hockey to monster trucks, as well as live music from major artists like the Rolling Stones, U2, even Madonna.
Inside, the 20,000-strong crowd had an uninterrupted view of the action, thanks to the giant self-supporting roof.
Constructing an arena this size is always a massive engineering challenge, but building one directly under the flight path of Chicago O'Hare gave engineers a real headache: noise.
As you can see, many, many thousands of planes travel very, very close to the arena, and they fly down the Kennedy Expressway and land right at the airport.
But jet engines and live music don't mix. So engineers came up with a clever solution. Instead of steel or concrete, they would use wood. Professor of Engineering, Dr. Solomon Kadira explains.
The reason why the Rosemont Horizon roof was to be wood versus steel, which is common to use for roof, wood is much better noise insulator compared to steel.
Wood is full of tiny gaps or pores, which help to trap air molecules, dampening sound from the outside world.
The fact that this arena is close to O'Hare, many planes going on top of it, and you definitely want to deaden the noise inside the arena.
Construction on the $19 million stadium began in September 1978.
The main structure of the arena was relatively simple, essentially 4 stories of concrete, but the epic wooden roof was unique.
16 wooden arches resting on 32 concrete buttresses would span almost 90 meters across the stadium, with hundreds of girders bolted between them, creating a solid frame, topped off with wooden planks and a 2.5 centimeter thick weatherproof canvas sheeting.
At the time, this was the largest commercial roof of its kind east of the Mississippi. It was an engineering masterpiece.
During the summer of 1979, the gigantic wooden roof was taking shape.
When they were building the Horizon, it was special to have it here. It was something we were all very excited about having.
On August the 13th, 18 workers were on the roof installing the final 2 arches. Just after 8 a.m., without warning, the innovative wooden frame collapsed. Journalist Todd Wessel heard the news.
I've heard something bad had happened at the site of the Rosemont Horizon. I immediately got in my car, drove out here, and I noticed right away that there was a disaster and the roof had pancaked down.
A firefighter at the time, Roy McCampbell, raced to the scene.
It basically looked like a lumber yard because it was just a pile of lumber at that point. The wood didn't look damaged. It looked like it had just all fallen over. you knew you had serious injuries. And some of these people were our neighbors and friends.
Rescue crews from surrounding communities helped scour the wreckage.
It was obvious that the devastation was total. The scene was chaotic. I remember seeing a fireman I've known for 40 years. He was crawling on top of the roof looking for survivors.
Our goal was to ascertain who needed care and if we could find people that were injured at that time. There were other members of the teams working to find people that were buried.
Rescuers freed many of the trapped workers. While 16 were injured in the collapse, tragically 5 lost their lives.
The deaths of many people due to the collapse, that was just awful. You could always build a new stadium, but you can't replace the people who passed away.
The authorities immediately launched an investigation. The concrete structure was unscathed, so something must have gone wrong with the wooden frame.
One of the reasons that was speculated on are the planes in and out of O'Hare International Airport. Planes, when they come over buildings, of course, they produce large amount of noise, decibels very high. If they are very low, they also will affect the wind flow, wind pattern.
Jet wash can create waves of air pressure, but engineers didn't think that that alone could explain the collapse and dug deeper for problems within the structure itself.
Closer inspection revealed the real issue lay in the method of construction, which had left the roof unsteady.
The reason why the Roseman Horizon roof failure occurred is because of global instability. The entire structure globally was not connected.
In the design, hundreds of smaller girders were supposed to be connected to the giant arches using angle irons, each secured with 3 bolts. But the investigation revealed that less than half the bolts were in place, and hundreds of those had no nuts fitted.
The members were not connected rigidly to each other during construction. They were apparently in the process of connecting them, but also there were some bolts that's missing. More than 53% of the bolts were not installed.
Yet, it turns out that was part of the plan.
They wanted to keep the roof as a flexible roof. If you install all 3 bolts and make it stiff, make it tight, rigid from the beginning, then what happens when the entire roof wants to settle down? Then there is some resistance to that settling, which creates some strange force distribution. So what they decided is, let's just install 1 bolt connecting the arch to the girder, let the structure be flexible.
Engineers knew the roof would be unstable until fully secured. So steel plates, known as compensating plates, were bolted where the girders met the arches to keep things steady during the construction phase.
The compensating plate that was supposed to be installed on the top of the arch, connecting all those members together, it was either not properly installed or it was not installed at all.
Although they were essential to stability, barely 1/4 of the plates were properly installed. The entire roof structure was a house of cards, just waiting to fall.
There was yet another problem.
One reason that contributed to the lateral instability is when they were building the roof, they were stockpiling materials on the side of the structure. So at certain locations, they were what we call concentrated load. It is not a uniform load. That load was they're just stockpiling, and from the calculation that done later, that stockpile of materials and light equipment and the weight of the workers exceeded the maximum that's allowed by more than 50%.
Now all it needed was a nudge.
The wind was blowing on the side of the arches. That also contributed to the lateral instability of the arches. So all of those reasons combined contributed to the global instability of the roof that caused the collapse.
The National Weather Service at O'Hare reported winds of less than 23 kilometers an hour at the time. It really didn't take much to bring the roof crashing down.
The collapse devastated the community. However, the city of Rosemont was determined to rebuild. This time, every single critical piece was fully in place.
Anytime there is a collapse, the construction industry, the engineering industry learn from any collapse. There's nothing better than learning from failures to avoid the failure in the future.
The Rosemont Horizon finally opened to the public in May 1980.
Once the stadium was built and ready to go, we attended the very first show here, George Burns and Kenny Rogers, and we knew from the get-go that this was going to be a real winner for our community.
More than 4 decades later, the stadium still stands in honor of the workers who died on that tragic day in 1979.
I never forget the sacrifice that was made. I never forget the day, because I think the people that sacrificed needed to be remembered, the events needed to be remembered, and there's part of history here.
When building big, every component, no matter how small, is crucial. Get it wrong and catastrophe can be just around the corner. Like this failure in Michigan, a nightmare on a major highway.
It was one of the worst segments of road that I've ever driven on in the United States.
A shortcut that drivers would rather avoid.
People were choosing to drive for an extra hour just to stay off this road.
A freeway that failed to stand the test of time.
Just deteriorated very quickly, and obviously much too quickly.
Grand Rapids, Michigan was founded in 1826 and thrived thanks to the powerful Grand River that flows through it. Jim Hager is a local journalist.
We are right in the heart of downtown, and the Grand River is behind me. The Grand River is the largest and longest river in Michigan, and it runs through Grand Rapids.
The river behind the rapids drove this city's success.
150 years ago, this river served as a primary transit arm for the logging industry. You didn't have trucks, you didn't have trains, you had the river and the logs would float down the river until they got here.
As the city grew, the Grand was dammed to provide power for industry, while the existing river traffic moved over to rail and road.
We've created these rivers of concrete, and they become vital to our economy. You need good roads.
Back in the 70s, the state identified one route south of the city that would be essential for future growth, the Paul B. Henry Freeway, known as the M6.
The M6 is a 20-mile freeway that was built in the early 2000s. This expressway is considered a significant shortcut for the people traveling from Chicago to Lansing and anywhere in outstate Michigan.
The M6 was designed to deliver a smooth ride for decades to come, thanks to an age-old material, concrete. Dr. Angie Okono is a civil engineer.
Concrete sounds very simple, and yet it is very complicated. You have to be very careful about the exact ingredients. So this is the stone. As you can see, it's very coarse. And then this is the sand. It's really fine with a size less than 5 millimeters.
Once those materials are mixed with cement and water, there's only one ingredient left to add.
We think of concrete as a hard, densely packed material, and it kind of is. But for road building, especially where winters are harsh, there's an unexpected ingredient: air.
A special resin is added last to create these all-important air bubbles.
As temperatures change with the seasons, these tiny pockets of air allow the concrete to expand and contract without cracking. Getting the bubbles right is vital.
The $700 million M6 took 3 decades from planning to construction. Finally, in 2004, to the relief of road users, this shortcut opened to traffic.
Usually when you lay concrete on a road as a pavement, you expect it to last 50 years before having to carry major maintenance work.
As local engineer Jade van der Kamp knows, getting roads like this right is vital for a nation reliant on its automobiles.
In the United States, we drive everywhere. This is how we get from point A to point B. And having the infrastructure to do that is incredibly important.
But after only 7 years, it became clear that the M6 had a serious problem.
It just deteriorated very quickly, and obviously much too quickly. It just began developing these giant potholes, and not just the size, but the number of them. It was just a pothole-filled road.
By 2017, a 6.5-kilometre stretch had become a daily nightmare for 50,000 commuters. Jade was part of the team tasked with assessing the problem.
The worst part of that road was like driving over inverted speed bumps, essentially. So if you think of when you drive over a speed bump going down the road, you typically slow down a lot, except now you're doing them at 50 miles an hour or 70 miles an hour. And it really was quite violent. The whole vehicle would shake. It was one of the worst segments of road that I've ever driven on in the United States.
Analysis of vibration levels revealed the road wasn't just bumpy, but a risk to vehicles.
It was surprising, but we found that in the 4-mile segment, which we're on right now, that segment especially would do 10 times the normal amount of damage for what you would expect in a highway setting. A road where people are, that's their daily commute, that is that violent, is going to do significant amounts of damage to your vehicle.
The road was clearly falling to pieces. The question was why. The region's weather immediately came under the spotlight.
In West Michigan here, it's lovely in the spring right now. It's beautiful in the fall. It's gorgeous in the summer. However, our winters are brutal.
Those harsh winters take a heavy toll on the roads.
The temperatures will rise above freezing during the day. The sun will melt the snow, and we'll have wet roads, and they'll be moist. And in the evening, when it gets colder and below freezing, it turns to ice.
With time, most roads develop cracks, and when it rains or snows, water gets in. Now that's no problem in the warmer months, but in the winter, when the water freezes, it causes the cracks to grow.
And then this cycle is going to repeat again, because then the next time that you have a freeze, because you have the micro cracks, you have more water seeping in, again it's going to freeze, expand, and then you're going to keep propagating the micro cracks.
But the cold weather alone didn't explain the speed of the failure. A closer inspection revealed a hidden flaw. The very thing that should have ensured the integrity of the concrete, the air bubbles.
Analysing the concrete, experts believe the bubbles, although already tiny, might have been too small, the result of using new, untested resin to create them.
The state's Department of Transportation also suggested that the journey from the concrete mixing location to the construction site could have played a part.
Ironically, transporting the concrete on rough roads before it was poured might have shaken some of the air out of the bubbles.
With the bubbles too small to do their job properly, harsh salts and the freeze-thaw cycle rapidly accelerated the damage, causing the M6 to crumble. In 2017, a $9.5 million project was announced to replace the failing concrete on the worst affected parts with new asphalt.
When we found out it was going to be replaced, I think the initial reaction was finally.
After a 6-month closure, the M6 reopened to the relief of local drivers.
My personal experience was it was great to be able to use all the lanes again. It was so much smoother than it had been, and I didn't avoid it anymore.
It was nice. I mean, it's went from probably the worst road that I've ever driven on to one of the nicest roads that you've driven on.
In Italy, a towering bridge suffers a catastrophic failure.
There was no warning and nothing anyone could do to stop it.
Tragedy strikes a Connecticut construction site.
The building was totally collapsed, as if a bomb had gone off.
In Canada's capital, devastation as a bridge fails mid-construction.
Boom, everything went down. So you didn't even have a chance to move.
And in Australia, a legendary icon that's been getting critical reviews.
It's always been quite controversial amongst musicians and performers.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. With big construction, engineers are constantly pushing boundaries with bigger and bolder designs. But if things go wrong, the results can be catastrophic. Like this disaster in Italy, a devastating failure on a vital crossing.
Diciamo, la scena che si è presentata è difficile da descrivere. La percezione della tragedia, del dramma è stata immediata.
A shocking bridge collapse that brought a city symbol crashing down to earth.
Incredulità. È come se crollasse una montagna. È impossibile.
And a tragedy that left a nation reeling.
This was one of Italy's deadliest ever engineering disasters.
Genoa in northern Italy is one of the country's most historic ports and the birthplace of Christopher Columbus. Like many local residents, Giuseppe Leonardi is proud of his city's long-standing maritime traditions.
Genova è sempre stata una città sul mare e continua, seppure diciamo con sistemi ovviamente consoni all'epoca che stiamo vivendo, ma continua a vivere per il mare e con il mare.
As Genoa's economy and population grew, its aging infrastructure was struggling to cope. So in the 1960s, engineers built this, the Viadotto Polcevera, or Morandi Bridge. At the time, it was one of the longest concrete bridges in the world. Brian Aietto is a structural engineer and journalist.
Genova stava subendo una trasformazione. Quindi, quando commissionarono l'autostrada e questo grande ponte, per Genova era una rinascita.
Opened in 1967, the Morandi Bridge towered high above the city, carrying traffic on one of the busiest highways in Europe. And soon became a landmark, defining a new era of Italian engineering might.
Ponte Morandi era un'opera così mastodontica, usava così tante tecniche innovative che è stato paragonato al Golden State Bridge per l'Italia.
This nearly 1,200-meter-long cable-stayed bridge stood out thanks to its bold and daring design. At each 90-meter-tall tower, the road deck was supported by just 4 giant steel and concrete cables. Vincenzo Nunziata is a structural engineer.
Lo strallo che cos'è in effetti? È un tirante che serve a sostenere in un punto l'impalcato. In questo caso il pilone o il pilastro, che è fatto in un certo modo nel viadotto Morandi, serve a trasferire i carichi dall'impalcato in fondazione. Normali sono costruiti solo con delle funi in acciaio. Questi invece sono dei tiranti che, oltre ad avere delle funi in acciaio, sono rivestiti con una guaina di calcestruzzo precompressa.
The idea was that the bridge's concrete structure wouldn't need any maintenance, and neither would the steel, because the cables would be protected from the elements by a concrete coating.
When the viaduct was designed, steel was in short supply. By using pioneering techniques to combine the two materials, engineers built a structure that was lighter than its steel predecessors, yet, in theory, just as strong.
For more than 5 decades, this eye-catching bridge carried millions of people every year. But a sudden and devastating catastrophe was about to make this majestic crossing infamous around the world. Tuesday, August the 14th, 2018. The city of Genoa was waking up to a huge summer storm.
By 11:30, the rain was so heavy that visibility had dramatically fallen. The bridge was covered in a grey mist, forcing vehicles to slow down.
Moments later, disaster struck. Footage captured by security cameras showed a nearly 200-metre section of the bridge collapsing, along with one of its 3 supporting towers. Unable to stop, vehicles fell around 45 metres to the ground. President of Genoa's Red Cross, Giuseppe Leonardi, received a call that the bridge was down.
Tanto nessuno di noi immaginava una cosa di questo genere. E quindi la percezione della tragedia, del dramma è stata immediata.
When Giuseppe arrived on the scene, his worst fears were confirmed.
Diciamo, la scena che si è presentata è difficile da descrivere. Comunque, diciamo, le macerie erano dappertutto Vi chiedo scusa, ma...
The symbol of Genoa and Italy's engineering prowess was in ruins. But incredibly, one truck on the bridge had managed to stop just in time.
L'autista, ho sentito poi raccontare, è corso indietro verso la galleria per avvisare il più possibile quelli che sopravvenivano di fermarsi. E forse il suo intervento è stato fondamentale per salvare la vita di molte persone.
While the truck driver's quick thinking had probably saved lives, dozens of vehicles had already gone down with the bridge. Tragically, 43 people died.
La scena che si è presentata era una scena che ritengo di non essere capace di descrivere nella sua tragicità, nella sua realtà.
This was one of the worst engineering disasters in Italy's history, and the nation demanded answers. Italy's Prime Minister declared a 12-month state of emergency, and an investigation was immediately launched. Attention quickly focused on the revolutionary sheathing encasing the cables. The pioneering use of more concrete and less steel had created a problem.
Concrete is great in compression, handling heavy loads pushing down on it, but unlike steel, it's not so great in tension with loads stretching or pulling on it.
By using less steel, not only have you got less strength under tension, but because the steel is encased in concrete, you can't inspect it unless the concrete cracks, and by then it could be too late.
And when the concrete did crack, the viaduct's location, in a busy industrial port with polluted and salty sea air, would only make things worse. Exposed to the elements, the crossing's signature structure was slowly being eaten away.
Cracks in the concrete casing meant that the steel inside was corroding. hidden and out of sight. The very thing that was meant to be protecting the steel was in fact slowly destroying the bridge.
With millions of vehicles crossing every year, and after more than 5 decades of deterioration, the bridge suddenly and tragically gave way.
C'è chi dice che si è rotto lo strallo, chi dice che si è rotto prima la trave, alla fine comunque si è rotto un qualche cosa che ha comportato che l'antenna ha comportato, diciamo, come se fosse diciamo, una costruzione Lego, cioè tutti gli elementi che componevano la struttura, quindi pilone, antenna, cavalletto impalcato, come un sistema, con una rottura a catene, in effetti è crollato l'intero ponte.
It turns out the signs had been there for years.
More than 25 years before the collapse, the concrete encased cables were already heavily corroded. But instead of replacing them, the decision was taken to add extra cables around the outside.
Chi ha studiato un po' ingegneria civile sa che le strutture non crollano all'improvviso, avvisano. Un edificio in muratura mostra lesioni, una struttura in acciaio si deforma tantissimo, così come una struttura in cemento armato. Le strutture, se osservate, ci parlano, a volte gridano il loro malessere e può questo grido durare per anni. Sta a noi ascoltarle e intervenire prima che l'inevitabile accada.
While the judicial case is ongoing, in December 2020, it was reported that the inquiry is focused on both design flaws in construction and poor maintenance as the most likely causes. The recovery and cleanup operation was huge. Nearly a year after the disaster, the 2 remaining spans were finally demolished, and work began on the new crossing.
Construction crews worked round the clock, and the new bridge was opened less than 2 years after the tragedy.
With the new bridge, the spans are entirely supported from beneath by 18 giant concrete piers. Although the new crossing was born of tragedy, 43 lights will serve as a constant reminder of the 43 people who tragically lost their lives.
Il ponte ormai era uno dei simboli della città, no? Di cui si andava anche orgogliosi. Quindi ci ha colpito tutti.
Spero che il Ponte Morandi il lascito del Ponte Morandi, di questa immensa perdita, ci ricordi l'importanza di prenderci cura di quello che abbiamo, che è inestimabile e unico, e come mi piace a volte dire, è il nostro onere e il nostro onore.
With big construction, how you build can be just as important as what you're building. One small mistake can trigger a major catastrophe. Like this project in Connecticut that came crashing to the ground.
Without any warning, both buildings totally collapsed.
This was one of America's worst ever construction accidents.
A tragedy that tore through the heart of a community.
You had workers trying to rescue their own. It was like Armageddon.
This catastrophe changed the American construction industry forever.
Engineers have come to recognize the risk just isn't worth it.
Bridgeport, Connecticut. Once a whaling and shipbuilding town, this historic seaport has become a cultural hub. Lenny Grimaldi is a local journalist.
Bridgeport is Connecticut's largest city. It's situated about 50 miles north of Manhattan. Bridgeport's known for its beaches and parks. There's a new buzz in Bridgeport right now because it's becoming an arts and entertainment destination, driving a lot of new people here.
But this thriving town hasn't always had it so good.
In the 1970s, Bridgeport was suffering from mass unemployment, rising crime, and people were choosing to leave. But in the 1980s, there were hopes that the city would turn things around with new construction projects.
In 1986, construction began on a luxury apartment complex to breathe new life into downtown Bridgeport.
So this was a period when Bridgeport was trying to reinvent itself with new housing downtown because there was very little housing in downtown at all. So there was excitement built around the construction of L'Ambiance Plaza.
The new project consisted of two 16-story towers slightly offset from each other, with 13 floors of apartments sitting above 3 levels of car park.
The building's design was relatively straightforward, but what was interesting was how it was going to be built.
David Peraza is a structural and investigative engineer.
It was built using the lift slab method of construction. The general idea is that all of the concrete slabs for the floors are poured or placed at ground level, right on top of each other, like pancakes. And then once they're cured, once they're hardened, then they're lifted into place to their final destination in the building.
The entire process centers on a network of vertical steel columns. Civil and former Army engineer Stephen Ressler demonstrates.
This represents a steel column, which is sitting on a concrete footing. Once all of the columns have been constructed, the next step is to cast the concrete slabs. As you can see, when it's cast, there will be a hole in the center, a rectangular hole, and integrally cast within that hole is a steel fitting. It's called a shear head.
These steel shear heads are key to the technique, which uses high-powered jacks to lift the slabs.
The jacks are placed on top of each one of the columns, and from these jacks, 2 very heavy steel rods hang down, and they engage or hook into the shear heads in order to lift the slabs.
The hydraulic jacks are activated, and the slab is lifted up into its final position. Once the slab has been lifted, it must be temporarily parked in place using temporary steel wedges.
At each shear head, there would be 2 of these wedges that were installed in order to park the slab. There'd be one inserted on one face of the column and then another one that's inserted on the other face of the column.
And then these steel wedges are welded into position. The jack can then be removed. Once the builder is sure that all the slabs are in the correct position, the welders go back in and put permanent welds on those wedges, and then concrete is poured into this rectangular opening in order to seal the joint between the slab and the column, and then that particular phase of the construction process is complete.
These concrete slabs are hugely heavy, so precision and balance are key. Too much lateral movement and the whole thing can come down like a house of cards.
The lift slab process is fraught with peril. There are innumerable ways that the process can go wrong if it's not managed with extreme care.
April the 23rd, 1987. About 6 months into construction, workers were lifting the slabs for levels 9 to 11. Journalist Lenny Grimaldi was on leave when his newsroom called.
My answering unit was very, very loud and very, very clear. Lenny, your vacation's over. Get into the office. L'Ambiance Plaza has collapsed.
Mayor at the time, Tom Bucci, also heard the news.
I thought maybe 1 or 2 floors had collapsed. Never did I think the entire building collapsed. How could that be possible?
Both towers had crashed to the ground.
Some eyewitnesses said the building came down in as little as 2 seconds.
Tom and Lenny headed to the scene.
I got out of the car and saw the building was totally collapsed. And it was as if a bomb had gone off.
you had workers trying to rescue their own. It was like Armageddon.
The race was on to scour the rubble for the injured.
Workers from every site being built in Bridgeport and surrounding towns descended on the area and started digging through the rubble by hand. By hand, no machinery, by hand, trying to see if they could find a survivor.
22 workers were injured in the collapse. Despite everyone's best efforts, tragically, 28 people lost their lives.
L'Ambiance became the largest construction accident in the history of Connecticut. You had international media that came over from Europe and even Australia that were asking, why did it collapse? Was this an engineering issue?
OSHA investigators arrived on the scene the same day and called in the National Bureau of Standards to help establish what had gone so badly wrong.
At the time of the collapse, many of the slabs were in kind of a holding position until they could be permanently fixed in their final location. So investigators focused on the lifting mechanism.
Engineer David Peraza was part of the investigation.
Each building fell into itself. All the slabs collapsed, they pancaked. Most of the columns were very severely distorted, kinked. They were like pretzels.
With the lift slab process, the columns were key to jacking the floors into place.
There was one column that stood out and was different from all the others. It was just a very gently arched column that seemed to have fallen down on top of everything else, after everything else had collapsed.
Instead of being crushed by falling slabs, the column had fallen onto the wreckage.
It turned out that this column, in fact, was the key. This was the column where the collapse initiated. At this particular column, the shear head was too large for the column. So this allowed the shear head to move laterally so much that it lost its support on top of the wedges. And it was only at this column and another column that error existed.
Based on this evidence, investigators came up with two main theories to explain why the shear head had come loose.
The failure theory that was put forward was that these metal fixtures, called shear heads, while they were strong enough, were excessively flexible. So, under the weight of 3 slabs, and subjected to the jostling and movement associated with the workers attempting to move those slabs into their final position, the lifting rods slipped out of their slots on one of the shear heads. That shear head came loose and it dropped down, and the shear heads surrounding it were suddenly overloaded, and they failed in the same manner, and a chain reaction collapse ensued.
The second theory cited problems with the welds.
So, under the extreme load of a package of 3 slabs being lifted, some of those welds failed, the shear head came apart, and a single shear head failed. And then from that point forward, the sequence of failure would have been essentially similar to a chain reaction collapse.
Whether the ultimate cause was excess flexibility or faulty welds, failure of just one shear head was the trigger that brought down both towers.
As they were falling, they were pulling in the rest of the structure, almost like a funnel shape, causing it to collapse.
With such huge forces at play, you can't afford to have any weaknesses in the system.
In 1992, 5 years after the collapse, a new apartment building opened on the same site. And just 1 year later, a memorial was dedicated to the memory of the fallen workers.
The inscription on there says it all. In their honor, some good has risen where so many tragically fell.
If any good came from the collapse of L'Ambiance Plaza, it put the lift slab building technique in the spotlight and ultimately changed the industry for the better.
One of the lessons to take from L'Ambiance Plaza is that very small errors can have catastrophic results. In this particular case, a little detail resulted in the total collapse of 2 buildings. The collapse of L'Ambiance Plaza really signaled the end of lift slab construction in the US.
Engineers have come to recognize the inherent risks associated with the method and have come to recognize that despite the great economy that can be attained from the use of the method, the risk just isn't worth it.
Some engineering fails lie hidden for years before triggering disaster. But others strike while construction crews are still hard at work. Like this tragedy in Canada, a catastrophic collapse in the nation's capital.
This was one of Canada's worst ever construction accidents.
Boom, everything went down. So you didn't even have a chance to move.
An engineering error revealed with devastating consequences.
The falsework collapsed into a pile of rubble and wet concrete.
It was so loud that it registered 3 kilometers away.
Ottawa, Canada, was established where the Rideau and Ottawa rivers meet. It was once a small trading outpost known as Bytown, then became the nation's capital in 1867.
Ottawa was picked as the nation's capital because it was centrally located between Toronto and Montreal, and it had great transport links by water, by rail, and later by road.
And the city has been growing ever since. James Powell is a local historian.
In the mid-1960s, the federal government wanted to move out of the downtown core and to build new office structures here on the periphery of the city. So the federal government was very keen on improving transportation links out here.
Key to improving those links would be this, the Heron Road Bridge. Completed in 1967, it connected the city across 2 waterways that had once divided it.
It spans the Rideau River here, and just further to the west, the Rideau Canal. One bridge for the eastbound lane, another bridge for the westbound lane.
When planning a bridge, engineers have to weigh up lots of different factors before deciding how to build it. What type of bridge is it? How high is the structure? How much space is there on the ground?
Here, the decision was made to build the bridge using 2 techniques. Engineer Tony Wing explains.
Well, the plan was to build a 7-span bridge out of concrete. They were using 2 different type of concrete structures. In 4 of the spans, the plan was to use cast-in-place post-tension concrete. And in the other 3 spans, the plan was to drop precast girders into those spans once these 4 spans had been constructed.
Because of their massive size, the 4 main spans would be poured in place into wooden molds temporarily supported by what's known as falsework.
The falsework was made of wooden members that were nailed and bolted together, creating a vast latticework box to support the steel and wooden molds for the new spans above.
What I've got here is a model that I've put together of the falsework of the Heron Road Bridge. So in this model, we have transverse frames that go across the bridge. We've got 2 of them in red, and we have longitudinal frames that go the length of the bridge. Without the falsework, you could not build the bridge.
But with the falsework in place, construction could start on the spans.
You pour the wet concrete into the form. At that point, the concrete does not support itself. It's all supported by the formwork and the falsework, and you have to wait for that concrete to harden.
Crucially, they had to bear their own weight, the molds, construction equipment, and finally, all the concrete for the new structure.
Wednesday, August the 10th, 1966. Construction was well underway on the cast-in-place spans.
The westbound lane was finished, was completed without any problems. The eastbound lane was half completed.
It was a warm summer afternoon. About 70 workers were on the structure, preparing for one of the job's big concrete pours, a huge 2,000 tons in all.
Mike LeCure was a rookie, working his second shift on the bridge.
I was 18 in my first construction job. I came down here on a Tuesday and I was assigned to work on this span here on the north span.
They were constructing the third cast-in-place span, which was much higher than the previous two, so the false work was much taller.
I went up and started shoveling the cement, and they were working with two of the large cranes and the big pots of cement to finish this span right here.
With cast-in-place structures like this, pouring the concrete is the most dangerous part of the project. For the first time, the false work has to withstand all that extra weight.
I remember looking up to the, like down further, a little down further that way, and there was something like moving on the bridge. Well, what was happening was the bridge was starting to go and things were starting to roll. But then, just like that, boom, everything went down. So you didn't even have a chance to move.
One witness said the entire span just flipped over, smashing everything beneath it down to the ground.
I fell the equivalent of 5 stories, and I went with all the cement, reinforcing rods, lumber, and all the rest of the debris that was up where we were working.
The false work collapsed into a pile of rubble and wet concrete and reinforcing into the valley floor.
And then I realized what had happened, and I realized I was still alive. But luckily for me, I wasn't knocked out, because if I had been knocked out, I would have been dead.
Rescue crews, workers and passers-by all helped to dig the victims from the wreckage.
Absolutely total chaos. Fire department, police, priests, even the mayor was here helping out.
A buddy of mine was up at the other end, and I knew he was there, and we had to find him, eh? So another friend of mine came from this span here, and he found me, and we kind of tended to, getting the cement out of my face, because I couldn't hardly see, because it was in your nose, in your mouth, because they kept pushing me down and down. Right? We eventually did find my buddy, and he sustained a pretty good gash in the back of his head. Luckily, he was at the lower end for him, but he had just come from this end here, and he left his buddies, and the buddies that he left, all of them died.
More than 60 workers were hospitalized. Tragically, 9 men died from their injuries.
Nobody was prepared for it. It was pretty horrendous.
The catastrophe left a nation shocked and in mourning. The Ontario government immediately launched an inquiry.
One worker who was cleaning a crane said he heard a crack, looked up, and saw the wooden false work start to bend before the whole lot came crashing down. That was a crucial clue for the investigation.
Investigators discovered a key piece of the false work was missing, as engineer Tony Wing demonstrates.
When you want to brace something, you brace it with cross-bracing or triangular members. If you try to deform this triangle, you can't. So engineers use triangles in their construction to brace members. In the Heron Road Bridge, they use lots of those in the transverse direction, but in the longitudinal direction, you see a complete absence of diagonal bracing. There's none whatsoever. All we have is horizontal bracing.
Horizontal bracing alone left the false work vulnerable to deformation.
When you're pouring tons of wet concrete into a mold, the forces aren't just acting downward. There's a lot of sideways, lateral movement too. And here, the false work just wasn't able to cope.
This is what happened during the collapse. Those horizontal loads caused the bridge to sway, come off the vertical, and then all of the red members, the vertical members, simply buckled, and the frames and everything came down in a mass into the valley, along with the concrete that was being supported temporarily by this structure.
With this one weakness, the bridge was doomed to fail before it was ever complete.
Simply put, had they been in place, the falsework would have been stable, and the concrete on top would have stayed in place, would have hardened, and it would have been a success.
Using redesigned falsework, construction continued on the bridge. And just under a year after the tragedy, on June the 29th, 1967, it opened to traffic.
Every time I cross the southern span here, I think about what happened 55 years ago.
In 1987, a plaque was erected to honor the victims. And 50 years after the collapse, the bridge was renamed the Heron Road Workers Memorial Bridge.
The guys that gave up their lives here, they should never be forgotten. Something I will never forget, and I don't think anybody in Ottawa will ever forget, like the carnage and the pain and the suffering. So it kind of hits you when you look at it again.
You have to have adequate design of the falsework so that the safety of the public can be ensured.
With standout structures, engineers walk a fine line between form and function. There's always a risk the balance will tip too far in one direction. Like this story in Australia, with critical reviews of one of the world's most iconic concert halls.
Performers and the audience have long said the acoustics could be better.
There's not enough room for the sound to get out.
An issue that has reverberated for half a century.
It's always been quite controversial amongst musicians and performers.
This just goes to show looks aren't everything.
Sydney, Australia, is regularly voted one of the most livable cities on Earth. It's also one of the most iconic, thanks in no small part to this, the Sydney Opera House. Journalist and author Helen Pitt has long had a passion for the groundbreaking structure.
The Sydney Opera House is probably our most beloved building in Australia. You look at that picture and everyone can immediately place you in Sydney. It's become our international calling card.
There are few buildings on Earth as unique and iconic as the Sydney Opera House. You wouldn't know that it was designed more than 60 years ago.
The now famous shells were first conceived in the 1950s in response to an international competition.
The competition attracted a host of Europeans, including a Dane who was entrant 218, so he's a little late in terms of the competition entries, and a fellow Scandinavian is said to have picked up this one and with a flourish turned to his judges and said, "Gentlemen, here is your opera house."
With the winner picked, now came the biggest challenge, building it.
This is a world-class opera house, and the audience would expect a world-class view. So there could be no columns between them and the stage.
The concrete skeleton inside the infamous shell design would have to be entirely self-supporting.
When the Opera House was conceived, nothing like this had ever been built. It took 4 years to just figure out how to make the shells strong enough to support themselves.
The engineering was seriously complicated, and the project was far from plain sailing.
It was budgeted to take a couple of years and $7 million. It took 17 years and cost $102 million.
Finally, in October 1973, the project was complete, and Queen Elizabeth II officially declared the Opera House open. Although striking from the outside, the real purpose was to sound good on the inside. Acoustics expert Professor Denzel Cabrera has extensively studied the Opera House.
The main purpose of a music auditorium is to send sound to lots and lots and lots of people. And the auditorium contains that sound. And as well as making the sound loud enough, it also provides a reverberation, which many people find beautiful and enhances the quality of certain types of music.
Getting the acoustics right is like mixing a highly complicated cocktail, balancing materials, geometry, physics, even neuroscience. so that the audience can enjoy the best possible acoustic experience.
Although it was 17 years in the making, in this one crucial quality, the Opera House started to receive mixed reviews.
The Opera House is clearly a very inspiring venue to attend, as well as the dramatic exterior, and the sound is pretty good. It could be better though.
So it's always been quite controversial amongst musicians and performers, the actual things that it delivers acoustically.
The obvious question was why. It all comes down to a decision made years before the Opera House ever opened its doors.
The original plan was for the opera to be in the larger shell, but at the time, symphonies were more popular than the opera, so the decision was taken to swap the two. Ultimately, neither was the right size for the job.
The trademark shell design added to the complications.
The issues with the concert hall stem largely from trying to fit a large concert hall into the limited space that was available underneath the shells. So that makes the concert hall a little bit narrower than perhaps it should have been. There's also a very high crown in this auditorium, so the sound from the stage going up to the top, the ceiling, and back down to the stage creates an audible echo.
The problem wasn't just in dimensions, but in shape too.
Adding to this issue is it has a ceiling shape a bit like a hat. And so we have these areas around the edges that have quite low ceiling. And that means that the seats underneath those low areas don't get the sound that's reverberating around the upper part of the auditorium.
As well as the overall size and shape, specific surfaces compounded the acoustic confusion.
The original acoustician put in 90-degree sawtooth surfaces to reflect the sound back to the stage. This is a phenomenon known as retroreflection. The reflectors have to be big enough to reflect the wavelengths that we care about. But unfortunately, they'll only reflect high frequencies because the sound wavelengths in the mid and low frequencies are much too big.
The issues weren't limited to the concert hall. The smaller theatre had a major problem, for the audience and performers alike.
The Opera Theatre orchestra pit is notorious because it's kind of buried underneath the stage and there's not enough room for the sound to get out. So it's too loud for the musicians and not loud enough for the audience.
Ultimately, although a monumental visual success, Sydney's prize landmark has never quite hit the same heights with its acoustics.
The Opera House opened nearly 50 years ago, and over the decades, various fixes have been tried. But in 2020, to try and sort the acoustics out for good, this icon actually closed its doors for a 2-year mammoth refit.
One of the modifications that's being done to the concert hall is increasing the surface area of the reflectors. This will reduce or eliminate the floor-ceiling echo and also provide the musicians with a better lower mid-frequency, maybe a warmer sound. They'll be able to hear each other better.
And the troublesome sides of the stage have also been reconfigured.
The faces of the vertical elements around the stage, these have been replaced just recently with wavy surfaces. Wavy surfaces provide a diffuse reflection, which means that the sound comes from a large surface area in a diffuse way to a listener, rather than coming as a chunk from one direction all at once.
When this huge renovation project is finally done, the hope is that Sydney's iconic opera house will sound every bit as amazing as it looks.
I still feel it every time I fly in and out of this beautiful city. I don't see the Sydney Opera House, I see my Sydney Opera home, and that's what it means to most Sydneysiders. It's not a house, it's our home.